Well, it looks like it's time to get started. So let's start with section 1 of chapter 1, discussing descriptive statistics and some basic terminology of statistics. So, right, let's get to work then. So, so in this chapter, in this section, we're first going to start out with some basic terminology. Let's start out with data. Data is what statistics is interested in. We're going to say that data is basically a collection of facts. We have generally a population or some group of interest for which we want to make some statements. So if we were to collect data for the entire population, then we would have conducted a census. Let's have some examples. There's the classic example of the United States, because right now we're actually in a census, the 2020 census being conducted by the Census Bureau. And this is a massive undertaking by the US government, mandated by the Constitution, to count every single individual currently living in the United States. And with that, to get a count that is supposed to be a complete count, not an estimate, but a count. This becomes the facts of how many people are currently living in the United States. On a smaller scale, there is this class, and I presumably have the grades for this class. So if I were interested in the grades of this class, I could conduct a census by looking at the grades of every single student. And with that, I would have the entire data set, the entire population, where I've defined the population to be this class. Now, that said, you may not necessarily have access to the entire population. For example, in the case of the United States, the census is an extremely expensive and complex undertaking that can only be done every 10 years. And in the case of this class, while I can conduct a census, you yourself as a student may not be able to conduct a census. So if you were interested in how your other fellow students were doing in the class, you would be forced to collect a sample. A sample is a subset of the population for which you manage to collect data. So in the case of the class, if you were to talk to some of your friends, which may not be the greatest idea anyway, but if you were to talk to some of your friends about how and ask them how they were doing in the class, then you would have selected a sample. Whereas in the United States, we're regularly subjected to surveys where a subset of the American population is going to be examined. And you're going to ask questions about them. And in the case of the Census Bureau, they have a lesser intensity project, such as the American Community Survey, which isn't aimed at getting the entire population. I think every year they try to get 1% of the population, which is big in and of itself. All right. So in a sample, we have observations. So maybe these are people, but in principle, they could be just about anything. Like they could be petri dishes, they could be the price of a stock on a particular day, something like that. And with those observations, we have variables. So in the case of our little person over here, who is an observation in our sample, we may have tracked their age. We'll say this person is 22. We may track their gender. We'll say that this person identifies as male, or maybe we are tracking, I don't know, their occupation. And we'll just say that this person is a student. All right. So univariate data is a data where there's only one variable being tracked. So in this case, if all we did was track age, then this would be a univariate data set. But this is actually a multivariate data set because we're not only tracking age, we're also tracking gender and occupation. So that makes this data set multivariate. Presumably there's more than just this individual in our sample. Maybe there are some other individuals too for whom we've collected some data. In this case, this would be a multivariate data set. There is kind of a special case for the multivariate case, which is the bivariate case. And bivariate data is a data where there's two variables And when you have only two variables, at least in this class, we can start talking about ideas such as correlation. How are two variables related to each other? You can do this for general multivariate data too, but that's kind of going beyond the scope of this course. And even then, you kind of start out with the bivariate case first. So, data itself, the variables can come in different classes, such as there can be categorical variables. So an example of categorical would be gender and occupation. These would be categorical variables because there are a finite number of categories that these could be in. Compare that to, say, age, which we would consider quantitative, because what's being tracked is a number, presumably an unbounded number. Now you might think, well, what about, say, the roll of a dice? If you're rolling a dice, then there's only a finite number of numbers 1 through 6. This is pretty much a simplification. More with categorical, we're thinking with things where there may or may not be an ordering, but we really don't want to view categorical data necessarily as numbers per se. Whereas quantitative are numbers, right? And there's also alternative formulations, alternative breakdowns with maybe some more granularity on how you're going to break down data. Like, for example, you might say there's nominal data where it's just categories that have no relation amongst each other. You might then progress to ordinal data where you do add a little bit more structure, where one value could be considered greater than another. Maybe we could talk about a person's year in college, in which case you would say that sophomore is less than, in some sense, junior, which is less than senior. Although you don't necessarily want to attach numbers to freshman, sophomore, junior, senior. And then you could have maybe interval where you're allowed to do addition, and ratio where you're allowed to do division. So, but yeah, that's an alternative breakdown. Don't worry too much about it. In modern statistics, we depend very heavily on probability theory. Probability theory is a field of mathematics that describes the behavior of objects in the presence of uncertainty. The mathematical study of probability, we've known about probability as a species for a very long time, at least since the Greeks, but it's only until around the time calculus was being developed when probability started to take a mathematical interest, and then it was around the beginning of the 20th century where probability became its own proper field in mathematics. So why do statisticians care about probability? How is probability used in statistics? Well, we have this relationship. We have a population, and we have a sample. So a sample is a subset of the population. So the question is, how is it that we get a sample from the population? When we collect a random sample from the population where every individual in the sample is picked with equal likelihood, how will that sample behave? How will statistics computed in that sample, such as, for example, the sample mean, or even then, like going beyond mean, like let's say we track the smallest age. How will statistics like that behave? The behavior of those statistics is determined by probability. So probability describes how random samples from a population behave. And as statisticians, we develop probability models for our samples and then use those probability models to describe parameters of the population. So this would be statistics. So probability and statistics are working in inverse directions, where probability describes how, if you knew the population, how will the sample behave, whereas statistics is interested in, given a sample, how can we infer the properties of the population, like, for example, important population parameters. So, okay. All right. So let's continue on. How we define a population largely depends on our problem. For example, in the examples that I gave before about the United States and my class, we would consider a study involving those populations enumerative studies, since in principle there is the population exists. The population exists in physical and temporal space. So that means that there's no, like, you can actually find, in principle, every single individual in the United States, and you can find every single individual in my class, and a census is in fact possible to conduct. Now, compare that instead to analytic studies where the population may not exist. So, in my previous example where I was talking about petri dishes as being a potential sample, a petri dish for some bacterial culture is probably going to appear in an analytic study. A lot of those biological studies are going to be analytic studies because the population isn't necessarily considered existing. Or in a simpler case, if all I wanted to do was determine whether a single dice that I have was fair, in principle, you can't really say that all of the possible rolls for this dice exist in some physical temporal space. I can keep rolling this dice forever. So you can't really consider it an enumerative study. So you're just going to say the population is all possible die rolls for this dice. And in the case of a medical study, you might say that the population is all humans, past, present, and future. And we're studying the behavior of some drug in humans. We're thinking of humans as some biological, as a human species, as a biological entity. Not necessarily the current people who are living right now. We would probably want to include future people too. All right, so statistics it depends very crucially on how the data is collected. And we're not actually going to talk very much in this class about how to collect data correctly. I'm just going to leave you a few words. In this class, we're going to assume that data was collected via a simple random sample. So if data was in fact collected via a simple random sample, then there is a sense in which every individual in the population is equally likely to have been chosen. The metaphor that I like to think of is we have a hat, and that hat has little slips of paper, and each of those slips of paper will identify individuals in our population. We pull one of the slips of paper at random with equal likelihood from the hat, and that gives us an individual in the population that will be included in our sample. Compare that instead to stratified random sampling, which is a more complicated procedure, and the procedure that the Census Bureau is actually going to use in these annual American Community Survey studies, where in this case you actually divide up your population according to some known strata. A strata is something that you automatically know for individuals in your population, for example, what state they reside in. So you divide up your population into strata, and those strata don't necessarily have equal size, but you're going to pick a random sample from each strata, a simple random sample as I described before, and then make inferences. And this procedure, the stratification procedure, can increase the power or the ability of your statistical procedure without having to collect as much data. So it's a nice procedure to have in hand. It's the procedure that is being used in more complicated surveys, but we're not going to discuss it here. The procedures that we discuss here are not appropriate for stratified sampling. So it's, of course, very easy to sample badly. So one instance of bad sampling is convenience sampling, where you're basically selecting individuals from the population based on how easy it is for you to get the data. In the case of this class, if you were interested in how and what the grades of this class were, and you decide to ask some of your friends what their grades are, that's a convenience sample. It is not a random sample. Because in the end, the sample is going to resemble you in some way. It's going to be more a reflection of you than it is of the class. So you may end up, if your friends are like better students, and that's because better students like to commingle, then that could be a problem because you're not going to get an accurate view. Or let's say we're studying politics and you decide that you want to determine people's political party affiliations. So you stand outside of the Marriott Library on campus and you start asking students, what party do you support in elections? In that case, you are not going to get anyone from St. George, Utah. Almost sure. Well, I mean, you might get a couple people, but for the most part, St. George, Utah will be extremely underrepresented in your sample. And that's going to be a problem. Now you don't have an accurate representation of the state of Utah. If the state of Utah were in fact your population of interest, and even if the University of Utah itself were your population of interest, not every student is going to be hanging out around the library, so that'll be a problem. Or in the case of voluntary sampling, where like the classic example is a TV host goes and tells his viewers to participate in a survey. It's like, who do you like, the Democrats or the Republicans? And it's like, oh my gosh, all my viewers like the same party as I do, and they agree with me. No shocker. So that would be a case of a very unreliable study. Yeah, that's another thing. But we're not really going to talk too much about this. This section, I mean, there's a lot that can be said about how to appropriately sample. And actually, this is one area where current events, I would like to say some more about it, like the coronavirus. What are some of the statistical issues surrounding the coronavirus? Because there's a lot of statistical issues involving the coronavirus and our understanding of it and its effect on the population. And I'm thinking I'm going to leave that to a separate video. But for now, that is the end of this section, and I'll see you in section 2 on pictorial tabular methods in descriptive statistics. So, all right, best of luck to you. Hey students, all right, so next section is on making graphs and making tables for descriptive statistics. All right, so first, let's describe the idea of a distribution. When we're talking about random variables, there's a couple things that we should keep track of. There is what values a random variable could take, and there's also how frequently those values are taken. Those ideas are captured in the distribution of the data set. So in this section, we're going to see some basic ways to understand a distribution of an observed data set. And in later sections, we're going to talk about the idea of the distribution of a population and how it could possibly extend the idea of distribution. And one basic way that we could understand a distribution is using a table, and we can also use visualizations. Visualizations can actually be very helpful in understanding a distribution because there are things that our eyes are very good at picking out. And when we make pictures of our data set, we pick those things out. Like, for example, where does the data tend to cluster? How spread out is the data? Are there outliers in the data set? Influential observations. And our eyes are actually very good at noticing those features. So creating visualizations of data sets can lead to us learning a lot that actually really cannot be learned by numbers on their own. In fact, there are some examples. For example, there's this thing known as Anscombe's quartet. Maybe I should very quickly have a look at Anscombe's quartet, because we can do that very quick. Okay, so let's see. WK Anscombe. Is it B? Quartet. This is close enough. It'll probably figure it out. Is it Anscombe? And I can't type. Oh, okay. So it has a B in it. All right. So there's this picture right here. and this is known as Anscombe's quartet. This is for a bivariate data set, which is not what we're talking about right now. But when working with bivariate data sets, you want to track, for example, the mean of X and the mean of Y, and also if you were to come up with a best fitting line, a regression line between the two variables, what would the parameters of that line be, and what is the correlation between the variables? And numerically, every single one of these data sets are exactly the same, even though our eyes can see they are not the same at all. These are clearly not the same data set, and they have very different properties. So making visualizations can help us learn a lot. In fact, this is a subject in and of itself. You can take a class from the computer science department on just visualization. But we're not going to be going into that much depth in visualization today. What we learned today is pretty much enough to get you by in life, unless you're doing some really serious work. So from this point on, in this video and future videos, I use this notation to describe a data set. And this data set has sample size n. So the sample size is the number of observations in a data set. The indexing here, we have x1, x2, xn. The indexing, the numbers themselves don't actually matter. They're just a way for us to differentiate observations. These observations may have the same values or different values. It actually doesn't really say all that much about the data set. In particular, I don't want you to look at this and think that this data set is now ordered. This data set is not assumed to be ordered. If the data set ever becomes ordered, I will let you know. But right now it isn't. I also would like to draw attention to the fact that this is in lowercase, and it's not a perfect rule. I've often violated it, but it is a hint that lowercase things, and this will probably be the case in the videos for this class. It is generally the case that lowercase numbers are constant, and a data set is constant. A data set is something that you observe, and because you observed it, it is now constant. Whereas capitals often refer to random things, which is not what we're going to talk about today. So the first visualization method that we're going to talk about is very basic. It's called a stem and leaf plot. So we create a stem and leaf plot using the following steps. The first thing we are going to do, given a data set, is we're going to select the number of leading digits to be the stem values. So we have a number, maybe that number is 123.45, and we're going to select some number of digits, maybe the first two digits, and these will be the stem values. The remaining values, let's use a different color for that. Where did red go? The remaining values will be the leaf values, which in principle you could put like the entire block 3, 4, 5 as a leaf value, although a lot of people will just like round to just one digit because, well, you'll see for a second why someone might be inclined to do that. So after you make that selection, you're going to draw a vertical line. Let's not use that color. We're going to draw a vertical line, and we're going to list the stem or possible stem values on the left-hand side of this line. So we might have 12, 11, 10, and maybe 13, and 14. And on the right-hand side of this line, we would record the leaf values. Let's assume for a second, just for simplicity, that we didn't observe this part, and all we saw was the 3. We might list 1, 2, 3, and this would be read off as 123. Because according to part 4, we're somewhere in this display, we're going to indicate the units of the stem. So we might say, in this case, tens, to indicate that the stem is tens place and beyond, which means that everything to the right will be in the ones place. Or maybe we're doing a more advanced plot where maybe we actually did write 3, 4, 5. So this would be 1, 2, 3.45. But we're not going to do that because I actually think that would be... It kind of defeats the purpose of a stem and leaf plot, because what we would instead do is list the leaf values for each observation or data set. So maybe you saw 101, 101, 2, 3, 4. So we have an observation 114 and another observation that's 113 and another observation that's 112. Or we'll also even throw in a 9. So there's an observation that's 119. We got 123, 130, and 144. And now we have a display. Let's just throw in like one more number, like right here. Now we have a display that actually later on we're going to see a histogram and say, oh, this actually looks a lot like a histogram. But we do have this display that's indicating that's telling us a lot about this data set. For one thing, it actually tells us the actual values in the data set. That's one advantage of a stem and leaf plot. When you have a stem and leaf plot, you get to see the actual data values, and that's one thing that's nice. Another thing that's nice about them is that they're very quick to create. Like, I imagine a stem and leaf plot being created in the field. Like, you are out there, you are watching, birds and tracking how many birds you're seeing or characteristics of birds, and you actually get to write down, as you are recording your data, you're also visualizing it so you can learn things about it, because you can see, like, for example, this data set seems to cluster in this 100 and 110s area. We might be able to guess that the mean is somewhere around here, that this is like where the center of the data set is, and we get some sense of its spread. All right, so here is another data set for us to practice with. This is a subset of McDonald's data on height and finger lengths, and this part right here is actually R code. So we could go into R and type this part in and use R to do some of this analysis. So, and I'll actually show you a little later how this can get turned into, like what R would do with this part. But we're just going to take this and treat it as our data set and construct a stem and leaf plot by hand. So what are we going to do? We first need to decide where we're going to make the cutoff. We're not going to make it in the ones place, because if we put it in the ones place, then there's going to be just 5 for our stem value. And what you'll end up with is a plot that looks like this, and it will be just like a giant skyscraper, and you won't learn anything. So we don't want that. So the next place that is available to us is the 10th place, and the 10th place seems pretty good. So I'm now going to make the line for the stem, and I'm going to write, let's see, we've got 5, 3, 5, 5. We have a 5, 2. Oh, we also have a 5, 0. So we'll put 5, 0, 5, 1, 5, 2, 5, 3, 5, 4, and we go all the way up to 5, 9. So 5, 5, 5, 6, 5, 7, 5, 8, 5, 9. Okay, there's some dead spots on this super cheap computer. I bought it for $200 at Target across the street, which was the most convenient place to buy a laptop super cheap. So you get what you pay for, and I'm especially learning that right now. Anyway, so we now have the stem values, and now we can start recording our data set. If you were to do this in a computer would actually order the leaf values. Here they actually are ordered because 9 comes after 4, which comes after 3. So a computer would actually order it. I don't really see the point, because the point is to understand the distribution as in a visual way, and ordering the leaves does not aid in that. So we can go ahead and just start reading across in this data set to make our stem and leaf plot. So we've got 5.55, so we'll put a 5 right here. 5.30, so we'll put 0 there. 563, 530, 513, 505, 538, 596, 5, 2, 1, and 5, 3, 8. So in this case, it actually turned out to be ordered, and that's pure coincidence. I wasn't planning on that. But now we have a stem and leaf plot. And if we scroll down, or if you actually have these notes printed out, one last thing we need to do is indicate what this line means. And this line is the tenths place. Okay. All right, so if we were to continue on to the next page, we would actually see some R code that would do this. So this is the height data set from before, this part right here, the R function. Oh, okay. So this is the same height data set we had before. The R function stem creates stem and leaf plots, and this is basically the same as we had before. Okay, before I continue on, I'm just going to double check to make sure I'm still streaming. Yeah, we're still streaming. Okay. All right. Okay. So next up for our visualizations, we have a dot plot. A dot plot represents each data point as a dot along a real number line. So we would then be looking for clusters in dots to note patterns in our data set. So in this example, we're going to use the data from the previous example, which has already been very nicely organized for us in a stem and leaf plot to create a dot plot. Let's see. Is there a nice, easy way to zoom out? Oh, very nice. Oh, that's not what I wanted. That's delete. I'm new to this program. And we're at the very bottom too. That's not what I want either. Okay, so all right. So this program is new to me. My apologies. All right. So all I want to do is zoom out a little bit. Okay, that's good. That's good. Oh, cool. All right. I just want to be able to see this nice stem and leaf plot that we created before when creating our dot plot. So for our dot plot, let's see. We've got, let's see. So for the left point of the range, we should pick 5.0. And for the right point of the range, we should probably pick 6.0 because we get really close to 6. So in between, we've got 5.5. And then we can just mark off in fifths. So 1, 2, 3, 4, 5. Okay, that's close enough. If you want perfection, ask a computer to do it. All right, so we've got an observation 5.05. So that's about right there. 5.13 is about there. 5.21 is about there. And then we've got 5.30. That is about there. And that's also got another one right with it. There's another observation. That's actually could be a little bit to the left, but we could also call that 5.38. So here's 5.30 for realsies this time. We've got 5.55, 5.63, and then 5.96. So then we end up with this dot plot. That's also giving us a sense of where the data tends to lie, but this time along a real number line. So, and I'm sure you can guess so far that the methods that we have been working with, our visualization methods are pretty much devoted exclusively to quantitative data. We'll see categorical in a second. I'm pretty much going to say draw a bar plot, and that's it. So here is our code for what I just did. The R function for making dot plots is strip chart. So strip chart is what makes these things, and I'm just passing some additional parameters to strip chart to make the function to make the plot how I like. Like for example, this parameter right here controls how what exactly we're drawing here. Are we drawing filled in circles or empty circles and so on? So this, you can think of this as point character because you're choosing the character of the point, and 19 corresponds to a filled in circle. We have a little bit of an offset and some other parameters that just help make the visualization look nice, I would recommend going ahead, firing up R, playing around with these parameters, seeing what happens. Stack, for example, means that when 2 points are about to collide with one another, stack them on top of each other. Because it's not the only way to do things. There are often very many ways to solve the same problem. So, all right, continuing on. So a quantitative variable, we need a further refinement of quantitative variables, and we say that a quantitative variable is discrete if its possible values are countable. Countable, that could be, for example, 1, 2, 3, 4, 5, 6, or that could be 1, 2, 3, 4, 5, 6, 7, 8, 9, blah, 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 up into the future. It could be the integers, so including negative numbers as well, or including 0 as well. And then, so we would call any of those things countable. There's also continuous variables, where the possible values could come from a continuum, so that includes 0, 1, and anything in between. So 0, 1, 0.5, 0.011012, 1 divided by pi, any one of those things are possible. There's actually a nice little rule of thumb, which is that discrete variables emerge when you count things. Like, for example, I count sheep. So what am I going to get? I'm going to get an integer in the end. So if that's going to be the case, then it's countable. Whereas continuous emerges from measurements. So like with a ruler. So you measure how long something is with a ruler, and that will probably produce a continuous variable. So continuing on, some further notions when describing a distribution. There is the frequency of a value, and there's also the possible values it could take. So the frequency is how frequently we see a variable take a particular value. And for discrete variables, it is in fact possible and quite likely that we will see the same numbers repeatedly. Whereas if we're dealing with continuous, you cannot necessarily assume that. So the frequency for each value for a continuous variable would be rather uninteresting, since you're probably going to see, like going back to the data set we were just looking at, admittedly, for this height data set, we did have some collisions, but you can't really count on that. You can imagine that if you were to increase the decimal precision of the numbers that you're looking at, you would actually not have a collision. You'd have two distinct numbers. The only reason why we get 5.30 twice is because that's where we decided to round. So if in the case of continuous variables, while with discrete variables, it's okay to just kind of consider the values in and of themselves and just say, how many times did 1 show up? How many times did 2 show up? And so on. For continuous variables, we probably should do a procedure known as binning. So binning is where we define a range in which a data point could possibly be, and instead of tracking how frequently a certain value is taken, we're going to track how frequently a variable will fall into a bin. Right. So you can imagine, for instance, that this is a continuous line between 0 and 1, and we saw numbers in this region, and they're just random numbers, and we're not going to actually list out in a table how often we saw those individual numbers, because most of the time the frequency for that number will be 1. Instead, what we'll do is we'll divide up this region and then count how many times numbers fell into those individual bins. Like, for example, we got twice here, 3 times here, 1, 2, 3, 4, 5, 6 times here, 1, 2, 3, 4, 5, 6 times here, and then 4 times here. And then we'd have like a more useful table for understanding our distribution. Very closely related to the frequency is the relative frequency. Relative frequency is where you take the frequency and divide it by the sample size. That's it. So if you really want to see a formula for the relative frequency is equal to frequency divided by n. A frequency distribution is a tabulation of the frequencies or the relative frequencies, or in the case of continuous variables, we'd probably also include the frequency of bins. Something that I haven't really discussed so far is that actually, how should we choose the bins? Like binning is a choice. I chose these bins, but alternatively, I could have chosen bins like this. Like, here's one bin and here's another bin. Why didn't I do that? So the actual binning decision is in fact a decision. You need to decide how many bins they are and what regions they're going to cover. So in terms of the regions, I think it's pretty safe to say the bins should be equal length. If the bins are not equal length, then what you're going to end up with is a difficult to understand chart or a difficult to understand table, because people then have to pay much more attention to the bin length. And also when you're trying to visualize what's like this is leading up to histograms, and the bin size is something you have to make when talking about histograms. And when you end up with bins of unequal length, then the histogram, there is a precise way to understand what's being visualized in the histogram, but unfortunately, people's eyes are not going to perceive it that way. And you are making the histogram more difficult to understand. So just always make your bins equal length. But the number of bins that you have, and also what exact regions they cover, because you can still, for example, take all of these bins shown here, take all of these bins and then shift them slightly to the left, and then you have a different visualization, or you then have a very different description of your data set. How exactly should you decide where the boundaries of your bins are, and how many bins should you have? These are all very important decisions that can have drastic implications for visualizations. But I really should move on to actually creating a frequency distribution, which is a tabulation of frequencies or relative frequencies. I should really move on before I start digging into that topic. So let's make a frequency distribution for this soccer data set, where we have a supposed statistically minded parent. Maybe that parent is you if you have a daughter or a son and they play soccer, and you've decided that you're going to track their little league soccer team scores during a regular season. So here I have a data set. And by the way, what I've done here in terms of R code is created an R vector. So I have this list of values in what's known as an R vector. I'm not really going to talk about R in these videos. I'm going to pretend and assume that you are watching my video series on how to use R. But enough of that for now. I want to construct a frequency distribution for this data set. So what are possible values in this data set? Let's see. We've got so on the left-hand side of this line for this table, so we're going to have a value, and we're going to have on the right-hand side the frequency. So what are possible values? Well, we've got 1, and we've got 9, and we've got numbers in between. So we'll just go 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, and then we need frequency. So let's see. How many times did 9 appear? Looks like 9 just appeared once. All right, so we got that covered. 6 appeared. So 1, 2. Yeah, that's it. So 6 appeared twice. 5 appeared 3 times. And 8 appeared twice. And each of the remaining numbers appears only once. So 1 appeared once, 2 appeared once, 3 appeared once, and 4 appeared once. Okay? 7 never appeared. All right. 1 second. I catch up in my notes. So the sample size for this data set, you can count. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 observations. Or alternatively, what you could have done is, and in fact, I'll go ahead and just kind of scroll down a little bit. And down here, I'm going to track the sum. And yeah, it adds up to 12. Another thing I want to do is, in this table, track the relative frequency. So we'll call this relative frequency. And in the relative frequency, I'm going to take the frequency and then divide by the sample size. So 1 divided by 12, that is going to be 0.05, or is that an 8? No, that's an 8. 0.083, and the 3 is a continuing digit. All right, so for the next one, it's the same thing, 0.83. And again, for 3, 0.083. Okay, and then for 5, no, wait, so let's see. 4 also appeared that amount, so 0.083. 4 appeared 3 times. So that's going to be 0.25. Because 3 divided by 12 will be 0.25. 3 is a quarter of 12. 6 will be 0.16, where the 6 is a continuing digit. 0.16, and 0.083. Okay, and if you add these numbers up, this is a way for you to check your sanity. This should add up to 1. Okay. So moving on, if you were interested in how to make a table like this in R, the function for R, in R for making such a table is, well, table. So you would have given it the soccer data set and asked it to make a table, and it will tabulate which observations were taken and how frequently they were taken. Notice that it did skip 7, which, I don't know, is that a feature you want? I don't know. I actually personally would rather not skip 7, and you'll probably see why in a second. When working with continuous data, as I was mentioning before, there's this issue of binning, deciding on the number of bins, deciding where the boundaries of the bins are, and so forth. But once you've decided on the number of bins, and there are some rules of thumb that you can use for how many bins that you should use. Like, for example, if the sample size is n, you could perhaps choose the number of bins to be the square root of n. Actually, there is some statistical arguments that the correct number of bins should be on the order of n to the power 1/5, or the 5th root of n. There are some arguments for that, but square root of n is also fine for now. At the end of the day, whatever it is that R is going to use for its binning decisions is better than what you're going to do. And it's going to have some nice theory backing it up. So you probably should just trust R. Whatever R is doing is probably better than the square root of n rule. So after you've decided on the number of bins, you segment your number line so that you have that many equal length bins. And depending on where each data point falls, assign it to a bin. If it falls on a border between the bins, assign it to the bin on the right. So in other words, bins are right inclusive. That is a parameter. Some people prefer left inclusive bins. Does it really matter? No, it doesn't. It doesn't really matter. Nobody really cares. Just pick one, right? And be consistent. Either put it on the left bin or the right bin. Just don't put it in both, please. And then construct a frequency distribution for the bins. Very quickly before I keep going. Okay, we're still good. All right. I'm very nervous about losing this video. I'll just put it this way. today I've recorded a number of videos that suddenly just went up into thin air because things went bad, and I don't want that to happen again. All right. Example 4. So using the data from example 1, you can go back in time to see what that is. This is the heights data set. Construct a frequency distribution. And for what it's worth, there were 10 observations in that data set. The function length, when given a vector, will tell you the number of elements in that vector in R. So since the number of elements is the number of data points, we want to use length to determine the sample size. Okay. Continuing on, I have made some decisions. I'm going to decide that the number of bins I'm going to use is going to be about the square root of 10. The square root of 10 is between 3 and 4. So if you wanted to use the square root of 10 rule, that would be about, we'll say 4, rounding up. Although, apparently in my notes, I decided that I was going to go with 5. And I don't want to change it. So I'm going to go with 5. Why 5? Why not 5? It's whatever you want. I think the reason why I went with 5, I don't know. I just did. So, let's go ahead and zoom. Oops, is that what I want? Yeah, that's fine. Okay. So, I'm going to make a table. So in this table, I'm going to list the bins. So I've got 5 to 5.2, and to indicate that this is going to be right inclusive, I'm going to put a little less than sign to say 5 to less than 5.2, not including 5.2. And then 5.2 to 5.4, 5.4, hold on. Okay, 5.4 to 5.6, 5, I need to kind of get away from there. Okay, 5.6 to 5.8, and then 5.8 to less than 6, and we can just leave it at that. All right, and then we have the frequency for each of these bins. So the frequency for these is going to be, well, there were 2 numbers between 5 and 5.2, 5 numbers between 5.2 and 5.4, and then 1 number in each of the remaining bins. So if we were to do the relative frequency, we're going to take each of those frequencies and divide it by 10, in which case you're just going to move the decimal point over one place. So 0.2, 0.5, 0.1, 0.1, 0.1. Okay? All right. Once we have a frequency distribution such as this, we can now construct what's known as a histogram, which is a plot for visualizing the distribution of quantitative data. So how do we construct a histogram? First, draw a number line and mark the location of the bins. So for example, we could do something like this, and we're going to say that the bins are going to be about here. And then if you want to, for discrete data, you can center your bins on the corresponding values themselves, because you're not really doing any binning with the discrete variables. Or you can imagine that your bins are exactly what they need to be touching each other and centered on the integer, the corresponding integer. And then for each of these classes or bins, draw a bar extending from the number line. So we have some y-axis that's tracking, let's say, the frequency. So we have a y-axis that's tracking the frequency. We're going to draw a bar from the number line to the y value that corresponds to the frequency of that bin, or the relative frequency if that is in fact what you're plotting on the y-axis. So we would end up with a plot maybe looking like this. And that resulting plot is a histogram. So, back to some of our examples, let's draw a histogram for the data set in example 3, which was that soccer data set. So for the soccer data set, we had numbers between 1 through 9. We'll go ahead and include 0 as well for this data set. So I'm going to start out by drawing the graph. The x-axis corresponds to goals. So goals in a game. And the y-axis corresponds to the frequency. So let's see. The frequencies never seem to go beyond 3. So we've got 1, 2, 3. Okay, and then possible integer values. I'm going to go ahead and include 0 because in principle this soccer team could score 0 points. So we'll go ahead and include 0, but we'll also include at the very end we'll have 9, and we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so there was one game where they scored 1 point, one game where they scored 2 points, one game where they scored 3 points, and one game where they scored 4 points. Then they had 3 games where the team scored 5 points, 2 games where they scored 6 points, no games where they scored 7 points, 2 games where they scored 8 points, and 1 game where they scored 9 points. Okay. New feature. Let's go ahead and see what happens when I... No, I don't think that works. Oh well. So there would be the histogram. It's not a perfect picture, but it's mine. So if we wanted to, down here is the R code for constructing a histogram. So the R function is hist, and I've given it some parameters to manually specify the breaks because otherwise it would choose its own algorithm. It would use its own procedures to come up with the breaks. And I wanted to override that, and this is one way to do it, where I basically gave the function the break points. So the minimum of soccer is going to be 1. So 1 minus 0.5 will be why can't I do math? It's 0.5. And then I went 1 above the maximum score, so that would be this number right here. So this right here corresponds to 0.5, and this will be 9.5 over at the right hand side, and that's just telling it where I want those breaks, and then it will infer that that everything in between is a bin. But then you end up with a plot that is essentially what we came up with by hand. Okay. Next example for the data set in example 1, let's create a histogram. Okay, so for that one, I am going to use the relative frequencies instead. Which do you use? At this point, it doesn't really matter because the shape is going to be the same regardless of whether we divide by n or not. And the interesting part when you're creating a histogram is looking at the shape of the resulting histogram. So I actually really don't care, although, for what it's worth, if you wanted to use this thing for more probabilistic inference, you probably should pay more attention to whether you've got the frequency or the relative frequency. And if also the bins were not of equal length, then you would have to pay much more attention to the frequency versus relative frequency, but also just take my advice and make your bins all equal length. So we've got the relative frequency. That is what we're going to draw this time. And we've got the highest it will ever go is 0.5. In fact, I don't think it ever reaches there. So we've got, right? Yeah, it does. It does reach 0.5. So, and we'll just increment by 0.1. So 0.1, 0.2, 0.3, 0.4, 0.5. So this is 0.1. right here. So possible bin values, I decided that we were going to have 5 bins for some crazy reason. I don't remember what it was. And so let's see, is that 5? It is now. So we've got numbers between 5 and 6, and using the table that we came up with that time ago, we're going to end up with a histogram looking something like this. So it goes up to here, and then oh yeah, so it goes to 0.2 and then 0.1 for these remaining bins, and that's our histogram. So if we were to continue along and look on the next page, I think that's the reason why I chose 0.5. It's because it's exactly what R thinks it should be. And you should given the choice between what you think the number of bins should be and what R thinks it should be, you should probably go with what R is doing. Don't fully trust it, but at this point you probably don't have the experience to have your own opinion. So, yeah. It came up with basically the same picture. Okay, now we've been coming up with these nice plots, and everything is great. 1 second, let's just satisfy my nervousness. Okay, we're still good. Okay, I mean, making these pictures is nice, but why are we making these pictures? Well, there are certain things that we are looking for when we're making visualizations like this. For example, is the data unimodal? One thing we're looking for is modality, which is where does the data tend to cluster? Is the data unimodal, where it only has one peak? This would suggest it's clustering around one area. Or on the other hand, is it bimodal or multimodal, where you have multiple peaks? So the unimodal case would be something that resembles this, so we'll call this unimodal. Bimodal would be a situation like this. Maybe think of it as a camel hump. And multimodal is you've got all sorts of different modes, all sorts of different peaks. So what would it mean if you had unimodal versus bimodal versus multimodal? For starters, the multimodal case, the first thing that you should ask with multimodal is, did I choose a bin that's too small? Because you can end up with situations, if you choose your bin size to be too large when you're making a histogram, at one extreme you can have a skyscraper where everything is in one bin, and that is a chart that doesn't really tell you anything. On the other hand, you could have that basically a pancake where every single observation gets its own bin, and that really doesn't tell you anything either. That's basically a dot chart, and you've kind of lost the point of a histogram. So the first thing in the case of this blue sort of histogram, it's not really a histogram because it's a smooth curve, but whatever. In this case, you should probably ask yourself whether you've chosen too few bins. It could happen that you have genuinely multimodal data, but the number of modes should not be too many, because modality and having more than one mode is indicative of there being more than one actual population in your data set. So, for example, if I say that this is tracking height of people, I could genuinely have a bimodal data set, because actually there isn't one population in this data set of people. There's actually two populations, men and women, because men and women cluster around different average heights. So that's features that you're looking for. Unimodal indicates that your data set, it probably consists of one population. And another thing that we're looking for when looking at stuff like histograms, and by the way, a lot of this discussion also applies to the stem and leaf plot and the dot plot. In particular, the stem and leaf plot, because you can argue that the stem and leaf plot is actually a histogram. It's just a histogram with a particular bin choice, but there's nothing really different about it. But anyway, is the data positively skewed or negatively skewed or symmetric? So a positively skewed data set, the way I like to think of it is, well, let's first draw it out. We have the positively skewed data set, And then we have the negatively skewed data set, which looks more like this. And then we have the symmetric data set. Let's do a little bit better than that. Okay, that's a little bit more symmetric. Okay, so if you're at all bothered by the terms positively skewed, negatively skewed, symmetric, and you're wondering how can I tell the difference between positively skewed and negatively skewed, here's a little rule for you. Draw a dinosaur. Draw a dinosaur. And then ask, where is his tail pointing? In the case of the black dinosaur, it's pointing towards the positive end, so it's positively skewed. All right, now let's talk about the green dinosaur. Well, let's draw the green dinosaur. Give him some legs. Give him some stuff on his back, because it's like a stegosaurus, so he's got these plates on his back. Where is his tail pointing? Oh, it's pointing in the negative direction, so it's negatively skewed, right? And you don't draw a dinosaur for symmetric because I don't know, we're just not going to do that. We're already silly enough. But why does it matter whether a data set is positively skewed or negatively skewed? It matters when we're thinking about the relationship between important statistics such as the mean and the median. So the mean and the median are going to behave a certain way and have certain relationships depending on whether the data is positively skewed or negatively skewed. Positively skewed data sets, what that basically means is that there are outliers in this data set, and when observations tend to be large, they tend to be very large. Negatively skewed data sets are data sets where when an observation is small, it tends to be very small. And I can think of specific data sets that fall into these types of categories. Like, for example, income tends to be positively skewed. So you have most people in a certain range of incomes, and then you have a few people who make much, much more than that, right? So most people are around here, but when you're rich, you tend to be very rich. And on the other hand, for negatively skewed data sets, I do have something in mind. I have test scores. Test scores for me, like, there's a lot of ways test scores could actually appear statistically, but it seems like most students tend to fall within a certain range, and the students who really didn't get it, when they fail hard. So it tends to be negatively skewed. And symmetric, symmetric is kind of this ideal case where you're just as equally likely to be above or below. I think heights could be possibly. I haven't really looked at a height distribution in a long time, but I think that heights could probably be symmetric, where it's like you're just as likely to be really tall or really short at some degree. So you're also looking in these plots for outliers. For example, a histogram that has an outlier. You might have a histogram that looks something like this, and then you have a point that's way out here. And you would say that this point right here is a candidate to be an outlier. And you're also interested in how spread out the data is. And by spread, when we're talking about spread, we're talking about the less spread out black distribution as opposed to the more spread out green distribution. Which of these cases are you actually looking at? Or at the very least, you're just interested in what the range of the data is. Okay, so that's it for visualizing quantitative data. Now let's talk about qualitative or categorical data. How do you visualize that? We're only going to advocate one method here, and that's a bar plot. In fact, in my visualization class, I was told if you don't know what visualization method to use a bar plot. Because bar plots are actually very good visualizations. Never, ever, for the love of God, draw a pie chart. I know, especially in like public policy and economics, people love their pie charts. For the love of God, do not create a pie chart. Do you have any idea how many memes of ugly and stupid pie charts there are? Please do not draw a pie chart. Okay, continuing on. To construct a bar plot, list each possible value of the variable and how frequently that value is taken. A lot like what we were doing before, it's just instead of having numbers on the left-hand side for like these bins, instead of that, you're just going to have the categories that your data set could be in. And then you're going to draw a horizontal line So let's see. A cartoon bar plot that we're making. So we have like category A, category B, category C. So draw a horizontal line. It could be a vertical line. It doesn't really matter. And along the axis marks possible values of the variables, and then draw a bar for each category extending to the category's observed frequency. So we'd end up with something that looks like this. It is worth mentioning, bar plots and histograms are two different things. And the difference is this axis here, this x-axis. With a histogram, that axis is a number line. And there is a very specific order. And if you were to plot a point on that line, it would mean something. Whereas with a bar plot, this doesn't mean anything. You could rearrange it if you wanted to, and the bar plot would say exactly the same thing. Even in the case of ordinal data, you could space it out. There's all sorts of transformations that you could do, and the plot says the exact same thing. That is not the case for histograms. So bar plots and histograms, despite looking somewhat similar, are certainly not the same thing. Okay, so for our next example, there is a data set showing the frequency of the class of passengers aboard the Titanic who survived her sinking. I have the Titanic data set in R contains this data set, but they're actually tracking a lot of things. They don't just track the class, they track male and female, they track age, they track survival, and so on. Here I have restricted to using this apply function, which I'm not going to talk about right now. I have restricted it to the case of survivors for for certain classes. I want to create a bar plot for the frequency of each class's survival. So I've already got the frequency distribution. R is already given it to me very nicely. So I'm going to say we've got first class, second class, third class, and crew. Okay, and then we're going to extend up. We're going to say up here, let's say that this is 220, and right here we've got 110. We're gonna just eyeball this. So for first class, there were about 203 survivors, so that's about here. For crew, there were 212 survivors, so that's about here. For second class, there were about 118 survivors, that's about here. For third class, about 178. So our bar plot should look something like this. Okay. And in fact, we can look at what R does. We give the bar plot function in R this data set, and it will in fact make a very nice bar plot for us. Okay. There is actually a visualization method that I haven't really discussed here, and I'm making a video, everything's quite nice. I really don't see why I shouldn't show you this if you're familiar with R. So let's see. First, are we still streaming? Yes, we are. Okay, so there is another type of visualization called a density plot. You cannot make a density plot by hand. So I'm going to go ahead and I'm going to make a density plot. Does this command still work? This is a new installation. Oh, good. Everything's working. Maybe we should go back to... let's see. What's a data set that we could work with? Rivers is fine. This is the length of some North American rivers. And there is a plot called a density plot. Remember that I was drawing some smooth curves? And histograms do not look like smooth curves. What I kind of was drawing was a density plot. So I could create such a plot by typing in plot, density, and then give it the name of the data set if it's stored in a vector. So in this case, rivers. And this is the resulting density plot. And it's actually plotting a smooth curve. Let's see. What's one of the data sets that we were looking at before? Page up. What data set was this? Okay. Okay, so we had this height data set. So let's go ahead and combine those two things. Center on this. Okay, so height will be a vector consisting of the numbers 5.55, 5.30, 5.03, 5.30, 5.13, 5.05. What was that number? 5.36? No, that's 5.38. So we've got 5.38, 5.96, and 5.21, and 5.38. Okay, so here's our data set. And I'm just going to create a density plot for this data set. That's not it. It's still rivers. Oh, because I typed in rivers. Silly me. Okay, so what I want instead is height. There, that's better. And it makes a smooth curve that kind of resembles. Actually, it certainly does resemble the histogram that we drew. Except it's actually, like in the histogram, there is, in fact, when you look at that data set, kind of a peak in this region. And that was completely masked by the histogram. But the density plot was able to capture it. Interesting. So, but you have to make a plot like this in R. You cannot make a plot like this by hand. So I'm just bringing it to your attention because these kind of plots do show up. All right, so that's it for section 2 of the book. And I thank you for joining me, and I will see, and I hope that you watch the video for section 3. So have a nice day. Hey students, all right, so next section is on measures of location. So up to this point we've talked about visual summaries, and visual summaries are nice. Thing is though, we don't want to restrict ourselves just to visual summaries. We would also like to be able to have numerical measures of data to understand distributions. So we're going to start with measures of location. Measures of location tell us where a dataset tends to be located along a number line. So the first and most common measure, you probably have already seen a lot of these measures that we're going to talk about, but the very first one we're going to talk about is the sample mean. And for a dataset consisting of observations x1 to xn, the sample mean is defined as x bar, which equals 1 divided by n times the sum from I equals 1 to n xi. Which, if you're not familiar with this notation, what this means is we would take our data set, add up everything in the data set, and then divide the resulting sum by n. Now, there's the thing called the sample proportion. And in fact, relative frequencies are sample proportions. They're counting the proportion of observations in a sample that take a certain value. The sample proportion is also a measure of location. It loosely is like the proportion of observations in the sample that have a certain characteristic. So we divide the sample into successes and failures. We like to use that vocabulary of success and failure. A success, and the sample proportion will count the number of successes. So we'll have P hat equals, and very loosely, we're just going to say this is the number of whatever we consider to be a success, and divide this by the sample size. Now, this could also be written as x over n, which could also, where x is this number of successes. And then we could say, let's suppose that xi is equal to 1 if the ith observation counts as a success and 0 otherwise. What then does it mean to count the number of successes? To count the number of successes is to go through each observation and then add 1 to a running count if that observation counts as a success, and otherwise do nothing, which is the same as adding 0. So we could then say that the number of successes is equal to the sum from I equals 1 to n of this new xi variable that is counting the number of successes effectively and saying whether an observation is a success. So we should say that this sum is equal to the number of successes. And then we take this sum and divide it by n, which is also, for what it's worth, the same as taking the sum and multiplying it by 1 over n. So notice what I just wrote down. I just wrote down the sample mean again, which means that the sample proportion is the same as the sample mean of a sample that consists of 1s for successes and 0s otherwise. So recognizing this is actually very important, because in probability theory, the mean, or more directly, sums of variables or sums of random variables, are very important. So recognizing something as a sample mean means that any theorems from probability theory that involve the sample mean can be applied to that variable. So this is actually quite important to recognize. But that means that after this point, we really don't have to say much more about sample proportions, because the sample mean, whenever we're talking about the sample mean, we're also talking about sample proportions. So let's get started with an example. What is the average number of points your daughter's soccer team scores? Here is, as a reminder, the data set. This is actually proper R code right here, just to write down the variable name soccer. And what will happen is R will then print out that data set. So, but we're just going to take that for granted for now and compute first. Let's go ahead and compute the sum of these numbers. So the sum from I equals 1 to n xi, which is basically this right here, just means take all the numbers in this data set and add them up. So we've got 9 plus 6 is 15, plus 5 is 20, plus 5 is 25, plus 5 is 30, plus 6 is 36, plus 2 is 38, plus 8 is 46, plus 3 is 49, plus 4 is 53, plus 8 is 51, plus, oh, it looks like I'm, all right, so I actually have something written down. I have 62. I think I might have missed something in that count, but it's going to add up to 62. Okay, so just take my word for it. So this adds up to 62. N is equal to 12. So the sample size is equal to 12. And the sample mean then, x bar, will be 62 divided by 12, which equals 31 over 6, which is equal to 5.16 with a repeating 6. Okay. If we were to go to the next page in these notes, we would see some R code that computes the sample mean for this data set. The R function is mean. So we say mean of the soccer data set, and it will report to us the mean, which is what we computed. Now let's suppose that R1 to Rn is the ordered version of this data set. So x1 to xn is just, so R1 to Rn is x1 to xn, but ordered. Remember from a previous video for section 2 on that for this notation, x1 to xn, I do not necessarily imply any sort of ordering. Now I do. For R1 to Rn, I'm going to imply an ordering. The sample median is another measure for the location of the data set. It is defined as the number that splits this data set in half. So that is basically the definition. And from that, we can come up with mathematical formula. So we can say that x tilde, that's the notation we will use for the sample median, x tilde will be one of two possibilities. First, there is the case when there are an odd number of observations. If there are an odd number of observations, let's see, let's zoom in so I can have a little bit more precise writing. If there are an odd number of observations, after we order the data set, the observation in the position n plus 1 divided by 2 will be the number that splits the data set in half. So this will be what we're using if n is odd. So to think about this, if we had 11 observations, 11 plus 1 divided by 2, so that's 12 divided by 2, that's equal to 6. The sixth observation, after you order the data set, will be the median. Okay? Now suppose that there are an even number of observations. We could potentially choose observation in the n over 2th position. So if the sample size were 12, this would be the sixth ordered observation. Or we could potentially have the 7th ordered observation. Both of those are kind of dividing the center. So what we'll do instead is we will take the midpoint between these two numbers, which could potentially end up being the same number. There's nothing that says that these two numbers are not the same. But we're just going to average those two numbers, take the midpoint in between them. And admittedly, if you had a number line and you had some data over here and some data over here, and you have these two observations as being potentially the median, any number in between them could be defined as the median, since any of those numbers would divide the data set in half. And in fact, you may see alternative definitions of the median in R to take advantage of this fact. But for now, it doesn't really matter if we had a lot of observations how exactly we define the median. This is perfectly fine to just take the midpoint between the ordered observation in the position n over 2 and the ordered observation in the position n over 2 plus 1. So if we had 12 observations, we would take the 6th and the 7th observations and average them to get the median. Okay. Let's see an example of computing the median. Find the median of the first 11 soccer games your daughter's team participated in. I chose 11 just to have an even number to kind of... odd number, just for demonstration purposes. In this case, the sort function in R, this function will order your data set from smallest to largest. Given a vector, it will order that vector from smallest to largest. So we have sorted this data set. We now have an ordered data set, and I want to compute the median of that data set. Well, first off, there are n equals 11 observations in this data set. That means that the observation in the middle will be n plus 1 over 2, which is 12 over 2, which equals 6. Therefore, the median will be the 6th ordered observation, which is, well, let's see, 1, 2, 3, 4, 5, 6. 5. So it will be 5. That will be the median. If we were to look at some R code, there is a function, an R function called median, and given that data set, by the way, I didn't mention this before, this right here, this square bracket stuff, this is subsetting notation. It basically translates to get the observations, get all observations between the 1st and the 11th in this data set. Okay? And remember that soccer itself is not ordered, so we're just getting observations x1 through x11. Okay? But I just feed that vector to the median function, and it tells me that the median is 5. And by the way, if you're wondering what this little 1 right here means, that's just part of how R prints vectors. If this vector was quite long, it would split over a number of lines, and this little 1 would just be tracking which observation you're looking at with each line. So you wouldn't have, so like if there was 10 down, so if there was like more numbers after this, and then we had in square brackets 10 and saw the number 6 and numbers after that, this would tell us that the 6th number in that that would tell us that the 10th number in that vector was 6. It's just something that's supposed to make reading what's in vectors visually easier. Okay, so I think I pressed something. Let's do that. Okay. All right. So continuing on, other measures of location are percentiles. So we're going to say that this is the Greek letter alpha, and alpha is a number between 0 and 1, and we're going to include 0 and 1 as well. The alpha times 100th percentile is the number such that roughly alpha times 100% of the data in the ordered data set lies to the left of that number. So if we choose alpha equals 0.5, that would be the 50th percentile. So roughly 50% of the data set lies to the left of that number, which means that 50% lies to the right. And what I just described is the median, because the median is the observation that splits the data set in half, which means that half of the data set is to the left, or 50%, and 50% is to the right. So the median actually counts as a percentile. Percentiles are a generalization of the notion of a median. In fact, there are other percentiles that we care about, such as quartiles. Quartiles divide the data set up into quarters. So for the first quartile, roughly 25% of the data set lies to the left of that quartile. And for the third quartile, roughly 75% of the data set lies to the left of that quartile. So to visualize, we would have the first, second, and third quartiles, and roughly 25% lies to the left of the first quartile, and roughly 75% of the data set lies to the left of the third quartile. And the second quartile is the quartile where roughly 50% lies to the left of that quartile. In other words, the median again. You can also say that there is a 0th quartile, which corresponds to alpha equals 0. Alpha equals 0 means that there is nothing really to the left of this observation. So that would correspond to the sample minimum. Whereas alpha equals 1 means that about 100% of the data set lies to the left of that number. That corresponds to the sample maximum. There are actually a number of procedures for computing percentiles from data sets, and I'm not going to repeat all of those procedures. If anything, I'm just going to list off the procedure that's easiest to do by hand, because at the end of the day, in the real world, what you would do is ask R to get a percentile, and R has its own algorithm for getting percentiles that's more complicated than what we're about to do. And I really don't see the point in telling introductory students how to do that, because it's more computationally intensive, and like, what's the point? If you're doing things by hand, let's keep things simple. I should also probably mention, if you combine the 0th, 1st, 2nd, 3rd, and 4th quartile, 4th quartile is the maximum. If you combine those together, you end up with what's known as the 5-number summary of a data set. So, here's a procedure for finding quartiles. First, find the median of the data set, then split the data set into 2 data sets at the median. And we're working with the ordered data set now. So split it into 2 data sets at the median. If n is odd, remove the data point that corresponds to the median. And then, to find the first quartile, find the median of the lower data set. And then, to find the third quartile, find the median of the upper data set. So to visualize this procedure, we have a data set, find the median, and then and this will split the data set into two, then find the medians of the other two halves. Okay? That will tell you what the first and third quartile are. The minimum and the maximum are easy. Find the smallest and the largest numbers in the order data set. Okay, so for our first example, we're going to find the first and third quartiles of this little girl's first 11 soccer games. So let me get caught up in my notes for a second. Okay, so to find these two quartiles, how about we write down what that data set was just for our own purposes. So we've got 2, 3, 4, 5, 5, 5, 6, 6, 8, 9. Okay, so the median was 5, and this is an odd number data set, so we're going to delete that median. 6, 6. Oh, oops, there were 2 8s. Sorry about that. So we're going to delete the median, which is 5, and then we have split the data set in two. So then we find the median of the first half. There is an odd number of observations here. So the median will be 4. Thus, the first quartile, which I will call Q1, that will be 4. And the median of the upper data set, that will be 8. So that means that the third quartile will be 8. And if we wanted to, we can kind of fill out the 5 number summary, saying the second quartile, which is the median, that number is going to be 5. The 0th quartile, which is the minimum, well, that's going to be 2. 2 is the smallest number. And the 4th quartile, which is the maximum, well, the largest number in the dataset is 9, so that will be 9. Okay? Okay, next example. Find the 10th and 90th percentiles of the height data. I have listed the data for you below in order. So the data set, oh yeah, this is actually what I was getting to regarding those little numbers in square brackets. This is the 9th observation, right? So that means that this number right here is the 10th observation in the data set. So that means that this data set has n equals 10 observations. So 10th percentile, so roughly 10% of the data set lies to the left of that number. So 0.1 times 10 is equal to 1. So that's about one number lies there. So we're going to choose 5.05. So 5.05 will be the 10th percentile, which we will call that Q hat point 10. And for the 90th percentile, so 0.9 times 10, that's going to be 9. So that's observation number 9. So 90% of the data set lies, including that number, to the left of 5.63. So we'll say that 5.63 will be the 90th percentile, which we'll call Q hat 90. Okay? And actually, R has functions for computing quantiles. Another word for what we're talking about here are quantiles. Here I have asked R specifically to give me the 25th and 75th percentiles. It is not using this procedure that I described. It is using a different procedure for finding quantiles. There's a number of different procedures for finding quantiles and percentiles, and if your sample size is large, nobody cares which one you use, really. It really only matters at smaller sample sizes which procedure exactly you use, and there are various different motivations for different kinds of procedures. There's various ways to solve the same problem. And what I described is simple enough to do by hand. So if you're going to do it by hand, go ahead and use what I used. This is probably, whatever came up with this is probably much more complicated. And if you need something more complicated, then don't do it by hand. Ask R to do it. So you can read R's documentation to see what exactly is being done here. It's using some sort of interpolation trick. So here I've asked
So the second parameter here, this is a vector that contains the numbers 0.25 and 0.75 corresponding to the 25th and 75th percentiles, or quantiles. I'm not really sure what the difference between those two words is. Here I asked for the 10th and 90th quantiles or percentiles, and it gives me numbers. These are all pretty close to what I came up with before. Okay, next up, let's kind of... We've come up with some measures of location, and there's actually a number of different measures of location. Like, for example, I have seen a measure where you take the largest and the smallest observations. So you could say that's Rn minus R1, plus R1. So take the midpoint between the largest and the smallest observations. That's actually another measure of location. There's a number of different measures of location. What I've shown here so far is fine, but let's go ahead and start comparing these different methods for describing the location of a data set. So the sample mean x bar is known to be sensitive to outliers, which means that outliers in the data set have a profound effect on the sample mean. So if you had, for example, a data set that consists of let's say 1, 2, 3, the average of that data set, or the mean of that data set, will be 2. And the median of that data set will also be 2. Compare that to a data set that contains the numbers 1 to 1,000. So the mean of that is going to be about 500, which is much larger than 2, what it was before. Compare that to the median. The median of that data set, 1 to 1,000, is still 2, which means that the median is insensitive to outliers. It basically doesn't care what they are. All it cares about is the ordering of the observations, so long as if you were to change the value of an outlier, so long as it doesn't change the ordering of the data set, the median will not change. So as an example of this, I'm going to compute the sample mean and the sample mean of the daughter's soccer games if I throw in a 12th soccer game. And I'm going to consider a number of different scenarios where her 12th game was 1 point or 1 goal, 4 goals, 2 goals, and 18 goals. We're going to consider that. And what I actually did here was I created a vector that contains these. So I'm not going to talk too much more about this because I want to focus on the math. First off, when I add up the 11 other games, when I add those up, I end up with a cumulative score of 61. So let's create a table for all of these potential outliers. So in this table, we're going to consider when the 12th game is 1, when it's 4, when it's 2, and when it's 18. And we're going to have a column for the sum of the observations. We're going to have a column for the sample mean and a column for the sample median. So in the case where the 12th game is 1, this will add up to 62. And by the way, I'm using the word outlier for 1, but 1 in this case would not be an outlier. Same with 4 and 2, but 18 certainly would be considered an outlier. So if her 12th game is 1, then it adds up to 62. If her 12th game is 4, it adds up to 65. If her 12th game is 2, the game's cumulative score is going to be not 62, 63. And if it's 18, they all add up to 79. And then we're going to take these sums and divide them by 12. In the end, we end up with, in the first case, we get a sample mean of 5.16. In the second case, we get a sample mean of 5.416. Repeating 6. In the third case, we get 5.25. And in the fourth case, we get 6.58, which is much different from what we had before. Hold on. I think my pen might be... Okay, my pen's back. Is it, though? Might need to charge. Okay, now the median. In the first case, so in the first case, the median is still going to be 5. And in fact, it's going to be 5 for the first 3 cases because the median was 5, and it didn't change the order of the data set. If you go back and look at the original data set, we're essentially, in these first 3 cases, we shift all the numbers to the left, which means that the median is going to be the number to the left of what it was before, which was 5. But if we chose, or it's actually going to be the average of 5 and 5, which is still 5. But in the last case, the median actually will be the average of 5 and 6. So it will be 5.5. So the median did change a little bit in the last case, but it's mostly because of where that outlier ended up. It ended up on the right-hand side of the data set, or the right-hand side of what the median was before. And it could have been 273, and the median would be exactly the same. But as we can see, the median isn't changing really at all, especially when you compare it to the mean. And here is some R code that the idea of this code is I'm going through a loop, adding this observation to a version of the data set, and then computing the median and the mean of that data set. The result will be an R matrix. I take the transpose of that matrix because that's the version of the matrix that I prefer. I'm giving the matrix some row names and column names, do some rounding, and this is the resulting matrix, and it's pretty similar to what we had before. In fact, there is a relationship that we can say in general between the mean and the median, depending on whether the data is negatively skewed, positively skewed, or symmetric. If the data set is positively skewed, so the data set looks roughly like this, then the median, which is the point that divides the data set roughly in half, will be less than the mean. And that's because the mean is going to try to chase the outliers, and the outliers are going to be on the right-hand side of the bulk of the data. So in the case of negatively skewed data, we're going to have the opposite relationship, where the median, since the outliers are going to be on the left-hand side of the bulk of the data, the mean is going to chase the smaller numbers. So the median will tend to be greater than the mean. And in the case of a symmetric data set, the mean and the median should be approximately the same. In real data, probabilistically, when we talk about means and medians and probability, they will be exactly the same when the distribution of the data is symmetric. But in real data, that's never the case. In real data, they will just be close. And what it means to be close is like that's a judgment call, right? So what would some implications for that, thinking back to some examples of positively skewed and negatively skewed data sets, I said that a positively skewed data set is incomes. This relationship means that the average income tends to be larger than the median income. And economists generally prefer to use the median income for income distributions because it seems inappropriate to use the mean. This kind of gets to the issue of, I've given you these competing measures for means and for measuring the location of a data set. Which one of these measures should you use? I would say use the one that's appropriate, which means, here's one thing. When should you use the mean? I would say you should use the mean when large observations are allowed to compensate for small ones. Let's say, for example, that you're gambling. If you're gambling, what you care about are your mean earnings and not your median earnings. Because it's okay for you to win nothing 99 times if you win a million, or I guess it also depends on how much this game is worth. But let's say that you're playing a game that costs $1 each time you play. It's okay for you to win nothing 99 times if on the 100th time you win $1 million. That would be awesome for you. Whereas in that situation, the median would be $0. And if you were judging by the median how well you were doing, you would think you were actually doing poorly. So if you're allowing large observations or small observations to maybe replace or detract from the overall score, then the mean is appropriate. On the other hand, the median in the case of social sciences, we care more about what 50% of the population is experiencing, and we don't necessarily want to allow the great fortune of the wealthy to compensate for the great poverty of the very poor. So in that situation, the median would be the preferred observation. And of course, if theoretically what you're trying to measure is the population median, then you should use the sample median. And if you're trying to estimate the population mean, you should use the sample mean. And in which case you should not be using the opposite. Now, there are some exceptions to this, and we'll talk about this when we talk about probability and talk about hypothesis testing. There's notions such as most powerful tests, like if your data set was symmetric and you knew it came from a normal distribution, you should always use the mean, even if what you care about is the median. And the reason why that is because for a normal distribution, the two numbers are the same. But we're just going to leave that for now. So all of this was talking about sample results. There are analogous population numbers too. Okay, so I just want to very quickly satisfy my nervousness. Okay, we're still streaming. Okay. All right, there is another measure for location called the trimmed mean. So I'm going to tell you about the trimmed mean, and I'm even going to compute it for you. But then I'm going to have some caveats about using it. You probably should not be using the trimmed mean, and I'll explain that in a second. But the idea of the trimmed mean is we have the median, and the median is not sensitive to outliers, which is generally considered a blessing, but it's not always a good thing because it feels a little inappropriate to throw out so much data when you're computing the median, because once you know the ordering of the data and you know which one or two numbers are in the middle, then the rest of the data doesn't matter, and that feels a little extreme. On the other hand, you're a little bothered by the mean's sensitivity to outliers. Furthermore, on outliers, you might think, should we throw out outliers? Should we ignore outliers? Because that's actually kind of what the trimmed mean is suggesting that we should do. With the trimmed mean, what we're going to do is we're going to use only... we're going to throw out a certain percentage of the data. Like we're going to throw out 10% on the left-hand side and 10% on the right-hand side of the data set. So throw out the 10% of the smallest numbers and 10% so in this data set, 10% of the numbers that are the smallest numbers of the data set and 10% of the numbers that are the larger numbers in the data set. That would be the trim mean where alpha equals 0.1, where you're trimming at 10% on each end. So the idea of the trim mean is throw out the outliers. So on this issue of whether you should throw out outliers, you should actually think very carefully before you throw out outliers in general. If you're computing a trimmed mean, then that's kind of what you're doing. But let's say you look at a data set and you see that your estimators are actually very influenced by a couple outliers, and you're thinking, maybe I should just throw those out. I would first ask, why are you throwing them out? Are you throwing it out because you think the number is erroneous? Because I, in my own experience, have seen numbers in data sets where it's like, that's probably an error. Someone probably entered the wrong number, so I'm going to throw it out. Like when someone writes in the American Community Survey that someone's made $1 trillion, it's like, that's probably not correct. You should just throw it out. If that's what's going on, go ahead and throw it out, because the reason why you're throwing it out is because of data contamination. But if you're throwing it out just because it's causing bad behavior in your estimators, that is probably inappropriate. And you should instead try to model the outlier or just accept it rather than throw it out. Or think harder about why it is that you are using the mean rather than the median. I would actually suggest that over throwing the outlier out. But anyway, let's go ahead and compute the trimmed mean for the height data set. So let's go ahead and rewrite that data set. We've got, I don't want blue. Okay, so I've got, for the height data set, 5.05. You can go ahead and like skip ahead a little bit to skip me writing down numbers. So 5.05, 5.13, 5.21, 5.3, 5.3. This splits the data set in half. So the next number is 5.38. And we've got 5.38 again. 5.55. 5.63. And 5.96. Okay. So there are 10 numbers in this data set. If we're going to trim, so if we're going to say alpha equals 0.1, so we're going to trim 10% of the data off on each end. So trim 10% at each end. That means that we're going to end up trimming 0.1 times 10, where 10 is the sample size, which is 1. We're going to trim off the smallest and the largest number in this data set. So that would be 5.05 and 5.96. And then take the average of the remaining data set. So in that case, X bar, where we trim off 10%, will be the average of the 8 remaining numbers, where we're summed from I equals 2 to 9, the ordered data set. And that is going to end up being 42. So the sum is going to be 42.88. And then we divide that by 8, and the result will be 5.36. So 5.36 feet, because this data set is in feet. We're talking about height. Okay, and R can compute trimmed means. In fact, you can just use the mean function like we had before. We're just going to pass it an additional parameter that tells the function to trim. Now, I mentioned a little while back, you actually probably should not be computing trimmed means. And the reason why is because when we compute a median, which a little side note, I guess the median, both the mean and the median count as particular trimmed means, where the median is like the trimmed mean where you trim off 50%, and the mean is the trimmed mean where you trim off 0%. So the trimmed mean kind of generalizes these other two statistics, but you probably should only use those other two statistics. You should probably not use the trimmed mean. I mean, I guess if what you were doing is instead of taking off 10% on either end, it's like always take off the two largest and two smallest numbers. That could be appropriate from a theoretical perspective. So because basically, as you increase the sample size, the number of observations that you're trimming off becomes very small relative to the rest of the sample. But trimming off 10% at either end from a theoretical standing is a little odd. And the reason why is that there is actually a population median that we are estimating when we are using a sample median. And there is a population mean that we are estimating when we use a sample mean, and both of those quantities are very well understood. But when you're using a trimmed mean, you are estimating neither of those things. You're estimating some weird hybrid, monstrous population statistic that we don't necessarily understand. You're estimating essentially the population version of a trimmed mean, and it's questionable whether that's actually what you want. It seems like the worst of both worlds in that case, because no one can actually, like, why would we talk about the population except for the 10% largest and 10% smallest numbers? Like, that doesn't really make a whole lot of sense. So, for that reason, unless you are, I would actually more advocate for like a fixed trimming where you take off the 2 largest and 2 smallest observations. Although at that point, you probably should just use the mean or use the median. I probably would not use the trimmed mean. So, okay, so that's it for this section. In the next section, we will be discussing measures of variability. So, I will cut it off here and have a good day. Okay, so this section is about measures of variability. So last section, we discussed measures of location. Let's start by justifying why we need measures of variability. Consider these 3 data sets, and I'm going to construct a dot plot for each of these data sets. So I've got 3 lines for my 3 dot plots, data set 1, data set 2, data set 3. And in these dot plots, I'm going to start with 1 and end in 12. And in between, I've got 6. So let's see. We're going to keep these all on the same scale. So 1, 12, 6. 1, 12, 6. And we'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, that's 1, 2, 3, 4, 5, 6. Okay, that's a little inexcusable. We're gonna have to try a little harder on that one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so I've now got these 3 number lines, and let's start with data set 1. So we've got numbers at so 4, 5, 6, 7, 8, and then we've got one at 2, 5, 6, 7, 10. And then finally we have 1, 3, 6, 9, 9, and then 11. Okay, so look at these 3 dot plots. Now, I want you to let's first start actually by computing the mean and the median for each of these data sets. So data set 1, 4 plus 5 plus 6 plus 7 plus 8 plus 9. That is going to add up to 36. The second data set, well, we subtract 2 from 4 to get 2, but then add 2 to 8 to get 10. So that second one's also going to add up to 36. And for the third one, you kind of are going to do the same trick. So they all add up to 36, which then means that the sample mean is going to be 36 divided by, there's 6 observations. No, actually there's 5. Oh, I'm sorry. They don't add up to 36. They don't add up to 36. Oh, silly Curtis. Silly Curtis. They add up to 30. So the sample mean will be 30 divided by 5, which equals 6, which is also equal to the median. because you look at them, because these data sets are ordered, they have 5 observations, so the third row is going to correspond to the median. So that means that the mean and the median for these data sets are all the same. And yet, let's suppose now that I were to tell you that this was the waiting time for the train. Which of these data sets would you prefer to be the observed waiting times for the train? Probably the first one, at least if you're like me. Because for myself, I actually did not really like inconsistent trains. I mean, it's kind of cool that this train there might be a 1-minute waiting time for this train, but there also could be an 11-minute waiting time for this train. And one way or the other, I would just love it if trains always showed up exactly 6 minutes between. Which, okay, admittedly around here they generally do that. But you don't really like a lot of variability in the wait time for the train because that makes the train unreliable. That said, this aspect of the data set is not being captured by our measures of location, the sample mean and the sample median, unfortunately. So, and the reason why is because the attribute that we're talking about is an attribute that doesn't have anything to do with the location. These data sets are located at essentially the same place. It has to do instead with spread, and we now have a pictographic method for understanding spread. We can see that these data sets have different spread, but we would like to have some numerical measures. So very quickly, I'm just going to say that I would prefer 1 because it's more consistent or less spread. Okay. What we need is a measure of variability to describe how spread out a data set is. How could we possibly do that? Well, we might start by examining deviations, where we look at xi and subtract out the sample mean, and if we were to add these up together, this might give us a measure for how spread out the data set is. But here's the thing, though, when we try that. We're going to sum up from I equals 1 to n. No, that should be a 1. So from I equals 1 to n, xi minus x bar. And this is a sum. Sums are linear, which means that I can now break up this sum into 2 sums and say that this is going to be a sum from I equals 1 to n, xi minus the sum from I equals 1 to n, x bar. But here's the thing about that latter sum. See, this is actually adding up a constant n times. And you probably remember from 2nd grade what it means to add up the same number n times. You end up with multiplication. So this number is going to actually end up being n times x bar. Okay? And this number also can be interpreted as n times x bar because it is the sum of the observations divided by the sample size and then multiplied by the sample size again. So we end up with nx bar minus nx bar. And that equals 0. So what that means is that this quantity is always equal to 0. Always equal to 0. I think I found a dead spot on my screen. Okay. So that always adds up to 0. Which means, I mean, the issue is that these deviations, they always have the same sign. Well, okay, they all have all right, what I just said was literally false. They don't always have the same sign. In fact, you have opposite signs. You have some positive, some negative deviations, and it turns out that the positive and negative deviations cancel each other out. So you end up with a 0. So that didn't quite work, although there was an interesting idea there. Looking at the distance between an observation and the sample mean, and one might be tempted
to try this. Replace the parentheses with absolute values. So you end up adding up the absolute value of xi minus x bar, and now you don't have that issue of negatives and positives canceling each other out, because everything will be positive, and you'll end up with a positive number. And that makes sense. The thing, though, is this is actually more difficult from a mathematical perspective to work with. And the reason why is because it's involving absolute values, and absolute values are not differentiable. Absolute values, if you remember from Calculus 1, they have a cusp, a sharp point, and sharp points are not differentiable. Compare that instead to, so this is like the absolute value of x. Compare that instead with the function x squared. That should work. I mean, that has the nice feature of being differentiable. So what actually statisticians end up doing is they say we should add up the sum from I equals 1 to n xi minus x bar squared. And this quantity is known as the sum of squared errors. Xi minus x bar, a term that statisticians like to use for that, is the error. And we're adding up the squared errors. And there is, in fact, an interpretation for the square part, which is, maybe you remember, this is how I like to think of it. I think that this formula kind of rhymes with x1 minus x2 squared plus y1 minus y2. Do you remember that? Do you remember that from geometry class? If you take the square root of this quantity, you end up with the distance formula for Euclidean distance, for Euclidean geometry. And it actually kind of rhymes with that sum that I've shown up above. So, and in fact, there is a very deep connection between the sum of squared errors and Euclidean geometry. But this quantity, to me, that seems like an appropriate way to think about distance. And if we were to average this by saying like this is 1 over n, we would have an average squared distance. Now, that's actually a good idea, but there's a better idea, which is to divide instead of by n minus 1. Now, that might strike you as a little bit odd. Why is it that we're dividing by n minus 1? There's a few reasons for that, some of which we'll talk about later in maybe chapter 6. But n minus 1, there's actually a term for this quantity, and it's known in this context as the degrees of freedom. And why are we dividing by the degrees of freedom rather than n? I'm going to present to you a few arguments for why you'd want to do that. For starters, let's imagine that we had a data set of size 1. Right, so there's only one observation in our data set. What we're trying to measure right now is a spread in the data set. If we had a data set of size 1, is there really any way to estimate spread? How can you determine the spread from a data set of one observation? That doesn't really make a whole lot of sense. And it seems like something has fundamentally gone wrong in that situation. And when you divide by n, it's not going to reveal that something is wrong. But when you divide by n minus 1, a sample size of 1 is explicitly forbidden because you cannot divide by 0. Okay, so that's one way to think. That's one way to think that maybe n minus 1 is more appropriate. And then secondly, what we're actually doing with this number, we actually call this, we've given this number a name as statisticians. This is known as the variance, the sample variance. Now, maybe you recall from previous sections
my saying that there is a sample mean, and you can actually talk about a population mean. And there's a sample median, and you could talk about a population median. And there is a sense in which the sample mean estimates the population mean, and the sample median estimates the population median. So the sample variance should estimate the population variance. There is, in fact, a population variance. But here's the thing, though, about the population variance. Our estimator, if we were to divide by n, would have a tendency to be too small. I mean, it would still be close to the population variance, but you could be a little bit better by dividing by n minus 1 instead of n. If you were to divide by n, you'd actually be a little too small. So we should divide by n minus 1 instead. There's a term called biasness that we will discuss more in chapter 6, but long story short, it turns out that when you divide by n minus 1, you have an unbiased estimator for the population variance, whereas if you divide by n, there is a very small bias. Now, that said, you can still divide by n and have a reasonable estimator, it just will have that bias problem. The bias gets really small as you increase the sample size, but it is still there. So why not just get rid of it? So these are some potential arguments for why you should be dividing by n minus 1. And later on in that chapter, we will actually, I may actually show that if you compute the expected value and you divide by n minus 1, you get the sample variance. But we're a long ways off from that. So accept it that you pretty much have to divide by n minus 1 instead of n, although it is still reasonable to think of this as like an average squared distance. Oh, yes, another argument for why you should be dividing by n minus 1. When you compute the variance, there's something you have to do first. You have to compute the sample mean. You have to compute the sample mean first, and there's a penalty that you have to pay for that. The term degrees of freedom means that this is basically the number of observations in the data set that you are allowed to change, and where you can change those observations freely, and you could still end up with the same sample mean. Because it turns out, for basically the reason that I showed up here, this line of reasoning that if you know n minus 1 of the observations and you know the sample mean, then you know the nth observation that you didn't list out before. So the sample mean contains information. And the fact that you had to estimate a parameter before you could estimate the sample variance means that you need to divide. It means that there's, in some sense, a penalty to your sample size. So it's inappropriate to divide by n minus 1. You now need to divide by n. You now need to divide by n minus 1. All right. Now, here's the thing about the sample variance that we don't like. Think about the units of these things. Let's say that we were talking about feet, or going back to some examples, or even for this soccer data set that I've seen in a few videos in the past, where we're tracking the goals scored by a Little League soccer team. If we were talking about goals, then this right here is a goal for a game, so its units are goals. The sample mean is also in goals, because you add up goals, divide by something without units, you end up with goals. And you have goals minus goals, so you still, in that difference, have goals. But then you square, and you end up with goals squared. What the heck are goals squared? That's a unit that doesn't mean anything to us. We don't like the fact that in the end, the sample variance produces squared units. We would rather have some measure of spread that is in the same units as the data set. And there is such a measure called the sample standard deviation. So the sample standard deviation is S, which is equal to the square root of S squared. So S squared is the sample variance, S is the sample standard deviation. So we'll call that SD. Right? I mean, it's right there. So the sample standard deviation. So yes, since you've taken the square root of the variance, you now take the square root of goals squared and now end up with the unit goals, which is what you want. So the sample standard deviation will be in the same units as the data set, and we like that. Furthermore, it is still reasonable to think of the sample standard deviation as measuring the average distance of an observation from the mean, or a typical distance. All right, so continuing on. There are, in fact, population analogs to these quantities, such as the population variance and the population standard deviation, and those will be discussions for a later chapter. I believe that's chapter 3. So now, when you're computing the sample variance, another way to write it, if we define SXX as the sum from I equals 1 to n of xi minus x bar squared, we could say that the sample variance, which is what you need to compute for the sample mean, is equal to SXX divided by n minus 1. The thing, though, is a lot of people don't like to compute the deviations and then square them. So compute the mean and then compute the deviations, and by subtracting the mean from the observations and squaring them. People don't seem to like to do that. So when doing stuff by hand, it's often easier to use this shortcut formula, where you add up the observations squared and then subtract the mean squared multiplied with n. And it is in fact possible to show, and because this is the second time I'm recording this video, I'm not going to show it because I'm tired. It is possible to show that these two quantities are the same. And I would say, I'm going to leave this as an exercise to you. If you are curious, if you're thinking you're probably going to take some more advanced stats classes, why don't you take a second to show that these two quantities, the sum of squared errors and this shortcut formula, are the same. But I'm just going to leave it for now that these are, in fact, the same number. So that could help you potentially save some time when computing the sample variance by hand. Okay, so let's now start looking at examples. In example 14, we're going to compute the sample variance and sample standard deviation of the soccer game scores. So here are the scores listed out again. Length is an R function. So soccer in R is known as a vector, and the length of a vector will tell you how many objects are in that vector. So there's also an R function called summary, which will give you some basic statistical summaries for a data set stored in a vector. Or actually, summary will give you some basic statistical information about lots of things. But that we're going to leave that for the R lab. For now, it's just giving us some basic statistics for a vector. And I am now going to compute the sample variance of this data set. Okay, so I like to create a table when computing this by hand. If you don't want to watch me compute this by hand, because it is kind of a tedious calculation. If you don't want to watch it, this is a part that you can skip over. All right, anyway. So we have 12 observations in our data set. So I'm going to start numbering off 1, 2, 3, 4, 5, 6, just to track the observations. 7, 8, 9, 10, 11, 12. Okay. We have an observation, and we have an observation. Hold on. In another dead spot. We have an observation squared. Okay, so observations in our data set. We had 9, 6, 5, 5, 5, 6, 2, 8, 3, 4, 8, 1. And then we're going to square each of these observations. So we'll get 81, 36, 25, 3 times. 36 for 64, 9, 16, 64, and 1. Okay. If you're also, like, you kind of want to work on this by hand a little bit, but you don't want to completely trivialize the problem by going to R and asking for the variance and standard deviation, because it'll just give it to you. Maybe this would be something to work on in Excel. Because what I'm basically doing is being a human Excel spreadsheet. At the very bottom, I'm going to sum up these two columns. The first column sums up to 62, and the second column, consisting of squares, sums up to 386. So now I want to compute the sum of squared errors, and that's SXX, and we have our shortcut formula for computing that. That's going to be 386, which is the sum of the squares of the observations, minus 12, which is the sample size, times the mean. All right, we need to compute the mean. So the mean is going to be the sum of the observations, which is 62, divided by 12. So in this parentheses, I'm going to put 62 over 12 and square it. And you plug it into a calculator, and the number that you get for the sum of squared errors is 197 divided by 3, which is, as a decimal number, 65.6, where the 6 is repeating. So the sample variance will be the sum of squared errors divided by, as a reminder, the sample size minus 1, which is going to be 65.6 divided by 12 minus 1, which is 11, which is equal to 5.96, where the 96 itself is repeating. Now, this is nice, but the thing is, the sample variance is in the units of the sample variance is goal squared. We don't like that. We want to compute the standard deviation too, because that's a more interpretable number. So the standard deviation is going to be the square root of the variance, which is going to be about 2.443, rounding to 3 decimal places. So you can think of this as your daughter's soccer team is varying around their average score of about 5 points, but they're deviating from that by about 2 points. So on average, they'll be about 2 points away. Okay. All right. So in R, the functions that are responsible for computing these quantities are var and SD. R computes the variance, and SD computes the standard deviation. So var of the soccer data set is basically what I wrote down, and the standard deviation is basically the same thing too. All right, so the sample mean, so for the sample variance, we actually have some nice properties that also translate into properties for the standard deviation. Actually, before I continue on, I'm going to double check, because this scares me. Okay. Everything is good. I'm scared. Okay. So, some basic properties. Let's suppose, in this proposition, let's suppose that we take our data set and then we shift everything by a constant to produce a new data set that's shifted by a constant. It turns out that the sample variance for the new data set will be the same as the sample variance for the old data set where you didn't shift. That's a good thing. What that means is basically this is, in fact, a measure of spread. If it wasn't a measure of spread, basically, if this was not the case, if the sample variance changed by shifting the data, then it doesn't seem really fair to call it a measure of spread, because it's also capturing location too. But the fact that you don't have to, the fact that it doesn't care about the location, or in a way, it doesn't actually care about the mean, because, and you can think of that as because it subtracts the mean out from the data set. The fact that it doesn't care means that it is in fact a bona fide measure of spread and not measuring something else along with it. The second proposition says that the variance, if you were to rescale your data set by C, the variance will scale by C squared, and the standard deviation will scale by the absolute value of C. So the standard deviation is always going to be positive. The variance will always be positive. So when you rescale the data set, it's not going to... whether you multiply by a positive or a negative number doesn't actually matter. And also it tells you that you can think of this as saying something about unit conversions. Because remember that unit conversions generally are multiplicative operations. If you wanted to change the units of the standard deviation, you could do so by just multiplying the original standard deviation by whatever unit conversion formula you have. And also this is basically telling us what I was saying before, that the variance is in units squared, but the standard deviation is in just the same units as the data set. So these are good properties to be aware of. Okay, so the sample variance and standard deviation, these are one one class of estimator of spread. They're not the only ones. Oh, by the way, we did have this discussion when talking about measures of location about biasness. No, not biasness. Sensitivity to outliers. It turns out that the sample mean and the sample variance and sample standard deviation are also sensitive to outliers. In fact, they are more sensitive to outliers than the mean is. So they care a great deal about outliers too. Just throwing that out there. And you can kind of tell by looking at those formulas, since when you look at them, they're basically means, right? They're averages. Or at least the variance looks like an average, and the standard deviation is the square root of an average. So if you end up having a very large error, then that's going to make your variance very large. So it's sensitive to outliers. Just mentioning that. Another measure for spread is known as the fourth spread, or sometimes, like in Math 1070, we call it the interquartile range. It is the third quartile minus the first quartile. And we're going to denote it in this class with FS. This is another measure of dispersion. So let's compute the fourth spread for the soccer game scores. We already computed in a previous video the third and first quartile for the soccer games. So the fourth spread will be the third quartile minus the first quartile, which actually turns out for this data set to be 8 minus 4, which is equal to 4. Okay. So the fourth spread is, in and of itself, a measure of dispersion. And one way statisticians might use the fourth spread is as a tool for outlier detection. Remember, we care a great deal about outliers. If there's we would like to have outlier detection tools, because if there is an outlier in this data set, we would like to investigate it further and decide how we should approach it and why the outlier is there. Outliers are very interesting aspects of data sets, so we would like to be able to detect them. So we might call an observation that is further than 1.5 times the fourth spread from its nearest quartile a mild outlier. So as an example, let's suppose we have a data set. Our data set looks something like this. Here's kind of a dot plot sketch of our data set. And we've also got a couple observations over here. So those two observations visually look like outliers. Let's suppose that we have the... I didn't realize that was a thing. Okay, let's suppose that our first and third quartiles are here and here. Okay? If that is the case, the fourth spread, or the IQR, is going to be the distance between those two quartiles. So we'll call this Q1, Q3. The distance between those will be the fourth spread.
So according to this rule, how you detect an outlier is you take this quantity and then increase it by 1.5, so 1.5, and go beyond, and you're gonna like see compare an observation to its nearest quartile. So these are going to be close to the third quartile because they're above the third quartile. And you see if those observations are 1.5 times the IQR away from their nearest quartile. And if they are beyond that range, then they are candidates to be outliers. So these are now starting to look like at least mild outliers. But in fact, if we were to double that quantity, so 3 times the forced spread, so that would look like this. Turns out that they are beyond 3 times the forced spread as well. So now these are looking like extreme outliers. We could also do the same thing on the left-hand side of the data set, look for outliers that are, numbers that are really small. There's nothing that says that outliers have to always be large numbers. They can also be really small numbers too. And there's no outliers on the left-hand side in this data set. I should point out, it's tempting for students to think that what I just gave you is a definition for outliers. The word outlier is intentionally vague because there's many different ways you could define an outlier. This is one such definition, or one such criterion for deciding if something is an outlier. This criterion would not work if we were to go into 2 dimensions. It is a one-dimensional approach, not a 2-dimensional approach. And you can still have outliers in 2 dimensions or in bivariate data, and you can still have outliers there, and they're going to behave like there's more possibilities the moment you've moved onto a plane, as opposed to just a number line. More ways for things to be outliers. I'm hesitant to just let students think that this is what an outlier is. There's actually different ways to think about outliers. We could come up with different definitions based off of our problem and how we want to approach it. So we could choose a procedure that is tailored to our problem to define outliers so that it's most useful to us. So this is what we're using in this class, but it is far from like what we'd always use. Okay, and it is not really the definition of an outlier. We would just say that an outlier is a point that seems unusual to the other points, that seems to be distant in some way from the other points, or it doesn't seem to follow the same pattern as the rest of the data. Okay, so moving on into example 16, use the forced spread to detect outliers in soccer game scores. What is the minimum score needed for a data point to be a mild outlier or an extreme outlier? So the forced spread, as you may recall from above, was 4. So 1.5, I don't want that color. All right, so 1.5 times the forced spread is going to be 4 times 1.5, which is going to be 6. And 3 times the forced spread is going to be 12. So let's see what it would take for something to be considered at least a mild outlier. To be mild, you would have to possibly exceed the third quartile plus 1.5 times the forced spread, which is going to be 8 plus 6, which is 14. There were no double-digit scores in our soccer data set, so that means that there were no outliers, at least on the positive end. And as for the negative end, in order for something to be so small that it's an outlier, it would have to be less than Q1 minus 1.5 times the forced spread, which is going to be, that's going to be 4 minus 6, which is negative 2. Well, negative soccer scores are impossible. So there's not going to be any mild outliers on the left-hand side, which means that there are no outliers in this data set. Now that's it. Let's go ahead and continue on, just for fun. Let's see what it would take for something to be an extreme outlier. To be an extreme outlier, you would have to exceed Q3 plus 3FS, which is 8 plus 12,
which is 20. So in other words, the other team didn't show up. To be on the left-hand side, to be an outlier on the left-hand side, you have to be less than Q1 minus 3FS, which is 4 minus 12, which is negative 8. And no way that's going to happen. So there are no outliers in our data set. Okay. So, there's another visualization method that I would like to discuss that we weren't able to discuss in section 2. The reason why is because this is a box plot, and box plots require the 5-number summary, which is the minimum, max. So the 5-number summary is the minimum, maximum, median, first, and third quartiles. So you need to have that in order to be able to compute a box plot and create a box plot. That's why we didn't talk about it before, because we hadn't actually talked about those things. So for a box plot, we first compute those quantities on a number line, which this could be a vertical number line, or it could be a horizontal number line if you want box plots oriented horizontally or oriented vertically. Either one is fine. Whatever suits your needs, do whatever you want. Okay? But on a number line, let's say something like this, we're going to draw a box. So we've got the first quartile and the third quartile. We're going to draw a box whose ends are at those quartiles. We're also going to draw a line in that box corresponding to the location of the median. We will then draw what are known as whiskers that extend out to the maximum and to the minimum. So the whiskers will extend out to the extrema of the data set. And that's a box plot. Now, I should point out that R does not draw box plots this way by default. R does something different. R will actually try to detect outliers, and it will draw the whiskers out to the observations that are not outliers. So the largest observation that is not an outlier and the smallest observation that is not an outlier. The outliers are treated differently. They get their own points in the box plot, kind of like with the dot plot. That's more complicated to do, and I'm not going to ask you to do that. Using just the 5-number summary and extending out to the maxima is fine for me. And I feel like that if you were ever to draw a box plot by hand, you should just keep things simple, because it's not too hard to compute a 5-number summary especially if you had, say, if you had like a stem and leaf plot. But a box plot, like computing the outliers, is a bit much. So a box plot on its own, I mean, it's okay. But a box plot really shines when there are other box plots with it. And when you have that, you can now start drawing comparative box plots. And when you have comparative box plots, you can start to say things about the relationships amongst different groups that, like if you want to compare different data sets, you may have two data sets for two similar but not the same populations. Like, for example, men and women. Men and women are both human, but if you were to compare height, you would probably want to differentiate between men and women. So you could have a box plot for men's heights, and you can have a box plot for women's heights, and then you can make comparisons. And you could compare, in this case, this looks like, if this were in fact talking about men's and women's heights, this would be suggesting that men tend to be taller than women. So one thing that you could do when looking at a comparative box plot is compare the location of the boxes. You can also compare the spreads of the boxes. So for example, if we saw one box plot that looks like this for one group and a box plot that looks like this for another group, we might say that those two groups certainly have different spread. Okay, so you can start making comparisons that are more easily made with plots such as these than if you were to, say, try to overlap density plots or something. So comparative box plots are very nice because they allow you to at a glance compare two different groups and their distributions. So let's go ahead and start creating some box plots. In this example, we're using a data set from R. In this example, we're studying the tooth growth of guinea pigs that were given a vitamin C supplement via orange juice at 3 different dosage levels. Here's a bunch of R code that takes the tooth growth data set and transforms it into a format that is nice for this problem, where it did not look like this before. Go ahead and look at the tooth growth data set. It does not look like this at all. For starters, the tooth growth data set also includes a group where the guinea pigs were given vitamin C, like a vitamin C supplement directly rather than via orange juice. And we've completely excluded that group using this filter command. These are known as pipes. They are part of the Dippler package. So we filtered so that we were looking at only orange juice. We selected the length and the dosage as the variables we were interested in, and then did some other stuff so that the data came in a format that I liked, which is where it's ordered from smallest to largest for each of these 3 groups. And we have the half dosage group, full dosage group, and double dosage group. Okay. So, all right. So, and the data set is ordered, which means it's going to be somewhat easy to compute a 5-number summary for each of these 3 groups. So for instance, the last row is going to be the maximum for the 3 groups, and the first row is going to be the minimum for the 3 groups. As for the other quantities, we also need the median. So there are 10 observations for each group. So the median is going to be the average of the 5th and the 6th rows. So the medians, after we compute those averages, or midpoints if you prefer, the medians for the half dosage group, its median is 12.25. For the full dosage group, it's going to be 23.45. And for the double dosage group, it's going to be 25.95. Okay? So those are the medians. Now we need to compute the first quartile. Remember, what we do is we split the data set in half and then look at the median for the smaller data set or the lower data set. This will be the first quartiles. And the median for the third data set, remember that both of these data sets have 5 observations each after we do the splitting. So the median for the upper data set, that will be the third quartile. Okay, so we now have everything we need to start constructing our box plots. Okay, so I'm going to construct this by hand. I don't want that. Let's make it black. Isn't that a song? Okay. Oh yeah, I want it painted black. Yeah, that's right. That is a song. All right. I want it painted black. Anyway, so I have the half dosage group, the full dosage group, and the double dosage group. I'm going to have my box plot end at 31 up here, and we're going to start down here at 8. So we're going to go 8, 9, 10, 11, 12, 13. Okay. 14, 15, 16, 17, 18. And then we go 19, 20. 21, 22, 23, 24, 25. 26, 27, 28, 29, 30, 31. Okay. All right. So we've got our scale. So for our first group, let's zoom out a little bit. So for the first group, the minimum was 8.2. So minimum of 8.2, we'll put a dot right there. Then we go to the first quartile, so that's going to be 9.7. That's about there. Then we've got 12.25. That's about there. Q3 is 16.5. That's about 13. That's about there. And finally, the maximum is 21.5. So that is going to be about there. Okay. So then we have a box, the median, and the whiskers. All right, so there's our first box plot. All right, so now for full dosage. Scrolling up a little bit. So for full dosage, the minimum is at 14.5, which is about there. Then we have a quartile at 20, which is about there. The median's at 23.45, so that's about there. Q3 is at 25.8, so that's about there. And then the maximum is at 27.3, so that's about there. Okay, so draw the box and the line for the median, and draw out the whiskers. Okay, and finally for the double dosage group, the minimum is at 22.5, which is about there. The first quartile is at 24.5, which is about there. The median is at 25.95, which is about there. The third quartile is at 27.3, which is about there. And the maximum is at 30.9, which is about there. So draw the box, draw the line for the median, extend out the whiskers, and there we go. All right, and now we have a box plot, a comparative box plot. And what can we see? We can see that, in fact, increasing the dosage does seem to increase the tooth growth length. We also see that there's much more spread in the half and full dose than there is for the double dose, which is an interesting fact. All right, so moving on, there is an R function called box plot that can construct these box plots for you. This is largely in agreement with what we drew. And as a reminder, R doesn't by default produce box plots in the way that I just described, where it draws whiskers out to the minimum and the maximum. It does something a little bit different, where it will draw it out to the largest and smallest observations that are not outliers, and then draw the outliers as their own individual points. Okay, there's actually one more visualization that's similar to a box plot that I would like to discuss. I didn't discuss it in the lecture notes because you can't really draw it by hand. But I've got a computer in front of me. Okay, very quickly. Okay, everything seems to be fine. Okay, so you can't really draw it by hand because... Uh-oh, what was that?
Hey students, let's get started with the chapter on probability. Probability is the mathematical study of randomness and uncertain outcomes. So the subject, in fact, may be about as old as calculus. At some level, humans have known about probability for a very long time. It's just, it wasn't until around the time of probability that we saw some of the first semi-rigorous treatments of probability. And then probability really became a serious mathematical subject around the beginning of the 20th century when a mathematician by the name of Kolmogorov rooted probability theory in some real analysis theory. So he developed a set of axioms that made it a rigorous mathematical subject in its own right, and here we are today. And statistics relies very heavily on probability. We've seen in the previous chapter quantities such as the mean and the median. We saw all these sample statistics. We discussed the ideas of a sample and a sample's relationship to a population, but it's hard. You can't really say much more than that and really can't have a rigorous discussion about different sample statistics without having probability theory to back it up. So we're going to start with that right now. We're going to start with section 1 on sample spaces and events. So we start out with the idea of an experiment. An experiment is an activity or process with an uncertain outcome. Examples of experiments including flipping a coin, or flipping a coin until the coin lands heads up, or you can have rolling a die, a six-sided die, or rolling two six-sided die, or you could even have something a bit more abstract, such as the time in the morning that you wake up. That can also be understood via probability theory. So when we have an experiment that we have described narratively, in a sense, so I say I'm going to flip a coin, or I'm going to flip a coin until it lands heads up. After we have an experiment, we need to describe the sample space, which we are going to denote in this class with the letter S, although I should point out that, at least in my experience, omega, the Greek letter omega, is more common notation for the sample space. But this is fine. S is fine. So this will be, the sample space is the set of all possible outcomes of the experiment. The sample space is defined by the person who's developing this probability model. So it basically, you say what the sample space is, and you're going to pick a sample space that seems appropriate to the phenomena that you wish to describe. A set is very loosely defined as a collection of objects. Actually, this definition of set is bad because it's possible using just the idea of a collection of objects to construct impossible sets. Sets that are impossible in the sense of being contradictory to itself. So there's this area of mathematics called axiomatic set theory that actually develops a rigorous notion of sets that largely allows for sets that we'd like to think of. But honestly, for our purposes, this is definitely overkill. Just thinking of set as a collection of objects is fine for us. Events are subsets of the sample space, defining possible outcomes of an experiment. We automatically get an event called, or a subset called the empty set, or the null event, which is denoted with this notation. This is a set with no members. It can be thought of as an event, as the event where nothing happens. And that is precisely how you should think about it. I might create a separate video describing what precisely the empty set is and kind of try to dispel some inclinations of students to try to assign some deeper meaning to the empty set. It's like, no. The empty set is a set with nothing in it, and you really cannot call it anything else. It's more a necessity of the mathematics than it is anything that you can honestly interpret. So let's get started.
with an example. We're going to define a sample space for the experiment of flipping a coin. We're going to list all possible events for this experiment. Let me just get caught up in my notes that I have aside here. And, all right, so I'm going to say that this sample space, which I'm going to call S, what are going to be the possible outcomes of flipping a coin? Well, despite what might be physically possible, like I actually have seen coins, not necessarily like mint coins, but things very coin-like that end up landing on their side. But that is not going to be allowed here. There's only two possible outcomes: heads and tails. And notice the curly braces. Often sets, what we are talking about is a set. Generally, sets are going to be denoted with curly braces. Another important fact about sets is that the objects in sets only appear once generally. If you were, so like for example, this set is the same as H, H, T. So at some level, there's uniqueness in a set. You get imposed uniqueness. So if you list heads twice, it's the same set. Okay? And additionally, the ordering of how I write stuff down in a set does not matter. So I could have written tails heads, and it would have been the exact same set here. But yeah, now we have the sample space, and this is what it is by definition. I decided this is the sample space for my experiment. And I decided this because I believe that this sample space is going to be the appropriate sample space for my problem. So I'm saying that there's two possible outcomes of this experiment. The coin either lands heads up or it lands tails up. So next I'm going to list some possible events for this experiment. So an event is a subset of the sample space. Okay, so what is one possible subset? One possible subset is the set that contains only H. Right, so only heads. So this is the event, or the subset, where when you flip the coin, it lands heads up. And similarly, we have the event where it lands tails up. And some authors like to call sets like these sets with only one element simple events because they have only one outcome. Even Kolmogorov in his book on probability theory had the notion of simple events where it has only one outcome corresponding to something that you would actually observe. I personally don't really care for the distinction myself, but students might like it. We can also have the event heads or tails. So what is a possible outcome for this? Well, we could get heads or tails, basically. And notice right here that this is the same as the sample space. So I could have said the sample space is an event. And generally that's true, because what does it mean for a set to be a subset of another set? What does it mean for something to be a subset? It means that every element in a set is present in another set. Or, equivalently, there are no elements in the subset that are not present in, let's call it, the parent set. Right? So, equivalently, you cannot find an element in the subset that isn't present in this containing set. Okay? So, by that definition, the sample space is a subset of itself, since every element in the sample space is also present in the sample space. So it seems almost tautologically true. And yet, at the same time, it matters. It matters a great deal that one set that you automatically get when you one event that you automatically get when you define a sample space is the sample space itself. And there is one more event that we have the moment we define the sample space: the empty set. That is also a subset of the sample space. Now, it seems really weird because you ask yourself, how is it that a set with nothing in it? Another way to write the sample space is like this, where you write two curly braces but with nothing in between them because the empty set has nothing in it. Okay? So you ask yourself, how is it that the sample space, every element of the sample space is also, every element of the empty set is also in the sample space? It has no elements. Well, exactly. Because by this alternative way to think about what it takes to be a subset, there is nothing in the empty set that isn't present in the sample space because there's nothing in the empty set. Therefore, you automatically get that the empty set is a subset of the sample space, and therefore the empty space is an event. Now, I'm kind of implying here that what it takes for something to be an event is that this set needs to be a subset of the sample space. So in other words, what it takes to be an event is that you simply be a subset of the sample space. Technically, that is not true, but the reason why it's not true is going well beyond the scope of this class. And you might see a little bit of it in probability theory, and it would become much more important if you were to take graduate level probability theory, measure theoretic probability theory. Technically, it is not true that every subset of the sample space is an event. That said, it's really hard to imagine a subset that isn't one. So basically, if you imagine the subset and you didn't actually try to break the theory, if you imagine a subset, it's probably an event. So it's, for now, it's probably fine, although I'll probably add a little more rigor to the notion of what it takes to be an event. Or do I do that only in, like, a class devoted to probability theory? I'm not really sure if I talk about it in this class. We'll see. We'll have to see as we go through the notes. All right, so that's that. By the way, I should probably mention something. Here, we might give names to these events. Like, we might call this first event EH. We might call this second simple event ET. To say that one set is a subset of another, we can use the notation, say, EH is a subset, and I like to put a line underneath, so to say that it could possibly be the same as the sample space. So we have this, or, a lot of people also will just write it like this. So we have that the event EH is a subset of the sample space, ET is a subset of the sample space, S is a subset of itself, and the empty set is a subset of the sample space. Okay? So, continuing on. Next example. Define a sample space for the experiment of rolling a six-sided die. List 3 events based on this sample space. Okay, so I'm going to say, because I think this is the best way to understand this problem, that it's going to consist of outcomes 1, 2, 3, 4, 5, 6, but I'm not going to write the numbers 1, 2, 3, 4, 5, 6. And I have reasons for not writing the numbers. The reason is there is nothing in probability theory that requires that your sets contain numbers. Nothing says that. It just says some object very loosely defined. So instead of writing numbers, I'm going to write little dice faces. So I have a dice face that has 1 pip, a dice face that has 2 pips, a dice face that has 3 pips, a dice face that has 4 pips, a dice face that has 5 pips, and finally, a dice face that has 6 pips. Okay, that looks like 6 pips. All right, so that's my sample space. And now I'm going to list 3 events based on this sample space. So one event is the empty set. I'm just going to say it right now. The empty set is the subset. So here we go. We get one event for free. I've promised myself I'm not going to do that here. That's my preferred notation. I'm not sure if it's the notation used in the book, and not everybody uses the same notation. That's something that you need to get used to in mathematics. You need to pay attention to what notation someone is using, because despite the fact that the books and sometimes the instructors make it look like there's one set of notation, for a subject, that's just not true. And that's including probability theory and statistics. It's just not true that there is one set of notation. And you need to pay attention to what someone is actually using to mean their stuff. Anyway, so the empty set is a subset of the sample space. The sample space is a subset of the sample space. Both of these are valid events. Okay, but they're almost trivial at this point because these are events that you automatically get. So what's something that's a little bit more interesting? Well, we could have the event where you roll a 4. This is one of those simple events that you may have heard of. So 4 is an event, and it's a subset of the sample space. What's another one that we could have? Well, we could have the event where you have an even number of pips. That's a valid event. Because, in fact, even though I've written this down in English, and often it's useful to write down sets in English sentences, what this actually translates into is a set with 3 elements. You have the set containing the dice with 2 pips on its face, 4 pips on its face, and 6 pips on its face. These are all... come on, you. Come on, I said 6 pips. Don't make me a fool, you stupid laptop. Some people. There we go. So this is also a subset of the sample space. This is also an event. Okay. So, there we go. I've given you 4 events, in fact. So you got a little bit more than what you paid for. Anyway, example 3. Define a sample space describing the experiment of flipping a coin until it lands heads up. List 5 events from this sample space. Ooh. So, what does this look like? What does this look like? Well, I'm going to say, here's my sample space. And, well, what's one possibility? Flip a coin until it lands heads up. Well, it could land heads on the first flip. So you flip the coin, it lands heads, and then you stop. You could then another outcome is you flip the coin and it lands tails. So you haven't gotten heads yet, so you need to flip it again, and then it lands up heads the second time. So tails heads is another possibility. Tails heads is a third possibility. Tails heads is yet another possibility, and so on. This set has an infinite number of elements because, in principle, if I have an outcome where you've got so many tails and the last one is a head, it's possible to also have an outcome where before you got to that point you flipped the coin and you got tails once. So for every outcome you can find a next outcome in a sense. So since there's always going to be a next outcome, this set must have an infinite number of members. Now, there is actually an interesting wrinkle that came up in one of my lectures on this. Is there an outcome in this sample space that corresponds to flipping the coin and it never comes up with heads? The answer is no. The answer is, in this probability model, it is impossible for the coin to never get heads, because I never described an element in this sample space where you just flip the coin forever because you never get heads. It is explicitly forbidden in this probability model since you cannot find an outcome corresponding to it. So therefore, since there is no such outcome where you never stop flipping the coin, it is literally impossible in this probability model. It's a very subtle point. It seems like you should have that outcome in this, but in fact you don't. It's just, and the reason why being I didn't define this sample space to allow for that possibility. Since there isn't a possibility that corresponds to it, it simply doesn't exist, right? Although it seems a little unfair because we can imagine a universe in which someone flips a coin and they never get heads forever. It does seem like it's a possibility, but it is explicitly forbidden in this probability model since it is not in the universe of possibilities. And by the way, it is different from something being impossible and improbable. Improbable will probably mean when you define a probability model for this, the probability of something happening is 0, which seems realistic to say for flipping a coin until where you flip a coin forever and you never get heads. It seems like it's reasonable to say it's improbable but not impossible. But right now it is literally impossible since there is no outcome that corresponds to that. We would have to add a separate element, which if we really wanted to, we could add maybe the infinity element to our probability model to represent the outcome where you flip the coin forever. And by the way, none of this says anything about what the probability of these events or these outcomes are. I have no notion of probability at this point. This is all set theory, right? So it seems like you would say that the probability that you flip the coin forever is 0, but I have said nothing about probability so far. Now, that said, that is a complication that we are going to leave out. We are not going to consider it any further. We are just going to stick with this probability model. Maybe I would revisit this notion of flipping the coin forever in a later lecture, but that's it for now. Let's list 5 events from this sample space. Well, what's one event? One event is what is the empty set. Why don't I listen to that? Because I'm bored. Well, no, not because I'm bored, because I'm lazy. Another one is, let's say you can maybe flip the coin exactly 3 times. That would correspond to tails, tails, heads. Okay, this is a possible event. That seems almost like a triviality. We could have the event where you flip the coin at most, let's say 3 times, because I don't want to write too much. All right, at most 3 times. So at most 3 flips. What would this correspond to? Like, this is in words, but in fact I can translate that into a collection of outcomes. Well, you could have flipped the coin only once. That's no more than 3. You could have flipped twice. That's no more than 3. But if you flip twice, then that means that the first flip was tails. And if you flip 3 times exactly, then you got 2 tails and a head. So we could have tails, tails, heads. And this would be the event. What's another event? We could say, well, another possible event would be, in words, at least 3 flips. That seems reasonable. What would that translate into? That would be the event where you flip it 3 times because it's at least 3 flips. So tails, tails, heads. And tails, 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 heads has at least 3 flips since it has 4 flips. And tails, 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 heads has 5 flips, so that counts. And in fact, there's an infinite number of such flips. Okay. And one final possibility is an even number of flips. That's possible. What would that look like if we were actually using the elements of the set to describe it? That would be the event where you have tails, heads. That has an even number of flips since it has 2. Tails, 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 heads has an even number of flips. Tails, 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 heads. That also counts since it has 6 flips, and so on. This event also has an infinite number of outcomes. So you can see here, it's perfectly possible to talk about a probability model that has an infinite number of outcomes. In fact, such models are quite common. And in fact, this particular model, where I'm flipping a coin until I get heads, as an instructor, I really like this model because it's not too difficult, at least in my opinion, to understand what is going on. The idea of flipping a coin until you get heads, it's a perfectly reasonable thing to think about. And yet at the same time, despite its apparent simplicity, it is actually a quite rich probability model. and makes a lot of points about probability theory. So I'll probably be revisiting this one. It's simple, but it can very easily get out of hand in a way. You can start. It can get quite complicated when you start analyzing it probabilistically, and the mathematics themselves, like students at this level can understand it, but it's also starting to push their knowledge a little bit, and it starts requiring some trickier calculations to do. All right, I'm just going to check something. That's not what I wanted. Yeah, we're still streaming. Okay. All right. Example 4. Define a sample space describing the experiment of rolling 2 six-sided die simultaneously. List 3 events from this sample space. All right. 2 six-sided die simultaneously. What would that look like? Well, it's tempting to say that this sample space consists of the numbers 2 through 12, but that's actually not what we should use. The reason why is probably what you're thinking is I'm adding the pips on the 2 dice together, but I never said that. I never said that there was going to be addition of 2 pips, so we're not going to do that because you can define a number of potential outcomes. Like maybe instead of combining the 2 pips together, you're taking the larger of the 2 pips, something like that. Or the smaller of the 2 pips. So we don't want to define our sample space that way. What's another thing that we probably should do? Well, when developing such a probability model, it's generally better to imagine that you are actually rolling 2 distinct dice. The reason why is because when you think of it that way, you end up with more appropriate mathematics. So it's actually better to think of this sample space. I keep doing that. It's better to think of this sample space as consisting of rolling a red die and a blue die. So that's what we're going to do. And just for my own sanity, I try to draw things out as a table. So as an example, we have a blue die, or we'll call it the left die, and we have a red die. So we have an outcome where the blue die comes up with a 1 and the red die comes up with a 2. We could also have an outcome where the blue die comes up with a 1 and the red die comes up with a 2. I think I might have said the wrong thing a second ago, but whatever. And we can have an outcome where the blue die comes up with a 1 and the red die comes up with a 3. And we would continue on with this. I'm not going to list out everything because I got better ways to spend my day. I'm going to say that in this first row, the last element is where the blue die comes up with the 1 and the red die comes up with a 6. All right. So for the next row, in the next row, we'll have the blue die comes up with a 2 and the red die comes up with a 1. So we'll just say that everything in the blue second row, the blue die will be a 2. So we'll just start out listing some of those outcomes, and then and in the third row, the blue die will be 3. And in our very last row, we would have the blue die is a 6. So 6, 6, 6, and finally 6. All right, so I probably should still write down my red die. So I'm going to write down my red die. So we got 1 and 1, 2, 2, 2, 3. Excuse me, I have somewhat of a cough. 3, 3, and 6. You failure. You failure of a computer. So 6.
6, and finally 6. For goodness sakes. Like I said, really cheap computer. 6. All right, there we go. I'm satisfied. We'll just kind of tidy stuff up, put some ellipses. I like things to be rather organized. And while we're at it, we'll put some commas too. Although at this point, I'm not really sure if the commas matter all that much. But this is a set. This is containing a bunch of stuff. This is what our set contains. So how many elements are in this set? Well, this set contains 36 elements, since you have 6 possibilities for the blue dice and 6 possibilities for the red dice. So there's 36 things in this sample space, which, using it this way, comes up with more appropriate probability models. Because this would be a model where, if you were thinking about adding up the dice, a sum of 2 would be less likely than a sum of 3, because there's 3 ways to get the dice to add up to 3, there's 2 ways to get the dice to add up to 3, but there's only 1 way for the dice to add up to 2. And that's more appropriate for our probability model. And we can start listing some events from this sample space. I'm going to list one event, one event from this sample space, and it will be the empty set, because I'm tired. E2, another event, would be the sample space itself. So anything happens. Again, I'm just really lazy right now. All right, now I actually have to start writing down some real events. Well, I mean, those were real events, but something that's a bit more interesting. Let's see. E3. What could we do for E3? Well, we do have the outcome where we roll 6 for the blue die, and 1 for the red die. Why this event? Because why not this event? It is an event. What's a 4th event? Let's start to get a little bit more creative. We'll say that the 4th event will be an even number of total pips. Total suggesting that you're adding the pips together. So, all right, so let's translate this into something a little bit more mathy. So you can have, let's see, there's a whole bunch of outcomes for 1, where you could have let's say that the, all right, we could say that the blue dice is a 1, and what's 1 outcome? We have the red dice also be 1. We could have the blue dice be 1 and the red dice be 3. That has an even number of total pips. We can just keep going on with this. I'm not really sure off the top of my head. I could compute it, but I'm not really sure off the top of my head how many outcomes are actually in this sample space. But it seems like it's going to be a number. And I'm tired, and I'm sure you don't want to watch me just list out stuff. So we'll just end this with 6 and 6. So, because at this point you probably get the idea. Plus, I also don't honestly remember the last time anyone asked for this type of event. Another event. So we could have for our 5th event that the die add up to 7. All right, so what would be in this event? Well, we could have that the blue dice is 1, and if the blue dice is 1, since they have to add up to 7, that means that the red dice is going to be 6. What's another possible outcome? Well, you could have that the blue dice is 2, and since oh no, they don't add up to 6, they add up to 7. Yeah, that's what I said. So you could have that the blue dice is 2, in which case the red dice must be 5. You can have the blue dice be 3, in which case the red dice must be 4. And you keep going on like this.
until eventually you get to the very last element that if you were to continue writing down, you would write down that element being when the blue dice is 6 and the red dice is 1. So how many elements are going to be in this event? Well, it seems like for every blue die, there's a corresponding... For every blue outcome between 1 and 6, there's a corresponding red outcome that would lead to the dice adding up to 7. So there must be 6 things in this event. So, yes. By the way, for whatever, for what it's worth, I'm not sure if I mentioned this later, but I'll just mention it now. We often use this notation, like for example, this, we would put a set in between two what almost look like absolute value lines to mean the size of a set, or more technically the cardinality of a set. But for now, when we're talking about finite sets, it's fine to talk about, to say the size of a set, meaning the number of elements in that set, in which case the size of the sample space is 36, the size of the empty set, the set with nothing in it, since there's nothing in it, its size is 0. The size of E5 would be 6. There's 6 elements in E5, and there's 1 element in E3. Okay. Continuing on, our next example: define a sample space describing the experiment of waking up in the morning at a particular time, where the time you wake up at, thought of as a real number, and that's a critical point, is the outcome of interest. List 3 events from this sample space. I'm going to say that the sample space, so we can think of it in terms of hours in a day, but we're going to allow hours to be decimal points. So an hour and a half would be 1.5. So we would say that midnight corresponds to 0 hours. And we're just going to say that you cannot reach the midnight of the next day. So maybe you've seen this notation before when regarding intervals of the real line, where a square bracket means that that number on that side is being included in the set, and an open bracket or a parentheses on a side means that that number is not being included in that event. So some more notation. We use what almost looks like an E or an epsilon to say that something is a member of a set. So for example, 0 is an element of the sample space. 12 is an element of the sample space. But 24, well, let's come back to 24 in a second. 50 is certainly not an element of the sample space, so we'll put a slash in that. And 24 is not an element of the sample space either, because I put what I call an open bracket or a parentheses around the 24. So in this alternate, so if I were thinking of 0, 24 as a set, this would be a set that doesn't include 0 either. Alternatively, just getting you more familiar with this notation, we could describe a set that includes both of its endpoints, 0 and 24. And by the way, all of these are corresponding... Oh, go away. All of these, by the way, are corresponding to intervals of the real line. So some interval of the real line. Hopefully you're somewhat familiar with that notation. Okay, so continuing on. This is our sample space. Let's erase all this stuff because this is somewhat of an aside. Okay. Okay. So 3 events from this sample space. We could have an event where we wake up at noon. So that would probably correspond to the outcome where you wake up 12 hours from midnight. So this would be exactly 12 hours, though. Exactly 12. Not a second more, not a millisecond more, not a millisecond less, and not a second less. Exactly 12 hours later. Which, think of that matters. It is exactly 12 and nothing. It seems like our own intuition of the world is Like if you wake up a millisecond after noon, you still woke up at noon. It's like, no, that is not what I mean right here. So it is a precise number, and that precision should lead you to think, well, that's impossible. Or maybe not impossible, but really, 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 really hard to the point of being almost impossible. And that is true. When we develop for a probability model for this experiment, we would probably assign a probability of 0 to the event of waking up exactly 12 hours from midnight, which is kind of a strange idea, but I'm going to talk about that in a later video. Just to understand what exactly I'm saying here. Let's come up with another event. This event corresponds to waking up between, let's say instead that you wake up sometime between 8 and 12 hours. Now, my language is a little imprecise here. So I need to specify, do I mean including 8 hours? Including exactly 8 hours? Or am I saying more than 8 hours? So 8 hours in a millisecond is okay, but 8 hours on the nose is wrong. So we'll just say that we're going to exclude those endpoints. Why? Because I said so. So this event would be an event where you do in fact where you can wake up 8 hours in a millisecond, 8 hours in a second, or 12 hours less a second, but you cannot wake up at exactly 8 hours or exactly 12 hours and have this event actually have occurred. Okay? Let's say for a third event, we're going to wake up, let's say that this is waking up after 3 a.m. So, or let's see, maybe no earlier than 3 a.m. So no earlier than 3 a.m. That suggests that we should include 3 a.m. in this event. So we should include 3 a.m. or 3 hours past midnight. But all right, so what should the endpoint on the other end be? It seems like we can wake up any time after 3 a.m. and that's fine. So we're going to end at 24 since that's the last. Since those points are the last ones in this sample space. Okay. Let me get caught up. All right, moving on. Events. Once we have some events, we can start manipulating these events in ways that create new events. So we can start giving some operations on our set theory. So for example, let's just say that A and B are events. And events in this situation, they're also synonymous with sets. So anything you know about set theory, you can import that here. When I'm talking about events, I'm really talking about sets. Those two terms in this class are used almost interchangeably. So the complement of A, which in this class we're denoting with A. In this class we're denoting with A prime, but that's not the only notation. There's A bar or a complement. This is actually my preferred notation. But anyway, in this class we're going to use A prime. This is the set of outcomes of S, the sample space, not in the event A. So it's all outcomes that could possibly happen that are not in A, in fact the English words that we use for this event is not A. That's a perfectly way to describe it. There's the union of two sets, which we would say A union B, but I also like to just say A or B since this corresponds to the logical notion of OR, where something in one event could happen or something in another event could happen. And by the way, when we're using OR in this context, we're using it in the logical sense where we can have an outcome in A only would count as happening in A or B. An outcome in B only would count as having occurred in the event A or B. And an outcome that is both in A and in B counts as happening in the event A or B, which is a little bit different from how the word or is used in English, because it's quite often the case in English that or means exclusive or, where you can say you can have your cake or eat it. And like so the phrase "have your cake or eat it" it suggests that you can either have your cake or you can eat it, but you can't have both, right? If you it was actually a really long time until that phrase made sense. So this might actually be something for people whose native language is not English. What they mean by "have your cake and eat it too." You can have your cake in your hand, or you can eat your cake. But if you eat your cake, it is no longer in your hand. So that's what it means. All right. So just in case, I think that might be something that for non-native speakers, it's actually worth it to make that clarification. But for a long time, I also, as someone who's spoken English all their life and was on the debate team and on the literary magazine, did not get. Anyway, the intersection of two sets, A and B, or A intersect B. So it's the set that contains only objects that appear in both A and B. So in words, we use A and B. I'm going to go ahead and get started drawing some diagrams. Venn diagrams are a way to describe set theoretic relationships between different sets. And Venn diagrams, you can construct Venn diagrams for pretty much up to 3 events. And Venn diagrams make sense, and Venn diagrams are very simple. And the moment you try to go to 4 events, Venn diagrams become impossible. So we're just going to live in a world where there's only 3 events. So here's how you kind of draw a Venn diagram, at least for this class. You draw circles and squares and stuff to denote sets. Often we draw a giant square, and this square denotes the sample space. So the square denotes the universe of possibilities. And we denote a subset of this sample space, otherwise known as an event, with some other shape such as a circle. Or maybe there are times where I will draw lines to try to divide it up, but basically we're going to draw shapes and lines inside of this sample space that divide regions of the sample space from each other, and those will denote subsets. So often I'm going to draw circles to denote events. So I'll often label one circle A and another circle B, and how we draw these circles allows us to reason about relationships amongst events. So here I have drawn a sample space with 2 events, A and B, and those events have some outcomes in common, since there is a region in which both of these circles intersect. Now, there's also a situation where there are outcomes in A that are not in B, so situations where A happens but B doesn't happen, because you can kind of imagine, if you really wanted a probability model, that we're going to pick a random point from this set, and we're going to ask, where did this appear? Did this appear in A? Did it appear in B? Did it appear in A or B? Did it appear in A and B, or did it not appear in either one? That would almost be a probability model. So we can use diagrams such as this to start reasoning about set theoretic relationships. And in fact, here's something to kind of think about. Well, actually, no, I'm going to save that for the next section. But this is a perfectly reasonable way to think about set theory at this level. Okay, so let's describe the situation A or B. So A union B means an outcome that is either in A or in B, or both. So what I would do in a Venn diagram is shade the region that corresponds to this event. Well, maybe before I do that, maybe before I go into that level of extra complication, how about I first describe the event just A? Well, visually, using a Venn diagram, what I would do is I would shade the region A and nothing else. And that would correspond to the event where A happens. So I'm using shading of these circles to try and reason about what happens here. I wonder if there's let's use this highlighter tool. I wonder what would happen if I use the highlighter. it makes my computer lag a lot. I'm not going to use that. Um, so, um, similarly, we could describe another event where we just have B occur. So we'll say the event B. How would we shade this? We're going to shade it like so. Just shade in the region that's enclosed by B and nothing else. So this corresponds. So this is the region that corresponds to the event B happening. Now let's go back to some of these other potential relationships, such as A or B, or A union B. This seems like a fancy feature. No, it doesn't work that way. So I need to get rid of that red region. All right, so here's a way to draw Venn diagrams when you're trying to do stuff. So, like, let's take for example the union operation, A union B. To draw a union operation, what I generally will do is I'll take a common color and I will shade in first A. I don't want black, I want blue. I'll first shade in A, the set on the left side of the union relationship, and then I will shade in B, the element on the right-hand side, and a point that was shaded at all is a member of this set. So, so this region that I've kind of enclosed in red corresponds to the set A or B, since any point that got shaded by blue at all counts as being a member in this event. Okay, let's draw another event. Let's illustrate, for example, A intersected with B. So to draw intersection, let's first draw our sets A and B. To draw intersection, you're going to subtract points. You're going to subtract from or actually what you would do is, I like to think of it in terms of pieces of paper, where you overlap two pieces of paper on top of each other and then cut the pieces of paper so that only the overlapping region is what's left. So you could imagine here, I draw something on A, and I draw something on B, and then I'm going to erase from the picture the region that was in B but not in A. And I'm going to erase from the picture the region that is in A but not in B. And what's left is going to be the region that corresponds to A intersected with B. Okay? So another important notion is disjointedness. Two sets are disjoint if they have no elements in common. In that case, A intersected with B is the empty set. So to draw disjointedness, this is what I would do. Here's my sample space. I draw an event A and I draw an event B such that there is nothing in common between the two events. All right, I'm going to draw the intersection between these two events. I'm done. Because there's nothing intersecting. So the intersection between these two events is the empty set. So this is one way, if you really wanted to assign some sort of meaning to the empty set, it would be that the empty set is a logical contradiction in a way, since the empty set shows up and when you have events that have nothing in common, which are almost logical contradictions. Another notion in probability theory, in set theory, is complementation. How would I illustrate complementation? So let's draw a sample space. I have A, I have B. What is so this is A intersected with B equals the empty set. That means disjoint. What is a complement? A complement is the region in the sample space that is in the sample space, but it's not in A. So that's going to correspond to shading everything that's outside of A. So there are some parts of B that get shaded, but nothing that's in A. Okay, so you shade everything except A. Some other important subset relationships. We have so some other set relationships. Here is the relationship A is a subset of B. What it means for one set to be a subset of another is that all of the elements in A are also present in B, or alternatively, there is nothing that A that doesn't also exist in B. So a subset relationship looks like so. You have the set B, and the set B contains the set A. So you would draw A as being in the interior of B. Another notion that I haven't really described above, but let's go ahead and mention it, is the notion of set subtraction. We have A subtract the set B. That corresponds to every element in A that is not in B. So it is in fact possible to prove that A subtract B, and you might actually be required to show this in your homework, and the way you'd probably show it is by playing around with Venn diagrams. You can say this is A intersected with the complement of B. So A and not B. So what does set subtraction look like as a Venn diagram? We have the set A, we have the set B, and we draw everything in A, and we shade everything in A that is not in B. So you kind of subtract out the set B. It's as if you had these pieces of paper. You put the piece of paper, the B piece of paper on top of the A piece of paper, and then you cut out the part of the A piece of paper that's in the B piece of paper. Excuse me. Okay, so let's see an example. Use a Venn diagram to illustrate A or B complement, or A and B. Before I continue on, let's just make sure I'm still streaming. I'm still streaming. At some point, I'll relax about that, but today is not that day. Let's get started by just drawing the Venn diagram. Oops, I don't want red yet. So here is my Venn diagram for the sample space S. I have A and I have B. Okay, so I'm first going to illustrate the event A intersected with B. I'm going to do so in blue. So A intersected B, that's the region that is in both A and B. As for A or B complement, you have the union of A or B, which is kind of this figure 8 looking region here, and I want everything outside of that region because I want the complement of that region. So I'm going to shade it everything that is outside of that region, and this is what you end up with. Okay, so that's one example. Next example, consider three sets A, B, and C. So how would I draw these in a Venn diagram? I would have my square denoting the universe of possibilities, which is S, and then I draw 3 circles, one for A, one for B, and one for C. So what is the union of A, B, and C? Well, it's going to be the set where if I shade A, everything in A, and then I shade everything that's in B, and then I shade everything that's in C, if the point ever got shaded, it's going to be in that union. All right. Next up, we have A intersected with B intersected with C. So let's draw our universe. Here's our sample space. So we have A, B, and C. So let's see. Let's take a point right here. This point that I just drew is a point that is in B and it is in C, but it is not in A, so it's not going to be in the intersection. This point right here is in B, but it's in neither A or C. But it's also just not in A, so it's not going to be in the intersection of all three. And you can just start reasoning about all of these points in a similar way, and the conclusion that you're forced to reach is that this little sliver here is the only part that's going to be in all three sets. So that corresponds to the intersection of all three. All right, next example. This is a more complicated one. We have A intersected with B, or A intersected with C, or B intersected with C. What is that going to look like? Well, let's get started. I don't want red. All right, here's our sample space. Here is A. Here is B. Here is C. All right, let's start out by building this thing up with the intersection A and B. All right, here's A and B. Here's A and C. And here's B and C. So this pinwheel looking region is the only region that ever got shaded, so that's going to correspond to the union of the three intersections. So this would, in words, this would be an event where at least two events happen. That's what it would correspond to. All right, so example 8, describe the intersection, complement, and union of events described in examples 1 through 5. Let me get caught up. So the point of this section is to go from these pictorial representation, or not this section, this example, is to go from these pictorial representations of events to more algebraic representations. So let's go with example 1. So for example 1, that was the example where we were flipping a coin and we could get either heads or tails. We could have the intersection of heads and tails. Of the two sets, heads and tails, these two sets have nothing in common. They are therefore considered disjoint events. So the intersection of these is the empty set, since you would only restrict yourself to what is in common, and they have nothing in common. Whereas the event heads or tails, that event would correspond to the event heads with heads and tails, which corresponds, by the way, to the sample space. Okay. Here's also some basic properties for you. Let's take an arbitrary set S. No, not S. Let's take an arbitrary event A. A intersected with the sample space is equal to A, since A is a subset of the sample space. In fact, in general, if A is a subset of B, then A intersected with B is going to be A, and A union with B is going to be B. And I'm just going to leave it at that. I want you to think about why that's true. Go try and reason about it with Venn diagrams. So, and in fact, that pretty much says everything that I would want to say about the sample space and the empty set, because since A is a subset of the sample space, A intersected with S is going to be A, and A union with S is going to be S. Likewise, A intersected with the empty set is a subset of A. Therefore, the intersection of two is going to be the subset, which is going to be the empty set. On the other hand, A union with the empty set is going to equal A, since A contains the empty set. All right, continuing on with what I was saying before. The next example. So example 2. We have, for example, the sets. My notation in the notes is a little bit different from one I'm sure I wrote down earlier. So let's I don't want to go all the way back there. I'll just throw some stuff out. We could have, for example, this was the one where we were rolling a die. We could say that the union of the set 1 with the die roll of 1 and the set with the die roll of so the intersection of these two sets, this is also going to be the empty set since they have nothing in common. But the intersection of the event with no, the union of these two sets is going to be the event that contains both of these possible outcomes. Darn laptop. So 1 and 3. And maybe less trivially, we could have the event, let's say 1, 3, 5. So this would correspond to an odd number of pips. And we're going to intersect that with the event where the number of pips doesn't exceed 3. So that would be the event where you have 1, 2, and 3. Okay. So the intersection of these two events is going to be, well, let's see, what outcomes do they have in common? 1 appears in both of them. 3 appears in this set, but it doesn't appear in the other one. So let's see, we've got 1. 1 appears in both. 3 appears in only 1. No, 3 actually appears in both of them. So 3 appears in both of them. 5 appears only in 1, and 2 only appears in 1. So whatever got underlined twice, that is going to be in the intersection of these two sets. So we're going to end up with the set 1 and 3. Now, for a lot of these set relationships, such as and or, you can kind of think logically using English. Like, for example, maybe going to the fourth example where I had sets where, I was rolling 2 dice, a red die and a blue die. You could imagine a set where they sum to 7 and the blue dice is at least 3. So maybe going to that. So in the context of example 4. So in the context of example 4, so they sum to 7. And they don't, no. The blue dice. So blue dice is let's say 5. So that would correspond to the event where you have so let's see, the blue dice is at least 5, so we could have the blue dice be 5. Stupid pen. So the blue dice could be 5, or the blue dice could be 6. And in these two situations, we know what the red dice is going to be. In the first, the red dice is going to be 2, and in the second, the red dice is going to be 1. So this would be the corresponding resulting event after we do that intersection. Okay. I'm going to leave it at that. Because there's a lot of examples. So for the rest of these, maybe try going through some of the events that I listed down and figuring out if you intersect or complement these events. So intersection, complementation, union, all these things. Try going through those sets and seeing what you get. Okay? But I've given you some examples to start working off of for now. All right, so I'm going to leave that for this section, and I will see you in section 2, where we go beyond just talking about some basic set theory and actually start saying what it takes to build a probability model. All right, so I will see you later.
Hey, students. All right, so let's move on now to the next section on starting probability theory. So, in order for us to, we would like to be able to assign numbers to events from sample spaces to describe how likely those events are. And in order to do so, we need to develop a notion of probability. So we'll start by defining what a probability measure is. So we have what's known as a probability measure, P, and this is a function. It's a function that takes events as inputs and returns numbers between 0 and 1 and satisfies the following three axioms. And axioms are things that are true basically because we say so. They're almost similar to assumptions. Maybe you remember axioms from geometry, but the idea is that we have some starting things that we simply say they are true because they are almost self-evident. First, we say that every probability must be at least 0. You cannot have negative probabilities. Second, we say that the probability of the sample space is equal to 1. So the probability that anything happens is equal to 1. Finally, this is the weirdest looking axiom. If we have a sequence of disjoint events, so in other words, for any I that's I equal to j, the intersection of any two such events is equal to the empty set. And furthermore, this is for a potentially infinite sequence of disjoint events. We say that the probability of the union of those events is equal to the sum of their individual probabilities. This is very wordy. This is very technical. There is a much easier way to understand what this axiom is saying if we decide, well, okay, there's usually only one situation where you're going to understand, where you're actually going to use this axiom most of the time, which is that if A intersected with B is equal to the empty set, so if A and B are two disjoint events, then the probability of A or B is equal to the probability of A plus the probability of B. So the probability of two events that have nothing in common, if the probability that either one happens will be the sum of their individual probabilities. Okay, so these are true because we say so, and from this we get pretty much everything else that we believe should be true about probability, or about how probabilities work. So for starters, we have that the probability of the empty set is equal to 0. So this is not something that we said. This is not something that we said must be true. This is simply something that this is actually a consequence of the assumptions that we have made up to this point. So this is kind of a weird... So we're going to show that this is in fact true using just these three axioms. So only these three things. All right. Now that said, we're going to have to use the fact that the probability of the sample space is equal to 1. What we could say is this: the sample space is equal to the sample space unioned with the empty set. And in order to use axiom 3 in the way we have written axiom 3 down, we're going to have to say that the empty set is equal to the union from I equals 1 to I equals 1 to infinity, the empty set. So in other words, we need to create an infinite union of empty sets. And it's certainly true that if you take an infinite collection of empty sets and you union them all together, there's still not going to be anything in that union, so you're still going to have the empty set. Furthermore, the intersection of the empty set with the empty set is also going to be the empty set, so technically the empty set is disjoint with itself. So that means that this collection of empty sets, this giant repeating of the empty set, technically satisfies the condition of the conditions of the third axiom. So then, and also it's true that the sample space intersected with the empty set is going to be the empty set because the empty set is a subset of the sample space.
Therefore, we can now apply this third axiom to prove the proposition, because we know that 1 is equal to the probability of the sample space, and the probability of the sample space is equal to the probability of the sample spaced unioned with the empty set, which is equal to the probability of the sample space unioned with this infinite collection of empty sets. And then we apply that third axiom to say that this is going to equal to the probability of the sample space plus the sum from I equals 1 to infinity, the probability of the empty set. And what that forces us to then say is that since the probability of the sample space is equal to 1, we're forced then to say that the sum from I equals 1 to infinity of the probability of the empty set is equal to 0. But that's only going to be possible if the probability of the empty set is itself equal to 0. Because since probabilities cannot be negative, and even just because of the fact that we're adding up something an infinite number of times, and that's the exact same thing, and it adds up to 0. So that means that each one of those must be equal to 0. Therefore, this proposition is proven. This was actually rather weird. It's so surprising. Like there is a way in which you kind of just want to say you have 1 equals to the probability of the sample space, which is equal to the probability of the sample space plus the sample space unioned with the empty set, and then it turns into a sum of probabilities, and that means that the probability of the empty set is equal to 0. But we have to, in order to be mathematically rigorous, use these axioms in the way they were written down. So we would actually have written the axiom in a way in which it wasn't written, and therefore wouldn't be able to directly apply it. So we had to be really tricky, but the good news is that we only had to be tricky really once with this proposition, just with this one, because now that we have this proposition, the others will not be nearly as strange. For example, proposition 3. Like this proposition, if we had this already, then that proposition that we just proved would actually be rather easy, because the complement of the sample space is equal to the empty set. The probability of the sample space is equal to 1, and since the empty set is the complement of the sample space, we can say if this proposition 3 were in fact true, the probability of the empty set is equal to 1 minus the probability of the sample space, which is 1 minus 1, which equals 0. Right? If we had proposition 3, then it would actually be rather easy to prove that the probability of the empty set is 0. But the thing, though, is in order to be able to prove proposition 3, we're going to have to probably use some of those other propositions. So, unfortunately, it's not quite that. We technically need to take a very long circuitous route in our proof before we can actually invoke this one. So what we're going to say is that the probability of the sample space, we can say that the sample space can be divided into the set A unioned with the complement of A. And A union A complement, A intersected with A complement is equal to the empty set. So since A intersected with its complement is the empty set, that means that these two sets are going to be disjoint, which means that we can then invoke that third axiom and say that the probability of the sample space is equal to the probability of A union A complement, which is equal to, by that other axiom, the probability of A plus the probability of A complement. And by the first axiom, this is all equal to 1. Therefore, after you do a little bit of algebra where you subtract both from both sides the probability of A, after you do that algebra, you can now say that the probability of A complement is equal to 1 minus the probability of A. And we're done. That proposition has been proven. Next proposition. We have that the probability of A is less than or equal to 1 for any event A. Let me get caught up in my notes over here. All right. So the probability of A complement, since A complement is in fact an event, by the first axiom, we get to say that the probability of A complement is greater than or equal to 0. Which means that 1 minus the probability of A is going to be greater than or equal to 0. And therefore, it follows after we add the probability of A to both sides. After we do that, we get to say that, so since these two things end up canceling out, the probability of A is less than or equal to 1. So that proposition has been proven. Next one. Where is that it? No, that's not it. The probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersected with B for any events A and B. So this, by the way, is generalizing more or less that third axiom, since that third axiom required disjoint events, whereas here in this proposition, we do not require disjoint events. We do not require just disjoint events, and the penalty that we pay for that is that we have to subtract out the probability of the intersection. Here's the thing, though. This makes perfect sense what's going on if we draw a Venn diagram. It turns out that probability is part of this general class of mathematical objects, or probability measures are part of this general class of mathematical objects known as measures. And amongst that family of mathematical objects, we include things such as measures of area or measures of length, which means that it's actually rather appropriate and convenient to reason about probabilities the same way we reason about areas or lengths as we do in the real world. So let's think instead about, we have a couple sets A and B. We want to figure out what the area is in A and B, that's enclosed within both of those. We want to figure out that area. And how we're going to do so is we have a couple sheets. We have an A sheet and a B sheet, and then we lay them down, and we have some scissors. So we can measure the areas of these sheets. So given that we're able to measure the areas of these sheets, how could we possibly compute the area that's enclosed in both A and B? Well, what we would do is we would lay down the A sheet onto this diagram, and we would have its area. Then we would lay down the B sheet on this diagram, and we would have its area. But the thing, though, is once we've done that, we now have an overlap. We have an overlapping area. So we've actually overcounted the area in A and B. The number is too large. So what we need to do is subtract out the overlapping part of A and B, subtract out its area, because otherwise we would have double counted it. So we're going to subtract out that area, or at least we'll cut out a little slice of it. Maybe just the red slice part and leaving only the blue part left. And we're allowed to measure the area of the part that we cut out. So after we subtract the area that we removed, we now have the area that's enclosed between that's closed within these two circles, and that's an aerial way to understand why this formula here is in fact true, because this is because how I described it is basically what we're doing. We have the area of the region A and the area of the region B, and we subtract out once the area that's in between them, since we accidentally, well, not accidentally, since without doing so, we would have double counted that part. So we need to remove the double counting. So now that's like a reasoning for what we're doing. And now let's turn that into a series of mathematical statements and a proof. Here's a way to think about this region, this Venn diagram. We can divide up in this Venn diagram. We can divide up this region so that we have the light blue region, we have the green region, and we have the red region. We will call the blue region A and not B. We will call the green region A and B. And we will call the red region not A and B. And it's clear that these three regions are disjoint. You can see so visually, but if you wanted a non-visual way to reason why that is the case, let's suppose an element is let's suppose that we pick a point that is in the set A and not B. Can that set be in A and B? Well, it must not, because in order to be in the part A and B, it must be in B. But it is not in B since it's in A and not B, so it cannot be in there. And similarly for not A and B, and for the same reason, if you're in A and not B, you cannot also be in not A and B, since you are in A and therefore you're not in not A. I know the verbiage is getting really complicated, but that is really the logic for why these things must be disjoint. Or you can just look at the picture and be satisfied. For that reason, we can say that you can also look at this picture and see that when you take the union of these three events, you have, in fact, the region A or B. And there's also no double counting here, since you counted each little part, each division once. So now we can say, I'm going to zoom in some more. We can say that the probability of A or B is equal to, invoking that third axiom, the probability of A and not B plus the probability of A and B plus the probability of not A and B. And let's see. How should I proceed next? Well, I do notice, for starters, that this part right here is equal to the probability of A, which is clear from the picture. Because if you add the probability of A and not B and the probability of A and B, then you're basically counted the probability of A. So this must be the probability of A. But the thing is, though, we need to somehow account for... we end up in the end with a subtraction of the probability of A and B. So how are we going to do that, Well, if we look at the probability of B, we could say, as an aside, that the probability of B is equal to the probability, for basically the reasons that I just wrote here, that this is the probability of A and B plus the probability of not A and B. And then if you do some algebra, you can then say that the probability of not A and B is equal to the probability of B minus the probability of A and B. Okay. Oh, well, look at that. We now basically have what we need because we've identified a part as the probability of A, and we can also identify the latter part in this sum as the probability of B minus the probability of A and B, which is exactly the statement that we wanted to prove. So therefore, we're done. And we have in fact proven this statement. And notice that this statement does in fact include that third axiom since that third axiom was about disjoint events. So, if we have a disjoint event, we've proven in the first proposition that we proved in this section that the probability of the empty set is equal to 0. And the subtraction of the probability of A and B is going to give you so that's going to so the intersection of A and B, since in this imaginary scenario they're a disjoint, that's going to be the probability of the empty set, which is equal to 0, and thus you get that other axiom. All right, so oops, I am doing something that I don't want to do. What I want to do is zoom out. Okay. So the next proposition I'm not going to bother to prove just because it's a lot of work. Although I may give you an argument for why it's true. So proposition 6, now we have 3 events, A, B, and C. And the probability of the union of those 3 events is going to be the sum of the probabilities of the events minus the probabilities of intersections of 2 plus the probability of the intersection of all 3. All right, so I'm not going to prove this, but I'm going to give you an argument for why this must be true. So here we have our sample space. We have the set A, we have the set B, and we have the set C. It's basically the same reasoning as we used before. Let's see. So what does it mean to add the probability of A, probability of B, probability of C? So if we add those 3 probabilities, so we're going to add the probability of A, because what we're trying to do is figure out in the area that is enclosed in all 3 circles. But those circles are overlapping with each other, so we need to figure out how to handle the overlaps. So we're going to color in the probability of A, that's what we're told to do first. Then we're going to color in the region enclosed by B, that's what we need to do second. And then we're going to enclose the region enclosed then we're going to color in the region enclosed by C, because that's what we've been told to do. Yeah, you can almost read this as a set of instructions on how to calculate an area. So we see that we have done some double counting. We've double counted here, we've double counted here, and we double counted here. All right, so we need to remove those double counts. Let's start with the let's start with the double counting here. We're going to subtract out the probability of A and B, which I will understand that as subtracting out a little green sliver. So how does this? I'm wondering if this is doing some. Oh no, it just was being laggy. All right, so I've subtracted out the green area from that sliver, leaving blue left and some red left. Okay, and then I'm going to cut out the red area that is that is at the intersection of A and C. Okay, so I'm going to cut that out, leaving only blue. Leaving only blue there. Let's see. So we're going to have right here. So, and then we need to cut out the area that is in the intersection of B, and so we now need to cut out the region that's in both B and C. So we're going to subtract out the red area, but the thing is that isn't enough. we cannot just take out the red area because we need to take out everything that's in here. So we also have to take out what that little blue sliver that's left as well. So we're going to be left with green in that spot. But the thing is, in that little sliver that is in the intersection of all three, we have now cut out. We have now cut out too much, and that area is not being accounted for at all. There's nothing left in there. So we need to add that area back in order to be able to have an accurate computation of the area. And there we go. So after we add it back in, we now have the area. So everything has been colored exactly once. And we're able to compute the area of how much area we've colored, in a sense. So we have what we need. So not exactly a proof because we need to do some of that tricky algebra business, but we're not going to bother with that. This should give you an idea of why it's true. Okay, so the next example, all of that stuff was rather theoretical. Let's start seeing how probability theory is actually going to be used. So for the most part of the remainder of the section, I'm going to be going through a number of illustrative examples. We do talk a little bit more about theory, mostly about what probability means. But for the most part, we can just talk about examples. So, example 9. Reconsider the experiment of flipping a coin and assume that the coin is equally likely to land with each face facing up. Assign probabilities to all outcomes in the sample space. So recall that the sample space for this experiment consists of the outcome heads and the outcome tails. And we're assuming that all of the outcomes in this sample space are equally likely. So that means that the probability of getting heads, and I'm writing this in terms of a simple event, but honestly, writing it this way often gets rather tedious. So I'm often going to omit the curly braces that are usually used to denote sets and just write whatever is in the set. So we have the probability of H. This is going to equal the probability of T because all outcomes are equally likely. So the thing though is the probability of the sample space is equal to the probability of the set containing only H unioned with the set containing only T, since the union of those two sets is in fact equal to the sample space. And furthermore, those two sets have nothing in common. One has H, one has T, and they don't share anything. So that means that they are disjoint events, and therefore we can write this probability as a sum, as the probability of H plus the probability of T. And both of these are the same, so we're going to say that this is equal to P. So this is equal to P plus P, which is 2P. And furthermore, we know from axiom 2 that the probability of the sample space is equal to 1. So this is equal to 1, and that implies, after you do some division by 2, that P is equal to 1/2. Which makes perfect sense, right? If you're saying that heads is just as likely as tails, then the probability of getting heads is 1/2. Perfectly intuitive, right? Well, probability is intuitive up until the point it isn't. And when it stops being intuitive, it really stops being intuitive. And it becomes suddenly very, very strange. So it's simultaneously intuitive and unintuitive. In fact, I've heard someone say that there are fewer subjects with as many paradoxes. They're not literally paradoxes, but they contradict how humans think of the world. Very few subjects have as many paradoxes as probability, because probability can get really weird really fast. We have not reached that point yet, but we probably will eventually. Example 10. Do the same as example 9, but when rolling a single dice. That is, we are trying to... we're trying to assign probabilities to outcomes in a sample space when we say that those outcomes are equally likely. So the sample space in this case is going to consist of die rolls. So we have an outcome 1, 2, 3, 4, 5, and 6. Okay, so those are our 6 outcomes, and we say that each one of them is equally likely. So that means that the probability of rolling a 1 is the same as the probability of rolling a 2, and that's going to be the same as as this, and the same as the probability of rolling a 6. All right, so it's a 6. So, all right, there we go, 6. It's an oddly painted die. All right, so all of those are going to be the same, and we're just going to say for convenience that this is equal to p. All right, so then we say that the probability of the sample space is equal to the probability of the result 1 unioned with the result 2 unioned with ... unioned with the outcome containing 6. There we go. Because that's equal to the sample space. You've basically written the sample space as a union of each of its elements. And furthermore, each of these sets, again, are disjoint. So we can then write them as the sum of probabilities. So say that this is equal to the probability of rolling a 1 plus the probability of rolling a 2 plus ... plus the probability of rolling a 6. And then we use the fact that we said from the beginning that all of these probabilities are the same. So this is p plus p plus p plus p plus p plus p. So this is equal to 6p. But it's also equal to 1 because of axiom 2. That says that the probability of the sample space is equal to 1. Therefore, p must be equal to 1 over 6. And you can see where this is going. In general, if you have a sample space with a finite number of elements, and you say each of those elements are equally likely, then the probability of a single one of those elements in that sample space, the probability of drawing that element is going to be 1 divided by the size of the sample space, or the number of unique elements in that sample space. So in fact, what we're seeing here can be very easily generalized. Okay. So example 11, we're now going to try and move away from equally likely outcomes and say that the dice from example 10 has been altered with weights. Now the probability of the dice rolling a 6 is twice as likely as rolling a 1, while all the other sides have the same probability of appearing as before. Therefore, we want to know what the new probability model is. So we're going to say that the probability of rolling a 6, so 1, 2, 3, 4, 5, 6. So the probability of rolling a 6 is equal to 2 times the probability of rolling a 1. And we're just going to say that's equal to 2 times p. Or we'll try to keep things a little bit different. We'll call it q this time. All right? So we need to figure out q because q gives us the probability of rolling a 1. And if we figure out the probability of rolling a 1, we then instantly know rolling a 6. Now remember, these are the only 2 faces that have been altered. All the other dice faces have the exact same probability as before. So the probability of rolling a 2 is equal to the probability of rolling a 3, which is the probability of rolling a 4, which is the probability of rolling a 5, and all of those are equal to 1 over 6. So that means that the probability of rolling a 1 plus the probability of rolling a 2 plus ... plus the probability of rolling a 5 plus the probability of rolling a 6 come on, cooperate, you stupid screen. I hate drawing the 6 because my screen is not very cooperative. All right. This is equal to 1. But what's different now is that all of these are equal to 1 over 6. So you end up adding 1 over 6 4 times, since it's 2, 3, 4, 5. There's 4 things there. The probability of rolling a 6 is equal to 2q, and the probability of rolling a 1 is equal to q. Okay? So collecting all of that information, we now say that we have q plus 2q plus 4 over 6, which is 2 over 3, is equal to 1, which implies, after you do some algebra, that 3q is equal to 1/3, which then means that q is equal to 9. Is equal to 1 over 9, not 9, because that's not even a probability. That's one thing to keep in mind. If you get a probability that's above 1, you have made a mistake. So 9 is not possible. So that means that the probability of rolling a 1. So yeah, let's write this down now. The probability of rolling a 1 in this new probability model is equal to 1/9, and the probability of rolling a 6 in this new probability model is equal to 2 over 9. And in fact, this is consistent, because 1 over 9 plus 2 over 9 is equal to 3 over 9, which is 1/3. The other dice faces, when you add up their probabilities, you add 1 over 6, 1 over 6, 1 over 6, 1 over 6, which is 2/3. And so you have 1/3 plus 2/3, which equals 1. So the probabilities still add up to 1, which means that we're fine. This is a way for you to check this is one way for you to check that when you do your probability calculations, you have done so correctly. Make sure that all the probabilities add up to 1. If they don't add up to 1, you've made a mistake. I remember once a student was working in I had a student of mine, and I gave her a quiz, and she had to do some calculation with probabilities, and she added up the probability sample space, and it added up to something that was to some fraction. It might have been maybe 8 over 9 or 80 over 81, who knows. But I said, this is very wrong. And she's like, well, it needs to add up to 1. And she said, well, it's close to 1. And I said, close to 1 is not 1. So if it doesn't add up to 1, it's just wrong. Close to 1, no caboose. It's either 1 or it's not 1. And if it doesn't add up to 1, it's wrong. It's very wrong. It always adds up to 1. So that's a way for you to check that you've done things correctly. Make sure that your probabilities add up to 1. Okay. Moving on. Example 12. Reconsider the experiment of rolling 2 six-sided die. It is reasonable to assume that each outcome in S is equally likely. This is the reason why, instead of writing the numbers 2 through 12, or maybe just listing out without really caring about the ordering of the die, or not really thinking about there being a red die and a blue die, we decided that we were actually going to assign an ordering to the dice. It's so that we could basically work with problem example 12 and get a reasonable looking probability model. Because now, if we assume that the two dice are distinct, we can now say that everything in the sample space, in that sample space with the red and blue die, is equally likely, and then get accurate probability calculations. So, getting back to this, it is reasonable to assume that each outcome in the sample space S is equally likely. What then is the probability of each outcome in S? Well, basically, I already argued it to you before. We'll say that omega is an element of S. So I'm saying this in general, right? Omega is an element in S, and every element in S is equally likely. I argued before, without writing it down, that the probability of drawing omega then will be 1 divided by the size of S. So in this case, for example 12, where you have 2 six-sided dice, the size of the sample space was 36. So the probability of a particular outcome of dice is going to be 1 over 36. Now we can use this this model to find the probability of an event E. So I'll just go ahead and write down in this case that the size of the sample space S is equal to 36. So for this particular problem, this is going to be 1 over 36. But in fact, what I just wrote down here what I just wrote down here is pretty much true in general. Like, I'm thinking in the context of rolling a couple die, but actually this is true in general. When you say that S, which is a finite sample space, has a finite number of elements, when everything in that sample space is equally likely, then the probability of an individual element is going to be 1 over the size of the sample space. And it's not too hard. Why? Go ahead. Show that the probability of the sample space when you do this is equal to 1. So use this model to find the probability of an event E where, first, E is the event where at least one die is a 6. So let's actually write down... what's in E. So that would be, we have a red die and a blue die. At least one die is 6. So that includes when the red die is 1 and the blue die is 6. We have the case when the red die is 2 and the blue die is 6. We can keep going on like this until we eventually reach the case where the red die is a 5. The red die is 5, and the blue die is 6. Ugh. Damn it, you cooperate. All right, that's 6. So that's one set of outcomes, and notice that there's that I've just listed down 5 elements. Okay. So next up, we will now make the red die 6. So we've got 1, 2, 3, 4, 5, 6. It never wants to do the last one. Never, ever wants to do the last one. All right, so 1, 2, 3, 4, 5, 6, and the blue die is 1. And just repeat. Just keep carrying on with this logic until we get where the red dice is 6 and the blue dice is 5. And finally, we have one last outcome where both the red die and the blue die are 6. So 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, 6. All right. So there are 5 elements where the where the red die is fixed at 6, and then there's one extra element where both of them are 6. So that means that the size of this event is going to be 11, which then means when we're computing the probability of this event, we could add up the probability of each one of these outcomes, and each one of these outcomes has an equal likelihood, and they all have an equal probability. All those probabilities are 36, so you're going to add up 36, 1 over 36, 11 times. So this is going to add up to 11 over 36. And in fact, once you have this assumption that all outcomes in this finite sample space are equally likely, in general, the probability of any event E is going to be the number of elements in E, or the size of E, divided by the size of the sample space. So at this point, all we need to do is determine how many elements are in our event in order to figure out that event's probability. All right. So let's use that now for this next problem, where E is the event where the sum of the pips showing on the 2 die is 5. how many outcomes are there where the sum is going to be 5? Let's start listing out things in this sample space. So we've got, I guess I've been writing the red dice first. Okay, so this is... All right, so I've been writing out the red die first. So let's see, the 2 dice is 5. So can the red dice be 1? Yeah, sure, why not? The red dice can be 1, and if it's 1, well, it must add up to 5, so that means that the blue dice must be 4. Okay, that's one possibility. Next possibility is when the blue dice is 2, is when the red dice is 2, in which case the blue dice must be 3. We could have the case where the red dice is 3, in which case the blue dice must be 2. And finally, we have the case where the red dice is 4, in which case the blue dice must be 1. And we can't go to 5 because it's not possible for the blue dice to roll a 0. So we're just going to have to end it there. We now have an event, and this event has 4 outcomes in it. So that means that the size of the event is going to be 4, in which case the probability of the event E is going to be 4 over 36, which is going to be 1 over 9. Okay. Next part. E is the event where the maximum of the 2 numbers showing on the dice is greater than 2. Okay, now here's the thing though. There's actually a lot of outcomes in this event. So we could attempt to try and figure out how many outcomes there are where the larger of the 2 numbers is greater than 2. Well, let's see. We could even have like 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6. All the cases where the red dice is 3, and that's already 6 such outcomes. And that's only for 3. So this could actually be quite difficult to compute, except for the fact that it's actually much easier to compute the probability of the complement of this event. If we were to look at the complement of the event E, that's going to be the event where the maximum of the 2 dice is not greater than 2. So it's at most 2. Okay. What are combinations of dice faces where the maximum is at most 2? Well, we have one situation where we have I said that the red dice is first. So we have the situation where the red dice is 1 and the blue dice is 1. All right, in that case, the maximum of the 2 dice is going to be 1, and that is not greater than 2. So this is, in fact, in our event. Then we have the outcome where the red dice is 2 and the blue dice is 1. In that case, the maximum would be 2, and that doesn't exceed 2. So this is in our event. We also have the case where the red dice is 1 and the blue dice is 2. Let's see. All right, there we go. So the blue dice is 2. And we also have the outcome where the red dice is 2 and the blue dice is 2. I mean, the maximum of those in this case would be 2, and again, that's at most 2. And we had to stop there because the next thing we would do is make one of the dice at least 3. And in which case the maximum would be at least 3. So it's not no longer going to be in this event. So therefore, we have an event with 4 outcomes in it, and the probability of the complement of the event E is going to be the number of things in the complement of E, which is 4, divided by 36, which is equal to 1 over 9. All right, we're cooking, because now we can use one of those propositions that said that the probability of the complement of an event is 1 minus the probability of the event. So that means that the probability of E itself, which is what we actually want to compute a probability of, that's going to be 1 minus the probability of E complement, because E is the complement of E complement. And that's going to be 1 minus 1 over 9, which is 8 over 9. There we go. We've solved it. And that's much easier than if we tried to do it directly. And this is one reason why you care about these complementation rules, because sometimes it's easier to work with the complement of an event rather than the event itself. If we had tried to work with that event, we would have ended up with a sample space with, or an event with 32 elements, or a size of 32. So we would have ended up having to count 32 things. I mean, it's not like impossible to count 32 things, but it's also a lot more work. So this is a very good trick to have, and something that you should be looking out for when you're doing your own work. You should be looking out for situations where the complement is actually easier to work with than the actual event itself. Okay, just real quick, satisfy my nervousness. All right, we're still streaming. All right, so we shall continue. Example 13. Reconsider the experiment of flipping a coin until heads is seen. Ooh, this one. This one's going to get rather involved. What is one way to assign probabilities to all outcomes of this experiment so that we have a legal probability model? Justify your answer. So, how could we possibly do this? Because we no longer can say that each outcome in the sample space is equally likely, because that only works when the sample space is finite. But as I mentioned before, this sample space is infinite. There's an infinite number of outcomes in the sample space. It's basically the integers in a way. You can map the sample space to the integers and kind of identify it with the integers. Or not the integers, but the natural numbers. And in fact, I think that's what we should do. We should try to view this sample space in terms of the natural numbers. I'm going to want to zoom in for this one. Zooming in for me is a way to almost get more room on this piece of paper. So we're going to say we're going to define n of omega. So omega is an element of this sample space. So this is going to be one of those strings: heads, tails, heads, tails, tails, heads, tails, 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 heads, and so on. So we'll say that n of omega is going to equal the length of the string omega. So for example, n of the string tth, this is a string of length 3. It then follows that abusing notation a little bit, because n is a function that doesn't take sets as inputs. But let's suppose for a second that we were to put a set as the input. This is actually pretty commonly done. Often when you have a function and you plug in its domain, what you're actually referring to is a set representing the range of that function. So in this case, the range of the function n is going to be the natural numbers. It's going to be 1, 2, 3, 4, and so on. These are all the possible outcomes. It's going to be the natural numbers. Okay? So, I'm going to suggest that what we should do for our probability assignment is say that the probability of an outcome omega is equal to 1/2 to the power of n of omega. So in other words, it's going to be 1/2 to the power of the length of the string omega. So for example, in this earlier case where we had tth, the probability of that outcome tth would be 1/2 to the power of the length of the string tth, or 1/2 to the power of 3, which is 1/8. Okay? All right then. So this is a suggestion for what the probability should be. But now I need to make sure that this is a valid probability measure. So what needs to be true in order for this to be the case? First off is the probability of, are all probabilities greater than or equal to 0 under this method? Yes, that is certainly true, because there's no way that this function will produce negative numbers. Secondly, is the probability of the sample space equal to 1? Well, that's actually something that we're probably going to have to check. And then there's that third axiom about the probability of about the probability of unions of disjoint events. And I'm not going to check that one because that one's actually getting rather complicated. That's getting even more theoretical, a bit too theoretical for this class. But I personally think it's perfectly appropriate to check that under this probability model, the probability of the sample space is equal to 1. And in fact, in my classes, this is actually something that I love to ask questions about on quizzes. I love to ask students that the probability of the sample space is equal to 1 under some probability model. I love asking that. So if you are in my class, you should expect a question like that. You should expect me to ask you to show that the probability of the sample space is 1 under some potential probability measure. Or alternatively, very very similarly, I might give you a probability measure, but it depends on some unknown constant, and I might ask you to compute what the constant is that causes the probability measure to be a valid probability measure. That is, the probability of the sample space would be 1 under that measure. Right. So this is something to look out for if you're actually taking classes from me. But let's get back to the issue at hand. I need to show that the probability of the sample space under this probability model is in fact equal to 1. So the probability of the sample space here is going to end up being the sum. I can basically view the sample space as consisting as being the union of all of these of events where each of these events contains one of these strings HTTH, TTTTH, something like that. And this is actually a situation where that third form of where the way I wrote down axiom 3 before, you really actually need it the way I wrote it down originally in like the body of the lecture notes rather than that footnote. Because we actually do, in fact, here have an infinite collection of events. So I'm going to write, this is going to be the sum over all of the omega that's in the sample space of the probability of that omega. Right. So remember, what this is actually doing is summing up the probability of H, the probability of TH, the probability of TTH, the probability of TTTH, and so on. All right, continuing on. We can then say that this is equal to the sum over all omega in the sample space. We have our probability assignment. This is 1/2 to the power of n of omega. And at this point, I'm just going to say that n of omega is equal to the length that is equal to the length of that string. I can simplify what I'm writing down here a little bit by basically writing down what the image of n is over the set S. So I can now write equivalently that this is going to be the sum when n equals 1 to infinity of 1/2 to the power n. And now you should recognize from, I think they talk about this in Math 1010 at the University of Utah, intermediate algebra, that this is a geometric sum. This is a geometric sum, and there is a formula for finding the value of a geometric sum. So recall this formula from your previous classes. You have a number r such that the magnitude of r does not exceed 1. Then the sum from n equals, we'll say 1 to infinity of r to the power n is equal to r over 1 minus r. Remember that? Well, we're going to use that here right now. And we're going to say that this sum is equal to 1/2 over 1 minus 1/2, which is equal to 1/2 divided by 1/2, which is equal to 1. Which is what we wanted to show. We have now shown that the probability of the sample space under this probability measure is equal to 1. All right, hopefully you have written down this formula if you don't remember it, because I need to reclaim that space. Now that we have this, we can now start answering some questions. Now that we know that this is a valid probability model, we can start using it. So under this model, what is the probability that the number of flips needed to see the first head exceeds 4? So what I'm asking for is the probability of... I'm going to have to write this in a somewhat funny looking way. Go away. Stop bothering me. I'm going to have to write this in a somewhat funny looking way. I'm going to say that this is the probability of drawing an omega from the sample space, or drawing a sequence of flips, such that the length of that sequence is greater than 4. And this is another one of those situations where it's actually easier to work with the complement and say that this is equal to 1 minus the probability of drawing a string of flips such that the length of that string is less than or equal to 4. Okay, this is actually a finite set because we can actually list out the strings of flips in which the length of that string is less than or equal to 4. We have heads, we have tails heads, we have tails tails heads, and tails 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 heads. So this is 1 minus the probability, 1 minus the probability that you get heads on the first flip, plus the probability that you get tails heads, first tails then heads, plus the probability that you get tails and heads. And then you have the probability of 3 tails and a head. And we can in fact figure out what each of those probabilities are. The first probability is going to be 1/2. The second is going to be 1/2 to the power 2, or 1/4. The third is going to be 1/2 to the power 3, or 1/8. 1/8. And the last one is going to be 1/2 to the power 4, or 1/16. And long story short, this is going to be equal to 1 minus 15 over 16, which is equal to 1 over 16. Which is kind of funny. It's a little funny to think about that. Why is it that it is equal to 1 over 16? Well, here's kind of another way you could think about it. Well, it'll make more sense when we start talking about independence. But when thinking about independence, what you end up doing is, like, we know that if a coin is equally likely to get heads and tails, then we know that the probability of getting a heads is 1/2. So what would then be the probability of getting 4 tails in a row? Because that we must get at least 4 tails in a row in order for us to have at least 4 flips in order for us to get a head. So what we're actually asking for is the probability of getting 4 tails in a row. So what I notice is, well, let's see. If we were to think about getting 2 tails in a row, it seems like the probability of getting 2 tails in a row is 1/4, and 3 tails in a row is 1/8. And then 4 tails of a row, well, that's 1 over 16th. So that's an alternative way to think about what's going on here. But there's an algebraic way to get it. An algebraic way to get the answer. All right. The second part. What is the probability? The number of flips until the experiment ends. In other words, the last flip will be heads. Is between 3 and 20. This one is a little bit more painful. But actually, maybe we could use that trick. Well, let's see. What we could potentially do is say that the probability of observing a sequence of flips such that the length of that sequence is exactly less than 3. Well, that's going to be that's going to be the sequences where the length of the sequence is 1 or 2. So that's going to be heads or tails heads, and that's going to be 1/2 plus 1/4, which is 3/4. Now, let's compute the probability of observing a sequence of flips where the length of that sequence is greater than 20. Now, this is not so far computing the probability of being between inclusively 3 and 20. But the reason why I'm computing these numbers is because I'm actually thinking I might want to use that complement trick again. So I want to compute this probability where the length of the sequence is is strictly greater than 20. And I could actually use the arguments that I was using above to argue that this is going to be a sum from n equals 21 to infinity of 1/2 to the power n. Right? It's basically the same arguments that I was using before to compute the size of the sample space, because this is going to be computing so you have the sum of the probability when you have 21 flips, and then probably when you have 22 flips and 23 flips, and so on. And I could say, what should I do next? The thing is, unfortunately, I don't have a formula for when we're adding up starting at 21. I do have a formula when we add up starting at 1. So maybe what we could do is try to find a sneaky way to try adding up at 1 again. What I could potentially do is say that n minus 20 plus 20. I could say that this is equal to the sum n minus 20 is equal to 1. Because that's equivalent to saying that n is equal to 21, right? Certainly. And then I could say this is 1/2 to the power n minus 20 plus 20. Well, I remember now that we can actually write this as or the part enclosed in red as 1/2 to the power n minus 20 multiplied with 1/2 to the power 20. That's equivalent. Okay. So what can I use with that? Well, I can now say that this is equal. This is equal to 1/2 to the power. Oh, I don't want red. 1/2 to the power 20, since that is effectively a constant that doesn't depend on n. And I have a sum from n minus 20 equals 1 up to infinity of 1/2 to the power n minus 20. But what I could do is say, well, n minus 20, you know what? I'm just going to call that I. I'm just going to call n minus 20 equal. I'm just going to say that's I. So replace all the n minus 20s with I. So I equals 1 to infinity, 1/2 to the power I. Oh, I know how to compute this. This is going to be 1/2 times 1/2 divided by 1 minus 1/2. So actually, this part right here, in fact, this right here is pretty much a probability model. This is summing over the sample space. So this blue part, is equal to 1. So that means that this probability is equal to 1/2 to the power 20. Think about that. Once again, going back to this probability, the probability of getting a sample of getting a string of at least 20 means that you must have flipped at least 20 tails. And I've computed effectively the probability of getting 20 tails in a row. All right. Now, I'm still not done, though. Let's start collecting this information. I now know, let's see, that, so I'm going to start erasing all this because I need to start reclaiming some space. All right, so this is equal to 1/2 to the power 20. All right. So we can now say that the probability that of observing a sequence of flips such that 3 is less than or equal to the length of that sequence, which is less than or equal to 20, I could work instead with the complement of this and say this is 1 minus the probability of drawing an omega such that either n of omega is less than 3 or n of omega is greater than 20. And here's the thing, though. I've basically written down two disjoint sets. One set where n of omega is less than 3, or one set that is where n of omega is greater than 20. So either a sequence is less than 3 flips or more than 20 flips, but it's not both. So this is actually the union of two disjoint events. And therefore, I can say this is 1 minus the probability of drawing an omega such that n of omega is less than 3, plus the probability of drawing an omega such that the length of the string omega is greater than 20. And I have computed both of those probabilities. So this is equal to 1 minus 3/4 plus 1/2 to the power 20. And I'm just going to leave it at that. I'm not going to bother trying to simplify this because this is the correct answer. So we're done at this point. I'm not going to go any further. I'm going to, that said, reclaim all of this space and say, so hopefully you can rewind if you missed some of that and catch up on what you missed, because I'm erasing this right now. And we're going to say that the probability of this event E is equal to 1 minus 3/4 plus 1/2 to the power 20. All right. Next part. What is... Oh, yeah. I don't want this business. All right. What is the probability that an even number of flips is seen before the experiment ends? An even number of flips. How could I possibly think about that? So I want the probability of an even number of flips. And in short, using some of the reasoning that I was using above, I could say that this is the sum of 1/2. How would I represent an even number? I could say that an even number is 2 times a natural number. That guarantees that a number is even. So just take any natural number you want and multiply it by 2, and that's going to be an even number. In fact, that's going to cover all the even numbers. And I'm going to sum this up from m equals 1 to infinity. Now what do I do next? Well, what I could do is recognize that I can basically take the m out and say that this is 1/2 squared raised to the power m, so that this is equal to the sum when m equals 1 to infinity of 1/4 to the power m. Oh, I know how to sum that. That's going to be, since this is a geometric sum, 1/4 over 1 minus 1/4, which is equal to 1/4 over 3/4, and those 1/4 parts cancel out, so this ends up being 1/3. So the probability of an even number of flips is 1/3, which is kind of funny to think about if you think about it. It seems like an even number of flips and an odd number of flips is equally likely, but actually no. They're not equally likely at all. It's much more likely to have an odd number of flips, since it's much more likely to get one flip exactly. Okay. In fact, getting one flip is twice as likely as getting two flips. So by that reasoning, it actually makes perfect sense. Okay, moving on to the next part. That was all a lot of work. Okay, example 14. In a small town, 20% of the population is considered wealthy, 30% of the population identifies as black, and 5% of the population is wealthy and black. Select a random individual from this population, everyone equally likely to be selected, but I don't think that actually matters to this problem so much because of how I've laid it out. What is the probability that an individual is wealthy and not black? So let's see. Let me catch up in my notes. Here's how I would like to think about this one. With problems like this, where you have, let's start out by saying that we've got a sample space, but I'm not going to think too hard about what the sample space is for this one. I'm just going to say we have an event B, which corresponds to an individual being black or racially identifying as black. W will be the event that a person identifies as probably this is probably like some sort of a census business. So the Census Bureau has some, may have some more technical definition of wealthy, like they make over 90,000. Is making over 90,000 rendering you wealthy? Well, you're certainly well off, but anyway, that stuff aside, we'll just say W denotes the event that you are wealthy by some criterion. And the probability of B, that an individual is a black, will be 0.3, and the probability of W, that this individual is wealthy, is going to be 0.2. Okay, and that's just true because the problem said so. So now what we want to... Well, actually, we're also given another thing, that the probability of an individual being both wealthy and black is going to be 0.05. Oh, by the way, here's the thing to keep in mind. The probability of A and B is always going to be less than or equal to the probability of A. Or if you want, you can replace the probability of A with the probability of B. It's just as true. And that's because A and B is certainly a subset of A. And if you think about about probabilities in terms of areas, the area of a subset is certainly less than or equal to the area of the thing it is nested within. So you're always going to have a decrease in area. It's not possible, despite some human cognitive biases, for the probability of A and B, or something being true and something else also being true, it is not possible for that to exceed the probability that the original thing is true. I think people sometimes confuse intersection with conditional probability. That's probably what is going on when you start seeing those studies talk about stuff like that. Anyway, we need to figure out what is the probability that that an individual selected from this village is wealthy and not black. And here's how I like to solve problems like this. Let's make it clearer. All right. Here's how I like to solve problems like this. I like to create a Venn diagram. And in that Venn diagram, I will start filling out regions. So we'll have the wealthy circle and the black circle. And we have the sample space. And you start thinking about this like a puzzle. Like, we know that the wealthy and black part is 0.05. We're going to need to zoom in some more. So the wealthy and black part, that is going to be 0.05. Okay? And then we have the wealthy part, which is 0.2. But we can't put 0.2 here because that 0.2 is also including that 0.05. So we need to put here is 0.15 so that when we add this blue region and this red region, those need to add up to 0.2. Okay? Now for the black part. That needs to add up to 0.3. So that means that the part that is not in the intersection needs to be 0.25. I didn't write that very clearly. That needs to be 0.25. Okay? which for what it's worth, we now know the probability of W or B, which would be 0.45, which means that the probability of being neither wealthy nor black is going to be 0.55. So that's something that I recommend when you encounter problems like these. Create a Venn diagram and then fill out the diagram. Figure out the probability of every single little sliver in that Venn diagram, and then you can get any probability you want. All right. And it will be like a generally useful chart for you, not just for that individual problem, because often these problems come in bunches. All right, so continuing on, the probability of being wealthy and not black. Well, actually, that corresponds in our little chart up here to the blue region, which is going to be 0.15. So this is going to be 0.15. Okay, what is the probability that the individual is neither wealthy nor black? Actually, I already computed that. I said it in words. It's going to be 0.55. All right. Next example. A bag contains balls and blocks. 30% of the bag's contents are balls. An object is either red or blue, and 40% of the objects are red. An object is made of either wood or plastic, and 65% of the objects are wooden. 10% of the objects are wooden balls, 5% of the objects are red balls, and 20% of the objects are red and plastic. 2% of the objects are red plastic. There's a typo here. We're going to need to change blocks to balls. Okay. Reach into the bag and pick out an object at random. Each object equally likely to be selected. What is the probability that the object selected is a ball, red, or wooden? And this is inclusive, by the way. Well, this is another one of those problems where what I suggest you do is you create a Venn diagram to represent the situation and fill out all of the little parts of that Venn diagram. So what does that look like here? All right, so I've got my Venn diagram. This is my sample space. All right, so I've got giant circles, but I should probably be a bit more precise about, let's start, before I start filling out this chart, let's create some notation and fill out what we already know in mathematical notation. So we've got balls. So B will be the event that we grab a ball. And we'll say, so objects are either red or blue. So we'll say R is the event that an object pulled out of here is red. So B complement is going to be a block, and R complement is going to be a blue object. And we say that, so we can either have wood or plastic, so we'll have W correspond to the event that you get a wooden object. All right, let's start collecting some more information. We have that the probability of drawing a, we have the probability of drawing a ball, so the probability of the event B is equal to 0.3. The probability of getting a red object is 0.4. The probability of a wooden object is going to be 0.65. The probability that an object is a wooden ball, that's W intersected with B, since the object is both wooden and a ball, that is going to be 0.1. The probability of getting a red ball, is going to be 0.05. The probability of getting something that's red and plastic, so that's R and W complement, that's going to be 0.2. And finally, we have the probability of drawing a red plastic, so W complement, block, No, not a block. It's not a block. It's a ball. This is equal to 0.02. Okay. So. We need to start filling out this chart. We're going to have red here. We're going to have balls here, and we're going to have wooden objects over here. I always recommend starting out with the smallest region first. So the greatest intersection. Start out with that and then fill outwards. So in this case, the smallest region is red plastic balls. Where is that on our Venn diagram? You are in R, you are in B, but you're not in W, so that actually corresponds to the blue region. Okay, so the probability of the blue region, according to the problem, is 0.02. All right. Next up, we could probably ask for what is the probability of being red and plastic? Red and plastic, that corresponds to being, let's see, so you're in the red region, but you're not in the W region. So that's going to correspond to this blue area. And we know that the probability of being red and plastic is 0.2, but we've already got a 0.02. So that means that in the other part, we're going to be left with 0.18. So the probability of being a red plastic block is going to be 0.18. All right. How about next? We've got the probability of being a red ball. So the probability of being a red ball is going to be 0.05. What corresponds to red balls? Well, this is the ball. So we have the balls region and we have red stuff. So that's going to be corresponding to the red region. Okay, and that is 0.05, which means we've already got a 0.02 here. It needs to add it to 0.05, so that means that this little sliver in the middle is going to be 0.03. Okay, let's see. We need next wooden balls. So wooden balls corresponds to this green region. The probability of being a wooden ball is 0.1. So that we've already got a 0.03, so that means that we've got 0.07 in this other little sliver. All right, we're getting close to done. What about... let's see. So we've got wooden balls, red plastic things. What else have we got? Well, we've got the probability of balls. The probability of balls is going to be 0.3, and so balls corresponds to this blue region, and we've already got 0.12 of the area accounted for. The total area needs to be 0.3, so that means that for this remaining sliver, we have 0.18 for its area. Okay. Next up. Well, we've got the probability of red stuff, and we know that the probability of red stuff is 0.4. So 0.2. So red stuff is going to be the region I've just encircled in red, and so far 0.23 of that area is accounted for, but its total area is going to be 0.4. So that means that so that means that when we're filling out this remaining blue sliver, it must be 0.17. Okay, and for wooden stuff, we know that the total area in the wooden region is going to be 0.65, and 0.27 of that area is already accounted for, so that means that the remaining area is going to be 0.38. All right, and we are almost done. We actually, in fact, know the probability of everything else. If you were to add up all of those probabilities, they would add up to 0.98, so that means that the remaining area that is outside of this region is 0.02. All right, we have filled out that diagram, and we are ready to answer some questions. What is the probability that an object selected is a ball, red, or wooden? So that's the probability of R or W or B, and we have already figured that out. that corresponds to the 0.02. So that is equal to 0.02. Okay, next up, what is the probability that the object is a red wooden ball? So the probability of being red and wooden and a ball. What is that going to be? Well, we're going to go back to our diagram that we created. We look for red wooden balls, so you need to be in the red circle, you need to be wooden, so you need to be in the blue circle, and you need to be a ball, so you need to be in the green circle. I guess that's a darker blue. So that leaves us 0.03. So that leaves us 0.03 for that area. So this is going to be 0.03. All right. What is the probability? Let's go ahead and do some zooming out. We no longer need such fine control in drawing. What is the probability that an object is a blue plastic block? Well, the probability of being a blue, which is the complement of red, not in a color sense, not like when artists talk about complements, that's red is not a complement of blue, but whatever. In a probabilistic sense, in our probability model. So that's the region that we've drawn here, and it's actually a problem. I'm going to leave this to yourself, but look up De Morgan's laws. Learn about De Morgan's laws. For my students, this is an assignment, I believe, if I remember right. But basically, this is R union W union B complement, which then means it's 1 minus the probability of R union W union B, and that is a probability you've already figured out. That's 1 minus 0.98, which is equal to 0.02. Okay? Okay, so that's it for the examples. Those were a lot of examples. But I'm just going to... We're now wrapping up this section, and I'm going to wrap up this section with a short discussion on the interpretation of probability. Now, it turns out this is actually a rather large topic. Philosophers actually are debating what do probabilities actually mean? And what is an appropriate definition of what a probability is? Because we have a mathematical notion of probability, but that doesn't necessarily translate into a real-world notion of probability. Now, I'm going to leave that discussion aside. I might make an aside video about the interpretation of probability, but in this class, despite the limitations of this interpretation, we're going to adopt the frequentist interpretation of probability, which is interpreting probabilities as long-run frequencies of events. So in other words, if we were to repeat an experiment many times, and each of those repetitions were independent of the past, we would, the sample proportion of times we would see that an experiment occur would approach that probability. So here's kind of here's a chart that kind of illustrates this idea. We're going to have along the y-axis, the y-axis ranges from 0 to 1, and somewhere along here we have the probability of some event E. Ugh. Stop being uncooperative, tablet. Alright, so we have the probability of an event E. Okay? And along the x-axis, well, it's not really the x-axis this time, it will be the n-axis. And we're going to mark this axis off at integer values. 1, 2, 3, 4, and so on. And we are going to track p hat n, which is the sample proportion of times the event E occurs. And you remember how to compute sample proportions. But here's kind of the thing about what we're doing here. We are remembering the past. So you could imagine that we are flipping a coin, and we're tracking how many times we see heads in this experiment. And so the first time you flip it, you're going to have either 1 or 0 heads. And the second time, you're going to keep the result of that first flip, but then recompute your proportion for a sample size of 2. For the third time, you then flip the coin a third time, and you keep the previous 2 results, and then recompute the proportion using those previous 2 results, and also the third flip you just did, and so on. Keep doing this in a sequence. So what could possibly happen? So I'm going to put a little dashed line at the probability of E. According to the frequentist interpretation of probability, the probability is basically this long-run frequency where if you're tracking p hat n, you'll start out at like maybe 0 or 1, depending on whether the event happened on the first trial or not. And then you might track that it happens on the second trial, and the third trial, and the fourth trial, and so on. And what will happen is this line will get very, very close to the probability of E. And that's how frequentists think about probabilities, as a long-run proportion, as a limiting proportion. Now, there is an unfortunate thing about this interpretation, which is that actually in mathematical probability theory, that is not an assumption, that's a theorem. So this is not something that we assume is true, this is something we prove is true. So why are we assuming that something is true that we then prove is true? That seems like a circular reasoning, and it's unfortunate. But I'm going to leave those philosophical issues aside. Because at some level, my own personal belief is that all of those technical philosophical issues aside, at some level, it's almost a limitation of human language. And probability theory, despite our difficulty in coming up with a proper definition for it, is a very real phenomenon. So whatever the definition is, it matches this frequentist notion. I've actually got some R code here that you can look at. This function R is capable of generating random numbers, and set seed is sets what's known as a random seed, and make sure that when you're generating random numbers, they actually are going to come up with the exact same results the same time. So if you run this code, it will produce the exact same results, at least in principle. Different versions of software may cause different results, but whatever. So I set the sample size for my experiments. I conduct a number of flips. I cumulatively track the number of heads in these flips, and then I plot these sample proportions and also draw a line at the theoretical probability of that event. So this is the case when if you were to flip a coin, flip 15 times and keep a running proportion of how many times you saw heads. This is what it looks like. And you can kind of see it seems to be converging around 0.5. If we repeat this experiment, but this time when n is equal to 50, what we'll see is it kind of looks like it's getting even closer to something constant. And then if we were to repeat this again, but now the sample size is 500, it almost converges. It almost converges to the truth. Now, that said, with probabilities, it never means that you are guaranteed to see that many in any single sample. We did not say that. Which means that at the very end here, you're not actually at 1/2. You're pretty close to 1/2, but you're not at 1/2. But if you were to just keep going on like this, and it were in fact possible for you to continue forever, and God suddenly grants you the ability to live forever so long as you continue to flip this coin, at the end of eternity, you will have 1/2 of flip. Half of your flips will be 1/2. That's basically what we're saying. All right, so that's it for this video. Quite intense. Quite intense. It's probably giving you some idea that probability can get rather out of hand, at least in terms of computational complexity. But I've given you a number of useful examples and a number of useful techniques. The thing, though, is those techniques, like, they're useful now, and it's good for you to see them, but you always kind of have to adapt to individual problems. The next section is going back to the situation where you have a finite sample space we're going to talk about how you count elements from that sample space. This part is both fun and frustrating because it's fun because we get to talk about things like poker problems and gambling and stuff like that. But it's frustrating because counting is hard. Counting is really hard. And also, like, I would love it to give you a magic formula that solves every and all counting problems. And I will give you some formulas, but those are just tools that you kind of need to combine. And the combination of those tools, that's the hard part. And I can't really give you a general principle for that. Every counting problem is kind of its own thing. But enough of that. We're calling it for now. I will see you later in the future video on counting.
Let's move on now to the section on counting techniques. To start things off, let's suppose that we have a burger shop that we're going to call, just off the top of our head, Bob's Burgers. And they're offering 3 types of bread. We have white bread, rye bread, and sourdough. A burger can come with or without cheese. How many burgers are possible? Well, let's see. We have let's come up with some encoding for our possibilities. We have white bread, we have rye bread, and we have sourdough, and a burger can come with or without cheese. So we'll say we can have with cheese or we can have no cheese. All right, so given this encoding, what are the possible burgers that we could have? So we've got our possible burgers, and we could have a burger with white bread and cheese, a burger with rye bread and cheese, and a burger with sourdough and cheese, or a burger with white bread and no cheese, a burger with rye bread and no cheese, and a burger with sourdough and no cheese. So let's see, how many burgers is that? That's going to be 6 burgers. So that's the way to do it by hand, where you basically enumerate all the possibilities for how many burgers there are going to be. But the thing, though, is, that's only going to work for so long. You can enumerate stuff when it's possible to do, and then literally count how many possibilities there are. But there's also other ways to possibly represent what's going on here. For example, we could use what's known as a tree diagram. With the tree diagram, we're going to create a tree that visualizes the branching possibilities of our choices. So, for example, at the first node, we're going to choose the type of bread. So we have white, rye, and sourdough. And then at the second level of node, we decide whether we're going to have cheese or no cheese. So we have, for the upper branch, cheese, and for the lower branch, no cheese. And we're going to do this a few more times for the different types of bread that we could have chosen. And we've got cheese, no cheese, no cheese. And then we're going to count how many nodes there are on the endpoints. And the number of nodes on the endpoints will correspond to the number of possible choices. In this case, there are 6 nodes, so that means 6 possibilities. And of course, one thing that's nice about these types of tree diagrams is that we could allow for more flexibility in our possibilities, such as perhaps for some reason Bob has decided that he is not going to permit sourdough bread without cheese, in which case you just remove that possibility from the tree diagram. You remove that branch, in which case there would now be 5 nodes in the branch. So it's pretty general. There's also something that we can use called the product rule. Proposition 7, if there are n1 possibilities for choice 1, n2 possibilities for choice 2, all the way to nk possibilities for choice k, then the total number of possible combinations is going to be the product of the number of possible choices we can make at each point. So let's use the product rule to answer this question. According to the product rule, we could have 3 possible choices for the first node
and 2 possible choices for the second node. And thus, the total number of possibilities will be 3 times 2, which is equal to 6. All right, so we've seen so far 6 ways to basically answer this question. Now, let's move on some more. The Sandwich Shop Deluxe Deli offers 4 bread options, where we have white, sourdough, whole wheat, and rye, 5 meat options, turkey, ham, beef, chicken, or no meat, 6 cheese options, cheddar, white cheddar, Swiss American pepper jack, and no cheese, with or without lettuce, with or without tomatoes, with or without bacon, with or without mayonnaise, and with or without mustard. How many sandwiches are possible? Let's see. How many decisions do we have to make? First, we need to decide on our bread option. So we'll say that that's decision 1. So we'll say that in 1, there are 4 possible options. So 4. Then we can decide our meat options. And there's 5 meat options. We have 6 cheese options. So N3 will be 6. And then for the remaining options, it's all binary. So we've got with or without lettuce, so that means that N4 equals 2. With or without tomatoes, so N5 equals 2. With or without bacon, so N6 equals 2. With or without mayonnaise, so N7 equals 2. And with or without mustard, so N8 equals 2. Okay, so based off this, how many sandwiches are possible? Well, according to the product rule, we're just going to multiply all of those numbers together. So we've got 4 times 5 times 6 times 2 5 times. So we'll say 2 to the 5th power. So this, when you multiply all this out, you're going to end up with 3,840 possibilities for this sandwich shop. Okay, so moving on. Here's the thing. We are now very fully into the realm of combinatorics. Combinatorics is generally figuring out how many ways there are to do things, and or how many combinations there are of things, how large finite size sets are when they're generated with certain rules. And honestly, combinatorics is pretty hard. Like, for example, I find combinatorics rather challenging. I remember once when I was in a probability class, and I was in... excuse me. I was in office hours with a professor, and a fellow student of mine, we were discussing combinatorics, and a fellow student of mine was just like, is this what probability is, or statistics is? Because if it is, I don't know if I want to do this. And he was like, no, it's not. You just kind of have to do this. You have to learn this at some point, but it's not what the bulk of probability is. And I can understand why she said that, because it can get pretty painful. Here's the thing about combinatorics. What I'm about to do is give you some tools, some counting tools, for counting type problems that are often reappearing. But the thing is, every single combinatorics problem is its own thing. It's really hard to come up with general tools. Like what I'm coming up with here, there are certainly tools in the toolbox, things that you kind of look out for when you're solving combinatorics type problems, but you still need to think of each problem as its own thing. And for this section, I kind of have to come up with a number of examples and run through those examples to give you an idea of the thought process of combinatorics, but it's really hard to teach that thought process without examples, since I can't just give you an algorithm that will solve every single combinatorics problem. Every problem is its own beast, and you're pretty much forced to think very carefully about the process by which a single combination has been formed. Also, I should probably just mention, if we have... there's something that I didn't mention in these typed up notes, but I call this the sum rule. So if you're choosing from k disjoint sets, so sets each with we'll say n sub I possibilities, possible choices. At one stage, so you're going to pick one of these sets and an item from that set. Then, in this case, there's going to be the sum from I equals 1 to k n sub I possibilities. So in other words, if you need to choose an item from bin A or an item from bin B exclusively, then the number of ways you can make that decision is going to be the sum of the items in those two bins. Not a particularly difficult concept, but I'm going to just lay it out for you right now, just so that you are aware of that, and it's a valid approach to solving combinatorics problems. And I would say that the techniques that I'm about to show, like these will get you through. These are things that you look out for when solving combinatorics problems, but they probably won't take you all the way. All right, so when we're solving some problems, suppose that out of n possibilities we will be choosing k. We have two essential questions to answer. Are we choosing with or without replacement, and does order matter? Depending on our answer to those questions, we're going to have different solutions that are summarized below. Here, if the choice was where there's order and we're doing so with replacement, then the number of possible outcomes is n to the power k. Ordered without replacement, that's known as a permutation. And here is a formula for a permutation. N factorial, by the way. So n with an exclamation point means n factorial. And that is n times n minus 1 times n minus 2 times dot 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 times 3 times 2 times 1. That is n factorial. And by convention, 0 factorial equals 1. That's kind of strange. At least for me, when I first saw that 0 factorial equals 1, I found it rather surprising. But actually, it makes perfect sense for 0 factorial to equal 1. And I may explain why 0 factorial is 1 in a separate video. But we're just going to leave it at that. So that is what n factorial is. One way to think of what n factorial is, it's the number of ways to order n things. So it's the number of permutations of n things. Now, in this case, for ordered without replacement, we're also calling that a permutation. It's just a permutation of k things out of n. So suppose that we don't have replacement. So think about what replacement means. It means that replacement means that if you choose an option, you can choose it again. So you're allowed to choose it again. An example of ordered with replacement is a sequence of heads and tails in coin flips, where you may consider, possibly, you may not, but if you're looking at a string, there are different ways that heads and tails can manifest themselves in the string. And furthermore, if you get heads on the first flip, you're still allowed to get heads on the second flip. Whereas if you don't have replacement, you can get heads on the first flip, but you can't get heads on the second flip. So that would be without replacement. And order matters that means that the order in which you see an item in a sequence matters. So you're tracking that. So heads, heads, tails is different from heads, tails, heads. Whereas if order doesn't matter, then heads, heads, tails is essentially the same as heads, tails, heads, because you don't care about the ordering of the items. So that's what we mean by with or without replacement, or with or without order. Okay, so suppose that we're choosing items where order doesn't matter and we don't have replacement. In that situation, we're going to use the formula n choose k, which is n factorial divided by k factorial, or the product of k factorial n minus k factorial. I'm going to prove each one of these formulas in a second because I do believe that the proofs are enlightening on the combinatoric thought process. And the combinatoric thought process is something where you just kind of have to get exposed to it a lot in order to be able to think that way yourself. Finally, we have the situation where you're choosing with replacement, but order doesn't matter. In which case, you're going to have k plus n minus 1 choose n minus 1. Okay, so next up is the proofs or the justifications for each of these formulas. I'm going to prove this in a snaking fashion or a clockwise manner, because often the formula in this clockwise order from before is going to be used in the next proof. Okay, so let's get started. We're going to start by proving the formula in which case we have ordering, and we also have replacement. All right, so ordered with replacement. I'm going to zoom in because I'm going to need I'm going to need more space. All right, so we want to come up with the formula n to the power k. Well, all right, so we have k choices to make, and since we have replacement, we're going to use the product rule. The product rule is kind of the underlying rule that we can use for all of these. So starting out with the product rule, we have k decisions to make. I like to think of combinatoric problems where you are describing in a combinatoric problem how to construct an instance of an element of this set. And when you are thinking about how to construct an element, you construct a narrative for how to construct one of these elements, and you're counting how many ways there are to make the decisions along the way. And you're tracking how many decisions you need to make, and using the product rule the entire time. So we can think of, if we're doing ordering with replacement, we might have, for example, 3 spaces, and we need to fill up those spaces with elements. So we might have 2 possibilities for each space. So at the first space, we would have 2 possibilities, and at the second space, we'd have 2 possibilities, and at the third space, we have 2 possibilities, and we care about the ordering and we care about the ordering of what we put in these spaces. So the number of possibilities for filling up these 3 spaces would be 2 to the power 3, because we're going to multiply, and we have to make a decision at each space, and when you have to make a decision at each space, you multiply the possible number of decisions that you needed to make. So generalizing this idea, we need to make a decision in the first slot, the second slot, the third slot, all the way to the kth slot. And for each of these, slots, there were n possible things to choose from, because we're not removing options as we go through our sequence of k slots. So then, by using the product rule, according to the product rule, we end up having to multiply. We end up having to multiply each of our possibilities, or each of the possible options we can make at each slot. But since all of those are the same,
since all of those are the same number, you end up with multiplying n k times, which is n to the power k. So that gives us the first formula. The next formula we need to come up with is ordering without replacement, which gives us the number of permutations. Okay, so we now next have, oops, that is definitely not what I wanted. All right, so next up we have ordered without replacement. I'm going to go back for a second, and I have in my head prototype problems for each of these four scenarios. So ordering with replacement is like determining how many strings of heads and tails there are in a string of flips. Because the ordering in that situation would matter because because heads tails is not the same as tails heads in a string. And you have replacement because if you get heads on the first flip, you can get heads again on the second flip. Ordering without replacement, to me, my prototype problem for that is forming a list. Because the item that you put at the top of the list cannot be chosen for the next item in the list. So you are removing items as you go through this list, and maybe it's like a times top 100 people or 100 people for the year list where the ordering matters, and there's certainly more people than 100. So they might have this larger master list of people they would consider to be candidates on their top 100 list. So you're going to choose people to be in certain slots on this list, and when you choose a person to be on the list, you can't pick them again. So that's kind of my prototype problem for ordered without replacement. For not ordered and with replacement, this is like poker problems, because when you draw cards from a deck of cards, you are allowed to reorder the cards in your hand, so there is no ordering. But once you draw a card, you cannot draw it again, so there isn't replacement. And for the final situation, my prototype problem here is choosing a dozen donuts when you have so many flavors of donuts. Because you are allowed to reorder the donuts in the box, and in principle, the donut shop has this almost infinite list for the number of or an almost infinite supply of donuts in this imaginary donut shop. So there is replacement when you choose a flavor. Like when you choose a flavor, you're allowed to choose as many donuts of that flavor as you want. So replacement is not an issue. All right, so you do have in fact replacement. Those are my prototype problems, and those are good to keep in mind when we're going through and trying to think about what formulas we should have and how we're going to prove these formulas. And additionally, it's kind of good to have these prototype problems in your mind when you're trying to solve combinatoric problems yourself. All right, so next up, getting back to these proofs, we need to show the formula for ordering without replacement. So I had that formula for n factorial. All right, so how many ways are there to form a list of k things when you have n possibilities? So we would need to pick the first item in the list, and the number of ways we could pick the first item in the list is n. Then we need to pick so there are n ways to pick the first item in the list. Then we need to pick the second item in the list. So there are going to be n minus 1 ways to pick the second. The reason why is that whatever we chose to be our first element in the list cannot be chosen again to be the second element. So we have n minus 1 ways to fill the second item. Then we have n minus 2 ways to pick the third item, because now, in addition to not being able to pick what we chose for the first
item in the list, we also can't pick what we chose for the second item of the list. So we're going to have n minus 2 choices now. So n minus 2 ways for the second item. No, not the second, the third. And we just continue on with this process until we reach the kth slot. And there will be, for the kth item in the list, there will be n minus k minus 1 ways to pick that item, which, by the way, is equal to n minus k plus 1. Right? So n minus k plus 1 ways to pick the kth item. So then we're going to use the product rule and by the product rule we multiply all of these numbers together. So we're going to get so the number of possibilities is going to be n times n minus 1 times ... times n minus k minus 1. And if we wanted to, we could stop there. This is, in fact, the formula. But thing, though, is it's sometimes better to... We might prefer a more compact formula. So we might say instead that we have n minus 1, n minus 2, ... and then we have n minus k plus 1. And then we could keep going multiplying and say we're going to multiply by n minus k, and still decreasing down. But we've now multiplied by n minus k, and if we're going to multiply by n minus k, we now need to divide by n minus k in order to keep things balanced. And then we're going to multiply by n minus k minus 1. Okay, so we're going to need to divide by n minus k minus 1. And we're going to keep going with this process on both the top and the bottom until we multiply 3, 2, and 1. And what I've actually written down in doing this, the top can be recognized. So the top part of this fraction, you may recognize that as being... I don't want that color. You may recognize the top part as being n factorial, and the bottom part of the fraction, the denominator, as being n minus k factorial. Hence, producing the formula. This will produce the formula n factorial over n minus k factorial, which we may also just call p and k. And that gives us our second formula. Okay. Next one. What we now need to do is figure out how many ways there are to choose items that are not ordered and there is no replacement. This gives us the formula that is often referred to in English as n choose k. So the proof for this one is actually quite tricky, where you start out by assuming that you know how to do it, and then you recover the formula in the end, where you pretend that you know the formula. And after you pretend that you know the formula, you then figure out something that you already know, which in this case is the number of permutations of a list. And once you have the number of permutations in the list, you're able to recover the formula that you pretended that you knew, but you actually didn't. All right, so that's rather convoluted. Let's get started with showing how we can get this formula. So the proof, again, is kind of weird. It's a really weird one, but all of a sudden, at the end, we're going to have the result that we wanted.
So we have no order, and we don't have replacement. I keep touching that. All right. I keep touching it. All right, so not ordered without replacement. So suppose n choose k is the number of ways to do this. So we know the number of ways to choose items when we don't care about order and we don't care about replacement, and the number of ways to do so is n choose k. Okay? Bear with me. I now want to know how many ways are there going to be to pick k items out of n when replacement doesn't matter. So as opposed to doing so in order doesn't matter, which we're assuming that we know. That is what I want to do. What I want to do is calculate P and K, or the number of k-length permutations of n objects. Okay? So, I want to compute that, which, by the way, we have already computed. That formula is actually already known to us. It's up here. But we're going to suggest that there is an alternative way to calculate this if somehow you knew the number of ways to pick k items out of n without order. So how would we do this? Let's think about how we would construct a single permutation if what we had to do was pick items without order first. So our first step, if we were to attempt to form a single list of k items out of n, when we can pick items without ordering them, the first thing we would do is pick the number of items, or pick what items will appear on the list without ordering them first. So our first step in our process is to pick objects when order doesn't matter. So you've decided basically what's going to appear on the list, you just don't know in what slots it will appear. And supposedly, we know how to do so. There's n choose k ways to do so. So there are n choose k ways to pick the items that will appear on our list without ordering the items. So first, we pick a set of items that will appear on the list. The next step then is to order those items. So the second step is to order the k objects. So how do we order the k objects? Well, we pick the first. We pick one of the objects that we have selected to be the first item on the list. There's k ways to do that. Then we pick another one of the objects that we haven't picked yet to be the second item on the list. There's k minus one ways to do that. Keep doing so until you run out of items. So there are k factorial ways to order the items. Oops. Oh, darn it. So there's k minus 1 ways to order the items. Going back to where I was. Or k factorial ways to order. So now we're going to use the product rule and say that the number of ways to pick items to appear on our list is going to be the number of decisions we have to make in step 1, which is the number of ways to pick the items to appear on the list. There's n choose k ways to do that. And then multiply that with the number of ways to order the items. So there will be k factorial. So that's the number of ways to form permutations, but we also know that the number of ways to get permutations from what we did before is n factorial divided by n minus k factorial. Okay, well, what we actually were interested in this whole time was calculating this number that I just highlighted in red. That's the number we actually want. Well, how can we get that? With division. Because now we have an algebraic relationship with which we can solve to get n choose k. And it follows that n choose k is equal to n factorial divided by k factorial times n minus k factorial. And we're done. We computed what we actually wanted to compute. So that was a little odd. That was a little strange. Here's some more ways to kind of justify this formula that we ended up with. So the number of permutations is larger than the number of combinations because when you are sensitive to order, you're going to end up with many more possibilities than if you're not sensitive to order. So as a result, you need to divide out by a factor that effectively removes all of the orderings that contain the same items that just in a different arrangement in order to get the combinations. And when it comes to computation, like let's say for example 5 choose 3. This formula, for me at least, when I was taking this class, the way I think of it is I have 5 factorial on the bottom, and on the bottom I have 5 factorial on the top, and on the bottom I'm going to have 3 factorial and whatever it takes to get to, and the other number such that 3 and the other number adds up to 5. So I'm going to have 5 factorial divided by 3 factorial times 2 factorial. Okay? So that's a way. So the formula is actually not that hard to remember because it's like, okay, 10 choose 7. That's going to be 10 factorial divided by, well, we've got 7 factorial down there, and we've also got something that adds up to 10. Okay, 3 factorial. So 10 factorial divided by 7 factorial times 3 factorial. So the formula itself is not that hard to remember, but you now have it. Okay, continuing on. So that was our third formula that I promised that we were going to prove. So now we have one last formula to prove. And that formula is, let's see how much space we got. Hopefully we've got enough. So the last formula we have not ordered. And we have replacement. So this is the donut shop situation. Okay. So the donut shop situation. Here's, like, this proof is, again, also rather tricky. Combinatorics often requires tricks, honestly. That's one reason why combinatorics is rather painful. It feels like there are rather few unifying principles in combinatorics. I know that there are some, but it doesn't really seem that there's all that many. So here's what we're going to do to solve this one. Let's suppose that we're in a donut shop and we're going to choose
say 5 donuts of 3 flavors. How could we possibly do that? We don't care about the ordering of the donuts because you put it in the box and no one's going to ask in what order the donuts were when you come home. So what I like to do is imagine, okay, whatever we're going to do, we're always going to arrange the donuts in the box, right? So whatever arrangement they originally were, we're going to put them into a fixed arrangement where we have one flavor first, one flavor second, and one flavor third. So what we could end up doing to form a single box, after we say that we're going to rearrange them at the very end, is we're going to put down all the donuts of a single flavor, and we know that the donut that comes first is going to be of a certain flavor, but we're also going to put dividers in our box to separate flavors. So the second flavor will come after the first divider, and the third flavor will come after the second divider. And it is also possible to not have a donut of certain flavors. So, for example, if we wanted a box of only the third flavor, we put a divider in the first position, a divider in the second position, and then put donuts in all the remaining positions. And with this encoding, I have now encoded one of the boxes of 5 donuts. This is a box where you have only the third flavor, and you can imagine what a box consisting of only the second flavor would look like. So you'd have a divider at the beginning and a divider at the end, and then in between you have your donuts. So this is a box that has only donuts of the second flavor. And maybe play around with this encoding of donut boxes. But once we have this encoding, it is now possible to calculate how many boxes we can achieve. Because what we can do is say how many ways are there to pick positions for dividers and positions for donuts. How many ways are there to do that? Well, we're going to have, if we have 3 flavors, we're going to have 2 dividers. And if we have 5 donuts, we're going to have positions for 5 donuts. So we're going to end up with 7 positions that we need to fill up. We could just pick 2 of the 7 positions to contain dividers, and the remaining positions will contain donuts. So let's see, we could potentially pick numbers. We could assign a number to each of the positions. So we have positions 1, 2, 3, 4, 5, 6, 7, and we pick numbers that represent positions that will contain dividers. So in this case, numbers 4 and 6 represent positions 4 and 6. So those will be, so if we pick 4 and 6, which by the way is the same as picking 6 and 4 to contain dividers. So in other words, we don't care on the ordering of the numbers that we end up picking. Once we pick that, we now know what our box of donuts is going to be because we've picked the positions for the dividers, and therefore every other position will contain donuts. Okay? All right then. So if that is the case, how many boxes of donuts are there going to be? So in this case, the number of possibilities, which is n, in this scenario is equal to 3. And out of that n, we're going to be choosing k possibilities. Or we're going to be choosing k items or k donuts. So for this problem, k is equal to 5. Okay? So, how many ways were there to make this decision? Well, it turns out there were 5 plus 3 minus 1, choose 3 minus 1 ways to pick donuts in this fashion. Because we end up picking the, or in other words, this is 7 choose 2. Because we had 7 slots and we picked 2 of those slots to contain dividers and the rest of the slots contain donuts, hence we get the number of donuts. Alright, so let's generalize this idea. So if we have n possibilities, we're going to have n minus 1 plus k slots, because we're going to have n minus 1 dividers and then also the k slots for the k things that we're going to end up picking. So in general, so let's see. So we have k plus n minus 1 slots to fill with n minus 1 dividers, which we call which we're going to call the bar, remaining slots so the remaining slots contain items. So we need to pick the positions. Let's see. Yeah. So pick positions for the dividers. And order doesn't matter. So, since order doesn't matter, there are going to be n plus... I like a different ordering. There are going to be k plus n minus 1. Choose n minus 1 ways to do so. And we're done. You end up with the formula. And we're done. So that was exhausting. This is rather tricky types of mathematics that honestly it's frustrating because it often just requires knowing special tricks in order to solve a certain problem. It just feels like all you're doing is coming up with a longer and longer list of tricks, and it doesn't really feel like there's much of a unifying principle to them. At least to me personally. It seems also to me like there are some people out there, some really smart mathematicians, for which this type of thinking just for some reason just clicks, and they are able to see an underlying principle. I don't see it often, but I often know enough combinatorics. Like this amount of combinatorics will get you very far in life, in your statistics life, that is. You don't really need to know that much more than this. All right, so those were complicated proofs. Now we're going to go through a series of examples to show how these techniques can be applied. So suppose we're going to roll 2 6-sided dice, and we assume each outcome is equally likely, and we're going to say that the dice are different colors. So if the red dice has a 6 and the blue dice has a 1, that's different from the red dice having a 1 and the blue dice having a 6. Those are two different outcomes. How many possible outcomes are there? And what about the situation when there's 3 6-sided die? So we're going to first answer problem that I'm going to call 1 and the problem that I'm going to call 2. All right. So the answer to 1, order matters, and we're doing so with replacement because if we roll a 1 for the red dice, we're still allowed to roll a 1 for the blue dice. So we end up with, there are 6 possibilities and we're choosing 2 of them, so we get 36. All right. For the next option, well, it's just the same thing. Now we're just choosing 3 instead of 2. So this is going to be 216. So this is a situation where order matters because the dice are different colors, and there is replacement because dice don't care what the other dice rolled.
All right. Next example. A high school has 27 boys playing men's basketball. In basketball, there are 5 positions: point guard, shooting guard, small forward, power forward, and center. Each assignment of player to position is unique. How many teams can then be formed? This is a permutation type problem. So here, order matters because there's different positions. And each of those positions are distinct. But there is a replacement because a person playing point guard cannot also be center. So position doesn't matter. Oh, no, position matters. Or order matters. No, sorry. No replacement. No replacement. I get it eventually. All right, so no replacement. So that means we're going to be using that second formula in the clock. So we got P. There's 27 possibilities. We're going to order 5 of them. So that's going to be 27 factorial divided by 27 minus 5 factorial, which is 27 factorial over 22 factorial, which also can be written as, maybe more simply and to the point, 27 times 26 times 25 times 24 times 23. That's almost easier than remembering the formula, just remembering that you decrement that many times. And this multiplies out to 9,687,600 potential teams. Okay. Example 19. When playing poker, players draw 5 cards from a 52-card deck. Every card is distinct, but the order of the draw does not matter. You are allowed to reorder the cards in your hand. How many hands are possible? In this situation, because you're allowed to reorder, order doesn't matter. And also in addition to ordering not mattering, there is no replacement, because if you draw an ace, you can't. If you draw an ace of spades, you are not allowed to draw an ace of spades again. So no replacement. Okay. So let's see. If that's the case, then we're going to use that third formula in the clock. We have 52 possibilities for 52 cards. We're going to choose 5 of them when we draw cards. And that's going to be 52 factorial divided by 5 factorial times 47 factorial, which is equal to 52 times 51 times 50 times 49 times 48 divided by 5 times 4 times 3 times 2 times 1. Okay, and we don't care about the 1 because it's times 1. That doesn't really do anything. We can do some cancellation, like for example, the 50 and the 5 cancel down to a 10. The 4, 3, and 2, those multiply the 24, so that reduces with the 48, rendering it a 2. So this is equal to 52 times 51 times 10 times 49 times 2, which you then go to your calculator, and it will give you 2,598,960 poker hands. Now, R can do a lot of these calculations. So for example 16, you can just say, what is 6 to the power 2? And it'll tell you the 36. And for 6 to the power 3, that's 216. R does have a factorial function. Now, be careful with some of these functions because you might end up with integer overflow. You might end up with numbers that are so large that the computer cannot handle them. So I would not just blindly use these functions because it is possible for these numbers to explode very rapidly, in which case your calculations will end up being wrong. But we do have a factorial function and we do have a choose function. So here's example 17 and here's example 18. Or is that numbering might be wrong. Yeah, that numbering's wrong. My apologies. So I guess at some point when I wrote this R code, or when I wrote these notes, I must have deleted an example a long time ago, but I did not change the comments in the R code. This is why I need to be very careful with comments. Comments expire. Eventually they turn bad. All right. And you know what's worse than no comment? A misleading comment. That's even worse. All right. So example 20. You want to choose a dozen donuts from a donut shop. There are 8 different kinds of donuts. How many boxes of a dozen donuts are possible? Well, okay. So in this situation, we are choosing 12 donuts, and there are 8 possibilities. So using that fourth formula in the clock, we have 12 plus 8 minus 1, choose 8 minus 1 possibilities, which is going to be 19, choose 7, which is equal to 19 factorial divided by 7 factorial times 12 factorial, which is equal to 19 times 18 times 17 times 16 times 15 times 14 times 13 divided by 7 times 6 times 5 times 4 times 3 times 2 times 1. All right. And let's do some cancellation to help make our life a little bit easier. Let's see. The 7 and the 2 are going to cancel with the 14. We've got, what else? 4 and 16 will reduce the 16 down to 4. The 5 and the 3 will cancel out the 15. And the 6 cancels out with the 18, reducing it to 3. So in the end, we're going to have, this is 19 times 17 times 13 times 3 times 4. And then you go to your calculator and ask what that is, and you'll get 50,388 potential boxes of donuts from this donut shop. Okay, and here is some R code that will also compute that quantity. Okay, so let's do some classic poker problems. Once people introduce combinatorics, it's like the next thing you have to talk about are poker problems, because poker problems are fun. Because poker is fun. It's fun to talk about poker. Now that said, there is one potential with talking about poker problems is that unfortunately not everyone is familiar with the poker deck, or the standard playing card deck as it's known in the English-speaking world, which for what it's worth, the standard deck is technically the French deck, and different European countries have different traditional playing card decks. So, like for example, my advisor, Lajos Horvat, the traditional deck that's used in Hungary is not the French deck. So he doesn't like, personally, poker problems because there's something that, like, they talk about a deck and he's not very familiar with that deck and it just goes against his intuition. Whereas I myself, I grew up with this deck. I grew up in America, so I'm very familiar with what is inside of a playing card deck. That said, if you're like an international student or something like that, here is a description of what is inside of a standard playing card deck, or a French deck, the deck that's used in the English-speaking world and often used in these probability textbooks, because most of these probability authors are most of the authors of these probability books, they may be in America, but they're certainly speaking English, so they're probably using this deck. So, and here's some additional notation for this is poker notation to describe what goes inside, what cards are inside of a deck.
All right. So, but basically, you've got 4 suites and 13 possible faces. All right. So for a total of 52 possible cards, you should know how to do that by now because how do you form a single card? You first pick a suit. There's 4 suits possible. Then pick a face value. There's 13 faces. So 13 times 4 will be 52. All right. So you've learned something today. Example 21. A poker hand is 4 of a kind. If 4 cards have the same face value, how many 4 of a kind hands exist? How are we going to solve this problem? Well, the trick that we're going to use, again, with these not just poker problems, but most combinatoric problems, what I suggest that you do is come up with a narrative, like I just did right now for figuring out how many cards there are in a deck. Come up with a narrative for forming a single combination. And then once you have that narrative, figure out how many choices there were to make at each junction, and multiply them together with the power rule, and you'll get what you need. So, first thing we're going to do to form a 4 of a kind hand is we're going to decide what card face value will be the 4 of a kind card. So first we're going to pick the 4 of a kind card. So we're going to say, for example, there are going to be 4 kings in this hand, or 4 2s, or 4 10s, something like that. So we need to pick a face value, and there are 13 face values, to be the 4 of a kind part. All right, so there are 13 ways to pick the face value. Then we need to pick the remaining card because a poker hand has 5 cards. We have picked 4 of those cards. If we decided that we were going to use the ace, ace for the 4 of a kind card, then we've automatically got the ace of spades, the ace of hearts, the ace of diamonds, and the ace of clubs. That's 4 cards. Now we need to pick the remaining card. If we picked ace, then we cannot pick the ace face value again. So in fact, in that 52 card deck, we have taken out 4 of the cards and put them in our hand, leaving 48 cards remaining in our deck. So that means that we have 48 cards to be the potential 5th card. So pick the 5th card. So 13 times 48, you multiply those two numbers together to get 624 poker hands with 4 of a kind. Okay. Next up, a poker hand is considered full house if 2 cards have the same face value and 3 different cards have another common face value. How many full house hands exist? Let me just list out for you an example of a full house hand. You could have, let's say, the 4 of diamonds, the 4 of spades, so the 4 of spades, and the 4 of hearts. And so that's 3 cards with a common face value, and then we need 2 cards with another face value. We can't pick 4 for this. So we're going to pick, let's say, kings. So we'll have the king of clubs and the king of diamonds. So this would be a full house hand. So let's see. How can we form a full house hand in general? Well, we're going to have 2 different face values in our full house hand. But one face value will be the more numerous face value, the 3 of a kind, and the other face value will be the 2 of a kind. So what I suggest we do is first pick the card that will be the 3 of a kind card. So pick the card that will be the 3 of a kind card. So pick the 3 of a kind. Face value. And there's 13 face values for this choice. So there's 13 ways to make that choice. Then we need to pick the suits because we picked, for example, 4, but there are 4 suits from which we can choose, and we need to pick 3 of them. So now we need to pick the suits. And order doesn't matter in this situation. We don't care about the ordering of the suits, we just need to pick them. So we need to pick exactly 3 suits for all those 3 cards. And since order doesn't matter for this choice, we have 4 choose 3 ways to pick the suits. And 4 choose 3 evaluates to 4. Which is not surprising. Alternatively, and by the way, this thought process is quite useful. Instead of picking the 3 faces we're going to include, we could have picked the 1 face. No, not face. I am so sorry. For the life of me, I can't keep my words straight. I'm always doing this. So not face, but suits. Instead of picking the 3 suits we're going to include, we could pick the 1 suit we're going to exclude. And there's 4 ways to pick the suit we're going to skip. All right, so there's a useful trick to keep in mind. Next up, we need to pick the 2 of a kind card. We need to pick the 2 of a kind face value. So we can't pick what we chose before. For example, we couldn't choose 4 again. So we need to pick one of the 12 remaining face values. So there's 12 ways to make this choice. And then after we pick the face of the 2 of a kind card, we now need to pick the suits. So we need to pick 2 suits. And again, we need to do so where we don't have replacement, but order doesn't matter. You can't have replacement because there are not 2 King of Hearts in the deck. There's only 1 King of Hearts. So you pick... you can't pick the same suit twice. Of the 4 suits, we need to choose 2 of them to include. So that's going to be 4 choose 2. 4 choose 2 evaluates to 6. So in the end, this is going to equal 13 times 12 times 6 times 4, which is equal to 3,744 full house hands. All right. And here's some R code that's computing those quantities. Notice, by the way, this is a useful trick to be aware of when using R. Notice that I wrapped the entire expression in parentheses. If I didn't put the parentheses there, nothing would have printed. But when I wrap an entire expression in parentheses, when I'm doing some variable assignment, the value of the variable that I just assigned gets printed, which is really nice. So if you have removed these parentheses, the 624 would not have been printed. But since I put the parentheses there, it in addition to doing the assignment done here, it prints the value of the variable. That's a nice trick. All right, so example 23. A flush is a poker hand where all cards belong to the same suit. How many flush hands exist, including what's called a straight flush? A straight flush is a flush where the cards are also, where you can order the cards so that they're in sequence. Poker actually has a number of sequences, but for example, a hand where all the cards are spades and the cards are 5, 6, 7, 8, 9, that is a straight flush since they're also since you can order them. Right? And a straight flush is considered a different kind of hand in poker. That's a straight flush is in fact the best possible poker hand. So we actually should be accounting for straight flushes because generally when people say flush, they are not including straight flush. But we're just going to include straight flushes for now. We're going to allow that possibility. So for a flush hand, we're going to... So in a flush hand, all the cards have the same suit. There are 4 possible suits. So the first thing we need to do
is pick the suit. And there are 4 ways to pick the suit. After we pick the suit, we need to pick the face values. So there are 13 possible face values. We need to pick 5 of them to be in our hand. So once you pick one face value, you cannot pick it again because there are no 2 king of spades, for example. So there are 13 face values, and we're going to choose 5 of them. We don't care about the ordering, and we're going to do so without replacement. So you multiply those 2 numbers together. This is going to be 4 times 1,287. That's what that 13 choose 5 evaluates to. And this is going to equal 5,148. But this is also including the straight flush hands. In the next problem, I'm going to show you how we could potentially remove the straight flush hands, because I'm actually going to ask that we do in fact remove them. So a straight in poker is where cards can be arranged in sequence. So for example, we have 5 of spades, 6 of clubs, 7 of clubs, 8 of hearts, 9 of hearts. So this is a straight, and the suit doesn't matter for a straight unless it's a straight flush. If it's a straight flush, the suit must be the same because it's also a flush. So a straight flush is both a straight and a flush. So it is a flush with all cards. I should change that wording. It is a straight. It is a straight with all cards belonging to the same suit. And it is also the best possible poker hand. Hold on. Okay, good. All right. How many straight flush hands exist? We're going to compute that number now. How many straight flushes exist? So to get a straight flush, so let's start some separations. So first thing we're going to do is compute the straight flush. All right. So, excuse me. Here, by the way, is the ordering of poker hands, because poker face values have a ranking. We have ace, 2, 3, 4, 5, 6, 7, 8, 9, and I'm going to write X for 10, the Roman numeral X. Then we have Jack, Queen, King, and also Ace again, because Ace can be both low and high. And in fact, the best literal possible poker hand is 10, Jack, Queen, King, Ace, all of the same suit. That is the best straight flush. Okay. So for the flush part, we need to figure out how many ways there are for the flush part and how many ways there are to get the straight part. So there are 4 ways to pick the flush part, the part where you have the same suit. So we're going to pick the suit for the flush part, and then we have the straight part. And the straight part, for that, what I would recommend you do is think about how many ways there are to pick the first card. So pick the first card of the straight. Because if you know that the first card, or the lowest card of the straight, is ace, since there are 5 cards in hand, that means that the other 4 cards are 2, 3, 4, 5. Right? So how many ways are there to pick the lowest card in the straight? So let's see, we got 1, 2, 3, 4, 5, 6, 5, 6, 7, 8, 9, 10. Well, what do you know? Because the moment you get to 10, the straight hand would be 10, Jack, Queen, King, Ace, and there is no straight that starts with Jack, because you would not be able to get the 5th card, since you can't circle around back to 2. So
So that means that there's 10 ways to pick the lowest card in the straight. So that means that the number of straight flush hands is going to be 4 times 10, which equals 40. All right, and I asked also how many straights are possible. But this time I'm not including straight flush because straight flush is considered different. Well, the first thing we're going to do is pick the lowest card. Like we did above. And then we're going to pick the suits. So pick the suits of the cards. So we decided that there are 10 ways to pick the first card to pick the first card of the straight. And now to pick the suits. Well, if I decide that the first card, let's say the ace, is going to be clubs, and then I pick the next card, which is going to be a 2, I can still pick clubs again. Because I took out the ace of clubs, but I didn't take out the 2 of clubs, so I can still pick clubs for that second card. So, and I can still pick clubs for the third card, and so on. So basically, I do have replacement, but order does matter, because picking the first card to be the ace of clubs and the second card to be the 2 of hearts is different from the first card being the ace of hearts and the second card being the 2 of clubs. Those are 2 different hands. So order does matter, and also you're doing so with replacement. There are 4 possibilities. We need to pick 5 of them. So this will be 4 to the power 5. The thing, though, is once I've done this, I am including picking the first card to be hearts, the second card to be hearts, the third card to be hearts, the fourth card to be hearts, and the fifth card to be hearts. That's a straight flush. I don't want to include straight flushes. So how am I going to remove the straight flushes? I'm going to subtract them out. So this is straight flushes. So just remove them. Remove them from the calculation. Subtract them out. And you no longer need to worry about them anymore. This is basically, remember that sum rule that I very briefly mentioned? This is basically that sum rule, right? Where you say the total number of straight flush, number of straights including flushes is going to be the number of straight flush and straight non-flush hands. So you add those together, which means you can do some algebra to get subtraction too. Anyway, in the end, you calculate this and you get 10,200 straight hands, excluding the straight flush. Okay, we are almost done with this section. We've had a long discussion about counting, and I haven't really said anything about how what this has to do with probability. Well, this entire section was devoted to the case that you may have thought was the easy case, where you have a set where your sample space has finite size. Your sample space has finite size, and you decide that every element in that sample space is equally likely. And you may have thought this is the easy case, because in that situation, it's actually rather easy to compute probabilities. You can assign a very natural probability measure. The probability of any event A, which is a subset of this sample space, will be the number of elements in that set A, or in that event A, divided by the size of the sample space. Which is a very nice natural probability measure. But here's the thing, though. You need to compute then, using these counting techniques, the size of the sample space and the size of your set A. And that's actually tricky, because now you need to use these counting techniques, and I personally don't think the counting techniques are all that easy. All right, so based off of this, once we have this natural probability measure, we can use counting techniques if we need to compute probabilities. So we're going to use this to compute the probability of the poker hands that we were considering above. So the size of the sample space consists of possible poker hands. We say that each of those poker hands are equally likely. We do not care about the ordering of poker hands. So there's going to be 52, choose 5 such poker hands, which is going to be 2,598,960 possible poker hands. All right, so I want to compute the probability of each of the poker hands that we saw in the previous examples. So for example 21, this was the 4 of a kind. So the probability of a 4 of a kind hand is going to be the number of 4 of a kind hands, which we computed to be 624, divided by the size of the sample space, which is 2,598,960 poker hands, which is going to be approximately 0.0002. For example 22, the probability of getting a full house is going to be, let's see. So probability of full house is going to be 3,744 divided by 2,598,960, the number of full house hands divided by the total number of possible poker hands. This is approximately 0.0014. Next up, so for example 23. So for example 23, we're going to compute the probability of our so-called flush hand, a flush that isn't actually that includes straight flush. So just the suit is the same. How many? So there were 5,148 such hands possible. We're going to divide that by the size of the sample space, which is that 2 million-ish number. And that's going to be approximately 0.002. And now for example 24, the probability of a straight flush. That's going to be there were 40 straight flush hands divided by the size of the sample space. This is going to be approximately 0.00002. Really, really, really small. And the probability of a straight, so that's excluding the straight flush, is going to be 10,200 divided by the size of the sample space, which is approximately 0.004. There's always kind of this question of which is more likely, a flush or a straight. Turns out the straight is twice as likely as the flush, which to me is a little surprising. It feels intuitively like the straight is harder, but it's actually not. And that's a common trait of probability. It defies what you feel like should be true. All right, so that's it for this section. And in the next section, we're going to talk about conditional probability. So I will see you then. Somewhere using the idea of independence. You can almost find it anywhere if you look hard enough. So independence is an extremely important idea in probability. I've heard some people say that independence is what keeps probability as a mathematical theory from just being a subset of analysis. So we're going to talk about independence. If you come away from this lecture come away from this class, maybe more appropriately, not knowing what independence is, then that's bad. That's really bad. You must understand independence because it is used everywhere. It's one of the most important ideas in probability theory. So, two events, A and B, are said to be independent if the probability of A given B is the probability of A. So, in some sense, the information about the event B gives no information about whether A has happened, since the probability of A knowing that B happened does not change. So, first off, I've said only that the probability of A given B is the probability of A. What about the probability of B given A? And before I proceed, I should probably make a quick note saying I'm going to assume that
A and B are events that have probabilities on their own that are not necessarily zero, just because it's easier mathematically to assume that their probabilities are not zero, and you kind of have to treat the case where they are events with probability zero as a separate thing. But honestly, for the most part, you get the information that you need with just pretending that, just ignoring the chance that they have probability zero. Okay, so all right then, let's compute the probability of B given A. It seems like what should be the case is that if A is independent of B, then B should be independent of A as well. And in fact, that turns out to be the case, because we compute the probability of B given A, and that's going to be the probability of A and B divided by the probability of A. And we then say that the numerator is equal to the probability of A given B times the probability of B divided by the probability of A. By the way, if you're not recognizing this part, recalling back to the previous lecture, this is a Bayes' theorem prototype. Ugh, all right, that's some bad handwriting up there. I cannot let that go. I know that in some of these videos, my handwriting isn't great, but I cannot let that go. So this is a Bayes' theorem prototype, in that you're pretty much one step away from getting Bayes' theorem. All you would need to do at this point is apply the law of total probability to the denominator down here in order to get Bayes' theorem. But anyway, that aside, all right, that was a distraction. We now say that this is the probability of A given B times the probability of B divided by the probability of A, but we now know that the probability of A given B, because A is independent of B, that's going to be the probability of A. So this is the probability of A times the probability of B divided by the probability of B. You can probability of A, sorry, and you can probably see why we're assuming that these events don't have zero probability, because we could end up with division by zero. So we're going to cancel those out because they appear in the numerator and the denominator, and we get the probability of B in the end. Okay, all right. So that shows what we wanted to show. So this implies that if A is independent of B, so if A is independent of B, that's going to imply that B is independent of A, and vice versa. All right. It seems that it would seem to be the case that if A is independent of B, and so heuristically, that knowing whether B happened gives you no information about whether A happened. It should also be true for the complement of A. So knowing that B happened should not tell you whether A didn't happen either. So this does in fact turn out to be the case, because we compute the probability of A complement given B, and that's going to be the probability of A complement given B. We know from the previous section, this is 1 minus the probability of A given B, and the probability of A given B is going to be the probability of A, so this is 1 minus the probability of A, which we know from section 2 is equal to the probability of A complement. So that means that the complement of A is also independent of B. So there is an immediate consequence of this definition, which is that the probability of A intersected with B is equal to the probability of A times the probability of B. You can see that because you could potentially say that, like you would start out before saying the probability of A, that this is the probability of A given B. But since A is independent of B, that's just going to be the probability of A. So that means that the probability of intersections turns into the product of probabilities. And
not only is this a consequence of how I've defined the definition. Ooh, I misspelled definition. Not only is this a consequence of how I defined independence of events, this is actually taken in later courses and higher level probability courses or courses devoted to probability as the definition of independence. Because the two are essentially equivalent. And furthermore, what I've highlighted in blue here, it's used even more frequently, and also it's you have this issue of zero probability events, and we don't have that issue here because there's no division taking place. Okay, students often want to, like, I've been encouraging students to think about probabilities and sets and events in terms of Venn diagrams. And is it possible to get a Venn diagram graphically representing independence? It is, although it's kind of hard and honestly not that enlightening. I'm going to show it to you anyway, though. First off, this is not what independence is. This is not a picture of independence. We have A, we have B, and we have our sample space. That is not independence. This is disjointedness. And two events that are disjoint and have non-zero probability are certainly not independent of each other, because if you knew that one of those two events happened, you know that the other one didn't. So disjointedness is not the same thing. In fact, it's almost the opposite thing, or implies non-independence. So disjointedness is not independence. It's almost the opposite. Okay, so I'm promising you to show what independence kind of looks like as a Venn diagram. I can kind of torture a Venn diagram. So what I do is, I'm going to need to zoom in a lot for this. So to attempt to draw two sets that are independent of each other, I draw the sample space as a square. I divide it up into fourths. And then I'm going to give the set A the upper left corner. Nothing special about that particular corner. It just needs to be a corner. And then I give the event B the middle quadrant. It should be the same area roughly as A. It's just taking up the middle area. And the area inside of A and B relative to B is the same as A's area relative to the entire sample space. So, or that is, A's area is a quarter of the sample space, and A's area in B, or A's intersection in B, is a quarter of B. So knowing that you fell into that, so basically A corresponds to the probability of falling into the upper left-hand quadrant, and knowing that you are in this middle square does not really tell you whether you fell into that quadrant or not. That gives you basically no information on that. So this is a sketch of what independent events might look like if you want to draw them as a Venn diagram. If this sketch does not make sense to you, then don't worry about it. Just leave it alone. Because it's very much a tortured example. You have to kind of work hard to get something that looks like this. And I'm not super convinced that it's necessarily all that enlightening as to what independence means. So if it doesn't make sense to you, then just move on. Don't worry about it. Okay. So the next example, we're going to consider rolling a 6-sided die, and I'm going to show that the event A, which is that the number of pips does not exceed 4, and the event B, that the number of pips is even, are independent events. So let's go ahead and enumerate what falls into these two separate events. We have the event A, well, not separate, just different. So the event A the number does not exceed 4. So that includes 1 pip, 2 pips, 3 pips, and 4 pips. All right. The event B, which is that you get an even number of pips, is going to be 2 pips, 4 pips. Ugh. Come on. I want the 4th pip. Ugh. I tried. And 6 pips. Ugh. Not always cooperative. All right. So let's compute the probability of A given B. To show that two events are independent, it is sufficient to just compute the probability of A given B and show that that equals the probability of A. So the probability of A given B is going to be the probability of A and B divided by the probability of B. All of these outcomes are equally likely. So the intersection of the two sets is going to consist of 2 and 4. Those are the two things the two sets have in common. So this is going to be the dice with face 2 and the dice with face 4. Ugh. Why is it so uncooperative? Okay, there we go. Probably 2, probably 4, and divided by the probability of B. Okay, and at this point we can basically just count how many elements are in these sets. So for the intersection, there's 2 outcomes in that set. And for the probability of B, there's 3, so that's going to be 3 over 6. So we end up with the 6's canceling out, and the probability of A given B is equal to 2/3 as a result. But the probability of A, there are 4 outcomes in A divided by the size of the sample space, which is 6, which is also 2/3. Those two numbers are the same, therefore these two events are independent of each other. Okay, next up, suppose we have events A1 through AN. These sets are said to be mutually independent if, and I know that this definition is rather complicated. For k less than or equal to n, the probability of any subset of that collection of events will become the product of their individual probabilities. So it is not sufficient to just check that for all of these events, A1 through AN, the probability of the intersection is the product of probabilities. It has to be true for not just the entire collection of events, but any sub-collection of that collection of events. They all must turn into product of probabilities. If this is not true, then they are not said to be mutually independent of each other. And here's kind of the reason why. When we were saying mutually independent, what we really kind of want to say is that none of these events give any information about any of the other events. And so that means you would want to say that you take any 2 events in this collection of events, and they will be independent of each other. You want to be able to say that, but it is not sufficient to just check that the entire intersection, the probability of the entire intersection turns into the product of the respective probabilities. And here is an example that shows why that is not in fact true. This is an example from this paper that I've highlighted in red. Use the diagram below for finding probabilities. Compute the probability of A and B and C. That actually is just going to be that tiny little sliver. So probability of A and B and C is equal to 0.04. And then we're going to find the product of the probabilities of the events A, B, and C. So the probability of A, so that's going to be the probability of the blue circle, which is going to be 0.1 plus 0.06 plus 0.04, which is 0.2. So this will be
0.2. The probability of B is going to be the green circle. So that's going to be 0.06 plus 0.04, that's 0.1, plus another 0.1 is 0.2, plus another 0.2 is 0.4. So this will be 0.4. And finally, we've got the probability of C, which is going to be this blue circle here. So we've got 0.16 plus 0.04 is 0.2, plus another 0.2 is 0.4, plus 0.1 will be 0.5. So this probability, the probability of C, is equal to 0.5. So the probability of A times the probability of B times the probability of C is going to be 0.2 times 0.5, which is 0.1, times 0.4, which will be 0.04. And those two numbers are equal to each other. So it's tempting to say that these events are independent of each other, but then I ask you to compute the probability of A intersected with B. So the probability of A intersected with B corresponds to this blue region that I've highlighted, which is going to be 0.1. So that equals 0.1, but that does not equal the probability of A times the probability of B, which is equal to 0.08. And before you say, well, those numbers are close doesn't mean a thing. I don't care about close. They need to be the same. So, yeah, they are not independent events. And as a result, these events A, B, and C are not mutually independent. Could you say that there is some other notion of independence that you could apply? I don't really know, and I don't really care, because I have seen notions maybe like pairwise independence as an alternative notion of independence, and I've never seen it ever used in my own life or work. It doesn't really seem like it leads to any sort of useful concepts. So yeah, that's that. All right, next example. This example is supposed to motivate. Maybe you remember when I was talking about flipping a coin until you get heads. This example is supposed to motivate our assignment of probabilities in that situation. So we're going to flip, remove the 8 part. That I don't know why that was there. I don't know why I have 8 fair coins. So flip fair coins until we get heads. And furthermore, each flip is independent. Okay, so what is the probability of heads? Tails, heads, tails, tails, heads, tails, 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 heads. What will be the probability of a sequence of flips, a sequence of n flips to have n-1 tails and a heads at the end? So the probability of heads, if this is a fair coin, is going to be 1/2. The probability of tails heads, and this is, by the way, getting a little abusive with notation, but the probability of tails heads is going to be the probability of tails times the probability of heads, since those two flips were independent of each other. We are now on to Chapter 3 on discrete random variables and probability distributions. This chapter serves both as an introduction to random variables and also an introduction to discrete random variables in particular. But many of the concepts that we see here are going to transfer over to the continuous context when we're dealing with continuous random variables. So let's get started. So in this section, we're going to talk about some random variables. A random variable, which is sometimes abbreviated with the letters RV, is a function taking values from the sample space S and associating numbers with them. Conventional notation for random variables uses capital letters from the end of the English alphabet, with lowercase letters, while lowercase letters are usually used to denote a non-random value or outcome. So up to this point, we have been using lowercase letters for data, and when talking about random variables, we're going to switch to uppercase variables or uppercase letters. And the distinction does somewhat matter. Honestly, this is a rule that is very frequently broken, although while I say that, in this class, I'm not planning on breaking that rule all that much. Yeah, I mean, I break it all the time in my research work, but this is a situation where I'm probably going to stay rather true to it. So there's a difference between a random variable whose outcome is unknown and a possible value that random variable could take. So using the fact that random variables are actually functions, like the term random variable is there's somewhat of a joke that random variables are neither random nor variables because random variables are not really variables, they're treated as functions. And they're not random because if you know what outcome from the sample space you got, you know the value of the random variable. Because the randomness comes not from the random variable x itself, but rather from omega, which is an outcome from the sample space. If omega is an outcome from the sample space, the notation x of omega equals little x can be used to say that the value of the random variable x when the outcome little omega occurs is little x. So little omega, that is a random outcome. Little x is non-random. And x will equal little x when the random outcome omega occurs. All right, so the set of omega such that x of omega is equal to x is the event that an element of S is drawn that causes the random variable x to equal little x. The set of omega such that x of omega is in some other set A, where that other set is often some subset of the real numbers, is the event that an element of S is drawn that causes the random variable x to assume a value that is in the set A. So technically, when we want to talk about whether a random variable it takes a value inside of a set or not, this is the notation. This is what we should be using for that notation. We are asking for the probability that we draw an omega that causes x of omega to be in the set A. But that is often rather tedious. We would rather just say, what is the probability that x is in A? That's much simpler. Random variables are commonly classified as being either discrete or continuous. Discrete random variables, or discrete real-valued random variables, take values in a finite or countably infinite, or innumerable if you prefer, set with positive probability. So examples of sets that discrete random variables take their values in could be a finite set of numbers, such as 0 or 1. It could be the integers. It could be the natural numbers, such as 0, 1, 2, 3, 4, 5, 6, and so on. If it's enumerable, then it could potentially be a discrete random variable. If the set that it falls into is any number between 0 and 1, including fractions and including rational numbers and irrational numbers, any of those numbers, then it's no longer discrete. It's going to be considered continuous. On the other hand, continuous real-valued random variables satisfy the following two properties. First, the random variables take values in intervals, which are possibly infinite in length, or disjoint unions of intervals of the real line with positive probability. That's the first property that continuous random variables satisfy. The second is that
for any constant C and R, the probability that that random variable is equal to C is equal to 0, which is kind of a strange assumption. You're saying that you know that this random variable, this continuous random variable, is going to equal some real number, but you're saying the probability that it equals any real number is equal to 0? Well, for starters, that must be the case, because this is an infinite set, so you need to have some way to assign probabilities, and there's too many numbers in the real number system for numbers in general to have positive probability. And secondly, there's a way that my probability instructor put it. He said, if you know that someone's going to win the lottery, you just know it's not going to be you. So by that same logic, you know that these random variables will fall inside of an interval. You just don't know what number it will be. You will never know what number it will be. And it's highly, highly, highly unlikely that it will be that particular number you chose. So unlikely that that probability is effectively 0. Perhaps the simplest non-trivial random variable is the Bernoulli random variable. If x is a Bernoulli random variable, then the probability that x equals 1 is equal to 1 minus the probability that x equals 0, which is p. And we say that x follows a Bernoulli distribution with parameter p. That's what we're saying. So we have the random variable x, and this notation means that it comes from some distribution with some parameter. We're going to leave that alone, that verbiage about distributions alone for a minute. That's going to be the subject of the next video. But basically, we would just say that x is a Bernoulli random variable because it has these properties. All right, so the set S on which x of omega is defined could be really just about anything. It's natural to think of Bernoulli random variables as being equivalent to coin flips or possibly biased coin flips. The thing, though, is you do not have to necessarily have coin flips. For example, you could have a probability space where there is a coin flip, where if you draw heads, this random variable will evaluate to the number 1. And if you draw tails, or you flip and it lands tails up, it will evaluate to 0. That's one possibility to get a fair or balanced Bernoulli random variable where the probability of getting 1 is 0.5. Alternatively, you could roll a fair die, track whether the result of the die was even or odd, and in the event of an even number of pips, this random variable evaluates to 1, and the event of an odd number of pips, this random variable evaluates to 0. Either one of those situations could be the case. And it is statistically impossible to differentiate between these two possible setups of random variables and sample spaces. So in that case, it's almost as if once you know the distribution of the random variable, you can pretty much forget whatever the original sample space was and any of the properties of that sample space. You can now work as if this random variable were the identity function, and its sample space is going to be the real numbers or something, maybe the number 0 and 1. So in that sense, you almost forget all of that stuff that we talked about before. I guess you don't forget about it, but you no longer care about the specifics of the sample space and the elements that you're drawing from the sample space. The specifics no longer matter. So we get to talk about these things in a very general way. All right, so for the first example, which of the following random variables are likely to be considered discrete and which are likely to be considered continuous? Describe the space of outcomes the random variable takes with positive probability. So for our first case, flip a coin, record 1 for heads and 0 for tails. If this is the situation, the sample space for our experiment would probably be the sample space consisting of heads and tails. And the random variable x, when given the outcome h, is equal to 1, and the random variable x, when taken the value tails, is going to equal 0. So the space of outcomes, which I will denote by x of s, where you almost feed the entire sample space into this function x, is going to be the set 0 to 1. By the way, the term for this is the image of the sample space s under the random variable x, or the function x. All right. This random variable, since the space in which its outcomes falls is generally, like, that's a finite space. There's only 2 numbers in it. So this random variable would be considered discrete. Okay. Next example. Roll a die, record the number of pips showing. So the sample space in this situation would be die rolls. So we got 1, 2, 3, 4, 5, and 6. All right, so that's the sample space. X of 1 would be equal to 1. X of 2, or 2 pips, would be equal to 2. And you'd kind of keep going on like this for other possibilities. So you could say x, when you have 6 pips on your face, would be equal to 6. So this is the reason why we didn't want to write down the numbers 1 through 6 when talking about die rolls. It makes it easier then to talk about random variables as being a translation from the number of pips showing on a dice face to numbers, actual numbers. And we would like to be able to make that translation. Random variables do not need to be defined on numeric spaces. There doesn't have they basically say nothing about whatever's in that original space. They don't care at all what's in that original space. And once you have a random variable, you get to work in the real numbers. And that's really nice. So the image of the sample space under x is going to be the numbers 1, 2, 3, 4, 5, 6. And that suggests, since this is a finite set, that this is a discrete random variable. All right, next example. Roll a die, record 1 for an even number of pips, and -1 for an odd number of pips. Okay, so the sample space is the same as before, so we're going to copy that sample space down. So x of 1 is equal to x of 3, which is equal to x of 5. In all of these cases, x is going to come out as -1 since you have an odd number of pips. In the case of 2, that's so x evaluated for the dice with 2 pips is going to be the same as when there's 4 pips, which is going to be the same as when there's 6 pips. In all of these situations, the random variable x comes out as 1. So the image of the sample space under this random variable will be -1 and 1. And again, this is a discrete random variable. Okay, the time in minutes needed to complete a race. It seems appropriate to say here that the sample space is going to be some positive real number, which we'll put with r plus, which is equal to the set 0 to infinity, including 0. And in this case, so it seems like the the random variable is going to be the identity function where it takes one of the numbers from the space and just spits out that exact same number. So in this case, x of omega is equal to omega, which is in the positive or non-negative real numbers. So that means that the image of the sample space under x is going to be the positive real numbers or the non-negative real numbers, and this is a continuous space. So this is going to be a continuous random variable. And basically what we're saying is the time it takes to complete the race can be any number from 0 to infinity, not just integers, but also including fractions and algebraic numbers and transcendental numbers, every single possible real number. And since the real numbers are an uncountable space, that means that this random variable is going to be continuous. For similar reasons, number 5, the length in centimeters of a hair plucked from a person's head. We could say that the sample space is going to be hairs. No, not x. Sorry. The sample space will consist of hairs and a random variable x from that sample space, which I'm going to draw a hair. Okay, that's the thing. All right, so x when given a hair gives you a number, so the length of the hair. And so it suggests that the image of the sample space under x is going to be the positive real numbers, or the non-negative real numbers again, since hairs can be in principle of any length and it's an uncountable length. So, I mean, it's going to be true that there's a finite number of hairs in the world and therefore a finite number of hair lengths. So, if we were being super, super duper technical, we would say, actually, this is a discrete random variable because there's only a finite number of possible hair lengths since there's only a finite number of hairs. But that seems ridiculous. That seems like a ridiculous model. That seems like way too much complication. Continuous random variables are continuous because it's easier to work with continuous things than discrete things. And you're probably going to agree with that when we start doing all the work for the discrete random variables and all the work for the continuous random variables and say, oh, it's actually somewhat easier to work with continuous stuff. So we're going to say that it's the real numbers, in which case this is a continuous random variable. Okay, next up, roll 2 dice. Record the sum of the number of pips showing. I'm not going to bother writing out the sample space, but I'm going to say that x could be, like, say, if you gave x the numbers 1 and 4, it's going to add up the pips showing on those 2 dice and give you the result 5. So the image of x under the sample space is going to be the numbers from 2 to 12. And since this is a finite set, this is going to be discrete. Okay, next up. Flip a coin until H is seen and count the number of flips. So the sample space consists of heads, tails, heads, tails, tails, heads, and so on. So the random variable x, when given one of these strings, let's say tails, tails, heads, is going to evaluate to the length of the string, which means that x, when fed this sample space, its image is going to be the natural numbers, which are the numbers 1, 2, 3, and so on. And this is a discrete space because there's an innumerable amount of numbers in this space. And since it's innumerable, that means it's going to be discrete. So this is a discrete this is a discrete random variable. By the way, if you're not familiar with the word innumerable, that means listable, as in you can list it out. And even though it will take you an infinite number of years to list out everything in this sample space, or in this set, you will hit everything in that set in finite time. So every possibility, the same cannot be said for the real numbers, by the way. Even if given infinite number of years, you will not hit every value if you started trying to list them out. So that's actually a very deep result in set theory, or I don't know if deep's quite the right word for it, but it's certainly an important result. So we're just going to take it for granted here that is the case. Example 2. Consider an experiment of rolling 2 6-sided die. Define 2 random variables for this experiment. Are they continuous or discrete? We can define multiple random variables for the same sample space, and there are advantages to doing so, because when doing so, we can talk about notions such as correlation, or study the behavior of different random variables in the same space. Consider different possibilities. I'll talk about their joint distribution together, stuff like that. So, as a reminder, the sample space consists of dice faces, so we could have, for example, 1, 1, 1, 2, and we would keep going on like this. You've seen in previous videos how to do this until eventually we listed out 6, 6. Okay, so this is our sample space. What's one random variable we could define? We could say that x, the random variable x, when given some outcome omega in the sample space, is equal to the sum of the pips. Whereas if we gave, no, let's not call the other random variable x, we'll call it y. That y will be another random variable defined on this space, and it will be the max of the pips. So, for example, x of the dice face, of the combination 1 and 2 will equal 3 because that's the sum, whereas y of 1 and 2 will equal 2 because the maximum of the number of pips is going to be 2. Okay, so that's it for this section. This was a basic introduction into what we are on to the next section in our chapter on discrete random variables. And at this point, you're probably thinking, okay, we got these things called discrete random variables. All right, what's the point? Why do we have these things, random variables? Why does anyone care about this? This seems like an extra complication on on these probability spaces. We were still able to talk about probability. We haven't really added anything so far. Well, random variables truly are an addition that makes things much better and allows you to say additional things about randomness. Once you have random variables, you are now allowing for concepts such as we have phenomena that is essentially the same except for a couple parameters. Like there's a few parameters that we need to figure out, and once we know those parameters, we basically know everything there is to know about this phenomena. Or there's concepts such as expectation or mean. In order to be able to talk about expected values, you need to have random variables. So once we've introduced random variables, these things that take things in our sample space and turn it into numbers, you now gain a lot of additional structure. The first thing that we get that is an essential property of random variables is a probability distribution. So a probability distribution for a random variable is a function that describes the probability that a random variable takes on certain values. Discrete random variables are determined completely by the probability mass function, which is abbreviated PMF, And the probability mass function for a random variable is p of x, which is equal to the probability that the random variable x, capital X, so remember that capital X is referring to a random variable. This is a thing that hasn't taken a value yet, or we don't view it as being equal to anything per se at this moment. But we're asking for the probability that this random variable, when we actually evaluate it and get a number out of it, is going to equal x. I like to think of random variables as they will have a future value, but they don't really have a value right now, and we're asking for their probability and stuff. So we're asking, what could this thing be in the future? So a coin flip is random before you make the flip, if that makes sense. After you've made the flip, then it's no longer random because you get to see whether it was heads or tails, which actually is getting more again into the issue of what does probability actually mean. Like, for example, let's suppose that we flip a coin and it lands heads up, and then we cover it up. We don't get to look at it. We never saw what the coin did. We immediately, the moment it lands on the ground, cover it up in a box. In principle, we would say that under this frequentist notion of probability, we should say that this random variable has a value and is no longer random. We just don't know what it is. Whereas if you're adopting maybe the gambler's notion of randomness and probability, you might still view it as being random, where you can start placing a bet on whether it's heads or tails when you take the lid off of the when you take the box off of the coin and then actually observe it. I'm not going to talk anymore about that. I've already recorded a half-hour video about the interpretation of probability, and you can watch that if you want to learn more. All right, so I'm just saying this because I feel like students, especially with this notation, especially when you're starting out, can bother students. And they're wondering what capital X is and what little x is and what's the difference between them. And the difference is this is random and we don't actually know what it is, whereas little x is something that is fixed and we know what little x is. So really, when I'm writing this down, little x is going to be substituted for a number. Like, for example, there's going to be p of 1, which is going to be the probability that capital X is equal to 1. Like, at some point, we're going to make that substitution. So basically, the little x right here is going to get substituted with a number, but the capital X is never going to get substituted, and that's always going to be viewed right now as being random. And we don't really know what its value is going to be. And we're just studying what its value could possibly end up being and how likely it will end up taking certain values. Sorry if I'm going on too long about this. This is just something that I know that students at some level struggle with, and I try over and over again to try and explain it, and I'm never fully satisfied with my own explanation. Okay, the probability mass function, one way to visualize a probability mass function is using a line graph, where a line is placed on each point x of r, that x takes a positive probability and extends to the height representing p of x. Okay, so before I draw a visualization, I'm going to say that we are totally allowed to say, all right, we've got inputs x and outcomes p of x, where p of x is a function that gives us the probability this random variable will equal x. And we can construct a table if we want to, like, for example, 0, 1, 2, 3, 4. We could construct a table of possible inputs to this function. And for possible outputs, we could say, let's see, what's something we could do? We'll just say that all of these are equally likely. So all of these are 1/5. So this function puts out 1/5 all the time. Well, should we always do that? We might say this is 2/5. And this is 1/10. And this is 1/10. There. I think that's okay. Does this still add up to 1? This must add up to 1, by the way. Actually, that's the thing we're going to talk about in the future. Let's see. 1/5 plus 1/5 is 2/5. Plus 2/5 is 4/5. Plus 2/10 is another 5th. So that does, in fact, add up to 1. Which, probability mass functions, if you add them up, if you add up all of their non-zero values, then they must always add up to 1. Always. Probably mass functions always add up to 1. If they don't add up to 1, then they're wrong. They're not probably mass functions. If you ever compute a probably mass function and it doesn't add up to 1, then it's not a probably mass function. And I don't care if it's close. It close is nothing. Close is not 1. 1 is 1. All right. Okay. And I suppose we're allowed to say, all right, let's suppose I threw in a fifth value, then the probably mass function will be 0. And presumably anything that's not on this table, if I didn't list it out, then the probably mass function is 0. Right? So anything not written down is 0. All right. But then we can visualize a probably mass function using a line graph. So we've got possible x values that this thing could take, and we've got its probably mass function, its probability at those points. So we could have x equals 0, 1, 2, 3, 4, and then for those, let's see. I've already got a lot of what I need. So we'll do 1/10, 2/10, 3/10, 4/10. So 0 is going to be 2/10, so that's about here. 1 is going to be 2/10 again, and then we got 4/10, and then 1/10 and 1/10. This is a visualization of the probably mass function that I wrote on the right-hand side of the page. So I generally am like drawing a dot at the probability and then drawing a line up to the probability of the random variable equaling that value or something like that. So yeah, that's how you can visualize it. There's also probability histograms, which are very similar to the line graphs and very similar to the histograms that I was discussing several lecture videos ago, where you could, instead of having these lines, draw like these. The table that I have is a lot like the relative frequencies that I was discussing when discussing histograms. So what you would do is draw something similar to the relative frequency of those possible values. So we got 0, 1, 2, 3, 4, and we draw a bar that is centered on that point. So we got we've got something going up to 2/10 and 2/10 again, and then 4/10 and then 2 1/10. Yeah, so there we go. There's that. This is another way to visualize the probability distribution if you prefer it. There's really no difference. In fact, I would say that Edward Tufte would probably say that they are the same graph, essentially. It's just the one up here, it should be preferred because it uses less ink. Okay, continuing on. Let's see some examples. A fair coin is flipped. We define a random variable x. When h occurs, x evaluates to 1, and when t occurs, x evaluates to 0. Find the probability mass function of x, which is p of x. Visualize p of x through with a line graph. And you're thinking, how do we know what the probabilities are? Well, we know because I said this is a fair coin. And since I know that it's a fair coin, I know that the probability of heads is 1 and the probability of tails is 0. Okay, so I'm going to start out actually with that tabular form. So we've got x and p of x. So we've got possible values that the random variable x could take are 1 and 0. So we are going to put 0 and 1 as potential values for this random variable. This random variable will equal 0 if the coin comes tails up. And since this is a fair coin, the probability of getting tails, so actually maybe I should be more verbose about this and say that the probability that x equals 0 is equal to the probability of drawing an omega from the sample space, an outcome from the sample space, such that x, when evaluated at that outcome, equals 0. I'm being very verbose about this. What are such outcomes that causes us to evaluate to 0? Well, we know from the definition of the problem that such outcomes are only tails. So this is the probability that you get tails, and the probability of tails, because this is a fair coin, is 1/2. So that means that x is so at 0 the probably mass function will be 1/2, and at 1 the probably mass function will also be 1/2 because this random variable for starters, this random variable is going to be 1 when the coin lands heads up, and the probability of heads is 1/2. That's one way to think about it. And another thing to think about it is there's only 2 numbers that this random variable could take with positive probability, 0 and 1. 0, its probably mass function is 1/2, so at 1, it must be whatever it takes to cause the probably mass function to add up to 1. So 1 minus 1/2 is going to be 1/2, and thus the other value is going to be 1/2. We visualize this with a line graph. We'll go ahead and make this 1/2. What we end up having for our visualization of the probability mass function is we have lines extending up to 1/2. All right, and that's our visualization for it. Okay. This, by the way, is a complete description of the probability mass function if we are willing to say that anywhere we don't list, the probability mass function evaluates to 0. Because that should make complete sense to you. Because let's say what is going to be p at 1/2. Well, that is the probability that x equals 1/2, which equals the probability of drawing an outcome from the sample space that causes the random variable to evaluate to 1/2. Okay, so we know that there are 2 outcomes in the sample space, which are heads and tails. And x is a random variable, and therefore it is a function. So you know that functions, when given one input, give you only one output. Only one output will come out. So what does that mean here? We know what this function will be at heads, which is one outcome in the sample space. We know what this function will be at tails, which is the other outcome in the sample space. So what outcome causes this random variable to equal 1/2? Because neither of those cause the function to evaluate at 1/2. So that means that the probability of drawing an outcome from the sample space that causes this to evaluate to 1/2 is the probability of the empty set. Because the set of all numbers, or not numbers, the set of all outcomes in our experiment that causes this random variable to evaluate to 1/2 is the empty set, because there is no such outcome. So you end up computing the probability of the empty set, and the probability of the empty set is 0. So that would mean that anything that isn't listed here, it's natural to say that the probability mass function is 0. Okay. Moving along. There is an R package called discrete RV. And this package allows for users to define random variables and work with them. And I think this package is pedagogically useful, but for serious work with these random variables, I wouldn't recommend using it. I actually just made a few minutes ago. It wasn't a few minutes ago. It was more like a few hours ago. I just made a few hours ago lecture videos for the lab for R. Are on my R introductory videos. Functions for dealing with probability in R and dealing with a lot of random variables and classes of random variables, families of random variables, and I never use this package. Because it's more for allowing students a laboratory to work with random variables in the notation that we're using in the lecture class, or a notation very similar to it, and not actually meant for serious work trying to work with the CDFs and the PDFs and expected values and all that stuff of these random variables. But it's kind of nice. So for example, in this situation, I could define the random variable x and say that this is a random variable with the RV function. Its possible values are 0 and 1, and the probability of getting those outcomes are each 1/2. And it will make a nice output, a printout for that, basically summarizing what I just said. And in addition to that, when I tell R to plot this random variable, it creates the plot of the probability mass function. So that was all very nice. Next example. Let S be the sum of the number of pips rolled on 2 dice. Find P of S and plot it. Okay. Okay, so let's form our table again. So we've got S, and we've got P of S. Okay, so S are possible sums of the dice. So what are some possible sums of the dice? Well, the smallest it could be is 2, because that's what happens when you roll snake eyes, or 1 and 1. So the smallest possible sum is 2, and the largest one happens when you roll boxcars, which is, both of them are 6, so that will be 12. So it's going to be everything in between. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Hold on. I didn't write that quite right. 10, 11, 12. Okay. And now we need to figure out the probability mass function. Okay. So we're saying we could imagine that there is a sample space that's consisting of dice of combinations of 2 dice, like we got 1 1, 1 2, and 2, and going on, and we got like 6 6. We've already worked with this type of sample space in previous videos, and I don't want to go into too much more detail into it because it can get kind of tedious. So, we know that there are 36 outcomes in this sample space. So, and we're saying that everything is equally likely, so therefore, the probability of the event that the dice add up to 2 is going to be the number of outcomes where the 2 dice add up to 2 divided by the size of the sample space. So how many outcomes are there where the dice add up to 2? Well, you can get snake eyes, and that's it. So there's only one outcome that corresponds to that, and then we divide it by 36. How about 3? We could either roll 1 on the left dice and 2 on the right dice, or I guess let's re-adopt that blue dice, red dice verbiage, and we could say the blue dice rolls a 1 and the red dice rolls a 2, or we could have the blue dice roll a 2 and the red dice roll a 1, and that's it. Otherwise, it will not add up to 3. So that's 2 outcomes that correspond with this. So we're going to have 2 over 36. And for 4, we could either have 1 and 3, 2 and 2, or 3 and 1. So that would be 3 over 36. And that's going to keep going. So we would have 4 over 36 for 5, 5 over 36 for 6, and 6 over 36 for 7. All right, 12. There's only one outcome where you can get 12, and that's boxcars, 6 and 6. So this will be 1 over 36. For 11, you could get 5 and 6 or 6 and 5. So we'll have 2 over 36. And you can see the pattern. It's going to become 3 over 36 for 10, 4 over 36 for 9, and 5 over 36 for 8. Okay, and now we're ready to create our little visualization. We got 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That is an awful looking 11. I really did try harder, but sometimes the screen doesn't want to cooperate. All right. And let's see. For the y-axis, we could go... the highest you ever go is 6 over 36, so we could go 1, 2, 3, 4, 5, 6. There we go. So 6 over 36 is at the top. So for our probabilities. So we'll go 1, 2, 3, 4, 5, 6, 5, 4, 3, 2, 1. Okay. And that's it. That's our probability mass function. So, using this discrete RV package, we've got what we could do is create a random variable representing a single die. So that's created here. And then we could say, all right, S is the sum of independent and identically distributed copies of the random variable D. That is getting into verbiage that and terms and ideas that I haven't really talked about yet. But basically, you add up 2 independent dice, which is kind of what's going on in this experiment. And then I tell it to plot it, and it makes a plot, and that's a very good plot. All right, next up. Consider flipping a fair coin until heads is seen. Let n be the number of flips. Find a probability mass function describing the distribution of n and plot the first few values of the PMF. And we've actually talked about this type of random variable before a number of times in the previous chapter. As I mentioned there, it's one of my favorite random variables to refer to since on the one hand, it's not like the setup is quite simple to understand. You flip a coin until you get heads. That doesn't take a great deal of imagination. And yet you can still get a lot of richness out of it. And the mathematics can get kind of involved. So, okay, so in this case, what we ended up coming up with before and suggest what we should have now, in fact, maybe if you go back to that video and look at how I was showing that the probability of the sample space under some probability measure will in fact be 1, I actually kind of defined a prototype random variable, n of omega, that was measuring the length of the string, and that's basically a random variable right there. I defined a random variable on that space so that I could show that the probability of that space added up to 1. So yeah, they're very useful things. But basically, we could just say that this is 1/2 to the power n for when n is a natural number. Otherwise, you would just assume that this thing is going to be 0. So this is a natural probability mass function for this space. We actually showed in that section that it adds up to 1. And yeah, so, okay, so let's plot this probability mass function. We got possible values: 1/2, 1/4, 1/8, 1/16, 1/32. So 1, 2, 3, 4, 5. So for 1, we go up to 1/2. For 2, we go up to 1/4. For 3, we go up to 1/8. For 4, we go up to 1/16. And for 5, we go up to 32nd. And in principle, this graph goes on forever. But we're just going to stop at 5.
Section is on expected values. Let's start by defining what an expected value is. The expected value of a discrete random variable, which we are often dealing with EX, is given below. So the expected value of X is equal to the sum of X times the probability mass function of X, wherever the probability mass function of X is non-zero. This is just a more general way to write down what expected values are. In principle, most of the time, the X over which you're summing are the integers. So if you really wanted to, most of the time you'll be okay thinking of expected values as this, like X equals, let's say, 0 to infinity. Or another way we could do it is, this is actually allowed, X equals negative infinity to infinity. Or if you know that your little x ranges from A to B, you could say, we could say x equals A to B. There's all sorts of ways we could possibly rearrange this, but really what matters is that you're summing up this expression
x times the probably mass function of x, wherever that probably mass function is non-zero. So I'm just going to leave this as x such that probably mass function of x is greater than 0. Actually, I'm just going to not even really say all that much over what x we're summing over. I'm just going to say that you sum over x. Okay? Next, expected value of x is viewed as the population mean, which we're often denoting with the Greek letter mu. Described in previous chapters, we can always compute the expected values of functions of x. Oh, no, not always. Why did I say always? Like, at the very end of this section, I'm going to give you an example of an expected value that can't be computed. But we can also compute, also compute the expected value of functions of x, that is. So that would be the expected value of h of x in a natural way by saying that the expected value of h of x is equal to the sum over x of h of x times the probably mass function at x. And this formula should make some sense to you because you've actually seen it before, or something very similar to it before. Remember when we were computing the sample mean? The sample mean was 1 over n times the sum from I equals 1 to n xi, which is also equal to the sum from I equals 1 to n xi times 1 over n. And the 1 over n, I mean, if you add up 1 over n times, what number do you get? You get 1. And also, 1 over n is a number that's greater than 0. So, actually, you could see this as a probably mass function for xi. So you could imagine that you have your sample of observations, and you're going to pull an observation at random with equal probability from your sample. If it's pulled with equal probability, then you're going to pull it with probability 1 over n. So actually, you've seen this expected value formula before. It's just that this formula down here is a more general notion of a sample mean, or not really sample mean, but of mean. So it allows for more situations. It allows for infinite possibilities for x and so on. The expected value is in some sense a best prediction for the value of x, and this form no, did I say sample mean? I don't think I did. Expected value. You can see this footnote for what sense in which it's a best prediction, but it's hence the term expectation. It's like if you had to guess what value this random variable is going to be, you can use the expected value to do that, and it will be correct in some sense. So, example 11, compute the expected value for some of the random variables that we've seen in previous sections. So, Bernoulli random variables, discrete uniform random variable that represents a die roll, and the geometric random variable with parameter p. Okay, so let's get started. The first situation for a Bernoulli random variable. The expected value of x is equal to the sum of xp of x, and the values of x for which p of x is possibly non-zero will be x equals 0 to 1. So this will be 0 times p of 0, which is 1 minus p. This corresponds to the probably mass function at 0, plus 1 times p, where p is the value of the probably mass function at 1. I guess this notation is actually a little unfortunate because I've got a couple different p's. So maybe I should switch out the notation for the probably mass function in this example. Just switch it with f. That could probably make things a bit more clear. So this still, nevertheless, in any situation, is the probably mass function for x. Okay, and well, let's see. That just goes to 0, and that's going to equal p, so that means that the expected value of x is equal to p, which is nice and actually rather insightful. It's saying that the expected value of a Bernoulli random variable with parameter p is equal to the probability that that random variable is equal to 1. And that's actually a very useful fact. That's rather useful. It allows us to relate Bernoulli random variables, probabilities for events, and expected values. It gives us a way to what we could do if we wanted to relate expected values to probability of an event is create a Bernoulli random variable that's equal to 1 when that event occurs and 0 otherwise, and then the expected value of that random variable would be the probability of that event occurring. But I'm just going to leave that issue for now. Let's work with the next example. So the expected value of S is equal to the sum of, let's say, SP of S. Again, we're talking about a probability mass function when we're talking about P down here. And let's think about what are things that this random variable could take with positive probability. We'll end up summing from S equals 1 to 6. So that's going to be, let's see, P of S is always 1 over 6. So this is equal to 1 over 6 times the sum from S equals 1 to 6 of S. And actually, there's a formula for that. Hopefully you remember that from your algebra classes. In general, you have the sum of S equals 1 to n of S. This is a sum of an arithmetic series. That's going to be n times n plus 1 divided by 2. Okay, which means that this sum is going to equal 1/6 times 6 times 7 divided by 2. Those two 6's cancel out. So this will equal 7 over 2, or 3.5. Okay. Finally, we have the expected value of, what am I calling this geometric random variable? I'm calling it n. The expected value of n, which is going to be the sum of n times p of n, where n ranges from 1 to infinity. All right, this is going to get much more complicated. So because this is going to involve an infinite sum. P of n is going to be, we've got np 1 minus p to the power n minus 1. And we're summing from n equals 1 to infinity. Let's see. The p here is a constant, so we can bring that out. We are not summing over p. That means that we can say that this is equal to p times the sum from n equals 1 to infinity, n times 1 minus p to the power n minus 1. You probably did not see a formula for this. So what are we going to do? We're going to get tricky. We're going to get really tricky. You've taken calculus. Presumably you've taken calculus 1, which includes differential calculus. So, you have seen this formula before. The derivative with respect to x of x to the power n is equal to nx n minus 1. With some assumptions on n, like for example that it's, let's say, at least 1, in which case that would hold in this situation. If you're looking at 1 minus p as the thing you're differentiating, those two things look rather similar, which means that actually we could be invoking some sort of differential or derivative in our sum and say instead that this is equal to p times the sum from n equals 1 to infinity, the derivative with respect to p, 1 minus p to the power n. Now, you would notice that right now, if you were to in fact take that derivative, you would almost get what I wrote on the left over here that I've underlined in green. You would almost get that, except you'd be off by a sign, as in you'd get negative something because you have to invoke the chain rule. So what are we going to do about that? Well, we're just going to throw a negative out here, and then it's certainly true. Although I'm going to mention that, well, okay, it's actually true as written down. There's no caveats yet, but there is going to be one in just a second, because I'm going to say that this is equal to negative p times the derivative with respect to p, the sum from n equals 1 to infinity, 1 minus p to the power n. Okay. You can't just bring derivatives out of sums like that. Or you can, but there are conditions. Like, you can't just look at any sum in the world and see derivatives inside of the sum and say, okay, I could just slip the derivative out. It's not that simple. There are details, there are conditions under which you can do this. Those conditions are satisfied here. I actually don't remember them off the top of my head. I just know you can. You can go look at some calculus book or some analysis book. It's probably going to be in an analysis book. Or Wikipedia. Wikipedia has pretty good math articles. And it would tell you when you can switch, because that's what you're doing. You're switching a sum and a derivative. It will tell you when you're allowed to do that. And I'm just completely sweeping that under the rug. And I'm fine with that, because I don't care. I got other stuff to do. All right. The thing, though, is we know how to compute this sum. You know that this sum is going to become 1 minus p divided by p. So that means that this will become negative p. Oops, wrong color. Negative p. And then we've got the derivative with respect to p of 1 minus p divided by p. Which we should probably simplify somewhat and say that this is equal to negative p and the derivative with respect to p of, let's see, 1 over p minus 1. Yeah, that's right. And so then we take that derivative and say we've got negative p, and on the inside, after we take the derivative, we'll get negative 1 over p squared. Those two negatives turn into positives. We cancel out one of the p's, and this is equal to 1 over p. There we go. This actually has a very nice, intuitive interpretation, which is that, let's say that you're flipping a coin until you get heads. How many times do you, what is the expected number of flips? First one's tails, second one's heads. Makes pretty good sense to me. Or let's say that you have a biased coin, and you flip this coin until you get heads, and the probability that you get heads is 0.1. How many flips do you need? 10 flips. Seems to make pretty good sense, at least to me. It allows, at least in my mind, a way for me to relate probability of an event happening with time, and say that if you were to have a sequence of independent replications of this event, this is about how long you have to wait until you see that event happen, which is another way to think of, or another way to reason about how rare that event would be. Like, for example, if there's like a 10% chance of an earthquake every year, how many years is it going to take for you to see an earthquake? 10 years on average. Something like that. So I really like that formula and interpretations like that. Okay, moving on. This is the same body of lecture notes that we've seen before. So we have loaded up the discrete RV library in R whenever you see the R sections. And there's a discrete RV function called E that is for computing expected values. So X was a random variable that we defined at some point. That corresponds to the Bernoulli random variable that we were talking about. S corresponds to actually the sum of two dice. So in this case, we should be doing 7 over 2 or something like that. If we were actually talking about the same S, but this is a different S. This is a sum of two dice. Two independent dice, by the way. Not just any two dice. Although I don't know how you make two non-independent dice. That would be really hard. N is, though, what we're talking about. And notice that the answer is approximate. We know that for this N, the P parameter was 2. So the number that results should be 2, but it's not 2. It's 1.999999. So be aware of that. It's giving us an approximate answer because it's only summing over a finite number of places. But you get the idea. You can tell that it's essentially doing the right thing. Okay, continuing on. Expectations are linear functions, and being a linear function is an extremely important property. And it's for that reason that we can say expectations are integrals. But that is a 60-40 idea right there. Instead, we're going to talk about how the expected value of ax plus b is equal to a times the expected value of x plus b. This is something that we can show. Watch. The expected value of ax plus b is equal to this. This, by the way, is this is basically h of x, where h of, let's say, s is equal to as plus b. So we can use some of those that expectation formula that we mentioned above towards the beginning of this lecture, and say that this expectation is equal to the sum over x ax plus b times the probability mass function of x, which is equal to the sum over x, and then we'll factor all that stuff together. We've got ax p of x plus b p of x, and then we'll break up the sum and say that this is the sum over x ax p of x plus the sum over x. Scroll down. The sum over x bp of x. Factor out the constants to say that this is a times the sum over x xp of x plus b times the sum over x p of x. And we can recognize what some of those sums are. For instance, this sum is the expected value of x, and this sum is the sum of the probability mass function over everything where it's positive. So this is going to sum to 1, and hence you get the result. A times the expected value of x plus b. Hence, it's linear. The variance of a random variable is given by, we'll call it var of x, which is equal to the expected value of x minus mu, where mu is just the expected value of x. We just don't want to write that again in there because it feels confusing. So we just put a mu in there. But basically, it's the mean squared distance of x from its expected value. So this actually does correspond very closely to the sample variance as well. If you could think of the sample variance as divided by 1 over n instead of 1 over n minus 1, you could say, we could argue as we did for how the sample mean is very similar to the population mean in terms of expected values, and say that this is a sample variance too. So, so this is something to notice. The Greek letter that's used to represent the sample variance is sigma squared. And like with the sample standard deviation, you can get the population standard deviation by taking the square root of the variance. It's just not as common to do so. All right. So there is actually a handy formula for computing the variance that is often easier than computing it directly. This formula, you may recognize this from when we were working with the did I say sample variance a second ago? I meant the variance or the population variance. But this formula resembles the formula for the sum of squared errors that we saw in chapter 1, where you have the mean of x squared minus the mean of x squared. Where hopefully you can tell from my inflection what's being squared. Okay, so the variance of x is thought of as the population variance and is denoted by varx, which is sigma squared, and the population standard deviation is sigma, which is the square root of sigma squared. Sometimes I'll write, though, the standard deviation of x because it's sometimes nice to do. All right, so our next example, compute the variance and standard deviation of the random variables listed in example 11. So if that's the case, let's start out with x. We already have the expected value of x, which was p, the expected value of s, which is 7 halves, and the expected value of n, which is equal to 1 over p. So as a reminder of what we have already. So now let's compute the expected value of x squared, which is equal to the sum from little x equals 0 to 1, x squared, f of x, because that's what I'm calling the probably mass function, which is equal to 0 squared times 1 minus p plus 1 squared times p, which is equal to p again. Hence, you get to say that the variance of x is going to be the expected value of x squared minus the mean of x squared, which is equal to p squared minus p, which we could be done right there, but people often like to factor this into p times 1 minus p. All right, next example in the case of s. So the expected value of s squared is going to be the sum from s equals 1 to 6 of s squared times probably mass function at s, which is 1 over 6 times the sum from s equals 1 to 6 s squared. This is something that we have. Actually, all right, you might not have seen this, a formula for the sum of squares in your previous algebra classes. Maybe you saw that, maybe you didn't. But there is, in fact, a formula for that, which I'm going to have to look up. Okay, so you have that the sum... let's use a different color for this. The sum from s equals 1 to n s squared is equal to n times n plus 1 times 2n plus 1 divided by 6. Okay, so using that here, we get to say that this is equal to 1/6 times 6 times 7 times 13 divided by 6. So those cancel, and that's pretty much all we can cancel. So we get to say that this is equal to 91 divided by 6. Therefore, the variance of S is going to be the expected value of S squared minus the mean of S squared which is equal to 91 over 6 minus 49 over 4. What is that number? 35 over 12. And you should have that the variance is always a non-negative number. In fact, the only time that the variance is ever equal to 0 is if the random variable is degenerate. That is, if it's effectively a constant. So it's unlikely that your variance is 0. And in the more general case, it's impossible for your variance to be negative. So if you ever ended up with a negative variance, then you've done something wrong. All right, for the final one, and this one is where things get weird. All right, and I'm going to zoom in for this one. Because this one is where things get really tricky. Because we're now working with the geometric case, and we need to compute the expected value of n squared. Okay, and that is equal to the sum from n equals 1 to infinity, n squared times the probably mass function at n, which is equal to the sum from n equals 1 to infinity. I'm going to go ahead and already do some simplification. We get p n squared 1 minus p to the power n minus 1. Now, how on earth are we going to compute that? Well, we're going to get really tricky is what we're going to do. So we're going to say that, let's zoom in even more. We're going to say, and you're not, all right, this is just so weird what's about to happen. According to my notes, it's actually advantageous to keep the p inside. So let's put the p back inside of this sum rather than factor it out. So we got a sum from n equals 1 to infinity, n squared p. All right. What's going to end up happening is we're going to end up adding 1. No, hold on. Subtracting 1 and then adding 1 again inside of that square. And leave everything else the same. And we're going to go do some calculations. And at the very end of them, the expected value... Oh, go away. The expected value of n squared is going to appear on both the left-hand and the right-hand side, left-hand and right-hand side of an equal sign. So after that happens, the thing is, though, on the right-hand side of that equal sign, it's not going to be just the expected value of n squared. It's going to be the expected value of n squared plus something times something. And when you have a situation like that, you're going to be able to solve for the expected value of n squared because you just have an algebraic relationship. And you're just going to have to see it and watch it happen in order to kind of understand. It's just at the very end, all of a sudden, what you're going to need pops out. This is one of those situations where it's a trick, and you're going to see the trick, and you might not understand the motivation for the trick, but someone did that trick once, and it seems to work. All right, so here we go. This part right here is a perfect square. A perfect square, so we can now write that part. I'm not going to write n equals 1 to infinity all the time. That's going to get annoying. So I'm just going to write a sum over n down here and say we've got n plus 1 No, not n plus 1. N minus 1. We've got n minus 1 squared plus 2 times n minus 1 plus 1. And then we've got p, 1 minus p to the power n minus 1. Yeah. Okay, and then this is equal to breaking up this part and breaking up the resulting sum. We get the sum over n, and we have n minus 1 squared, p, 1 minus p, power n minus 1, plus 2 times the sum over n, n minus 1, p, 1 minus p, to the power n minus 1, plus the sum over n of p, 1 minus p, to the power n minus 1. Okay, now we can start recognizing some stuff. The term on the very left-hand side, no, not left-hand, right-hand side, this term, this is equal to 1 because this is just the sum of the probability mass function. This term is the expected value of n minus 1. Okay? And then we get to say that so far, collecting our stuff, recognizing those substitutions, is the sum over n, n minus 1 squared p, 1 minus p to the power n minus 1 plus 2 times the expected value of, I'm going to write this as the expected value of n minus 1 because we have that linearity property that I proved a few minutes ago. And then we have plus 1. All right, and doing some even further simplification, we're able to recognize that the expected value of n is equal to 1 over p. So that means that this term that we're adding is going to be 1 over p minus 1. So we got plus 2 over p minus 2 plus 1. So this will be, so that means that this is going to simplify into plus 2 over p minus 1. And then we're going to take this n minus 1 and say, oh, well, that's a perfect square too. So this will be n squared minus 2n plus 1. All right, so we then get, oh, wait, actually, we don't want to do that. No, we don't want to do that. We do not want to do that. We don't want to do that. We want to do something even trickier. What we're going to do instead, all right, let's write in again what I have been omitting this whole time, that this is a sum from n equals 1 to infinity. But we're going to re-index this. We're going to re-index this and say, well, actually, this is the same as saying n minus 1 equals 0 to infinity. All right. And then replace all of those n minus 1s with, let's say, j. And say this is j equals 0 to infinity. So we get j squared. And the thing is, though, we're the first term in this sum, though, is going to end up being 0 because all right, plug in j equals 0. That means the first term is going to be 0 because 0 squared is 0. 0 times whatever is 0. So that means that the first term is actually 0. So we get to replace j equals 0 with j equals 1. Because, well, when you start at 0, you just add a 0 term. You're just adding 0 to the sum. So we get to start at 1. And this is now looking almost like the expected value, except for the power up here is wrong. It should be j minus 1 to have the probability mass function, but we've got j instead. Okay, so we'll replace that with j minus 1 plus 1. Okay, And to account for the plus 1, that means that what we need to do is factor out a 1 minus p. So, all told, we will have 1 minus p times the sum from j equals 1 to infinity, j squared p, 1 minus p to the power j minus 1, plus 2 over p minus 1. And that sum is what we started with. This term right here is the expected value of n squared. Oh, look at that. So we get to say that this is going to be 1 minus p times the expected value of n squared plus 2 over p minus 1. And as a reminder, at the very beginning of this long statement of equalities is the expected value of n squared. Oh, look at that. We can do some algebra now. For instance, we can subtract from both sides the expected value of n squared. And say that this is going to suggest that what is 1 minus p minus 1? That's going to be negative p. So we've got negative p times the expected value of n squared. We will subtract 2 over p and add 1 to both sides. Minus 2 over p plus 1. To get that this is equal to negative 2 over p plus 1. And then divide both sides by negative p. And now we get to say that this is equal to that the expected value of n squared is equal to 2 over p squared minus 1 over p. And there it is. That, by the way, is the expected value of n squared. I'm just writing it down again because it's not on my screen and because it was put on a separate line. That's what we need to compute. So, it then follows that the variance of n is equal to 2 over p squared minus 1 over p minus 1 over p squared, which is equal to 1 over p squared minus 1 over p, which is equal to p minus 1 over p squared. Wait a minute, that's... Hold it. That's... Oh, no, not p minus 1. 1 minus p. Okay. Otherwise, that would have been bad because I would have just computed a negative variance. So 1 minus p over p squared. Did I ask to... Did I say that we should compute the standard deviation too? It's not super hard to do. You just take the square root. But yeah, I did ask for standard deviations. So, okay, computing the standard deviations too. Like, that's super easy. You just take the square root of the variance. So the standard deviation of x is equal to the square root of p times 1 minus p. The standard deviation of s is equal to the square, 1/2 times the square root of 35 over 3. And for n, the variance, the standard deviation of n is going to be the square root of 1 minus p divided by p. That's an ugly looking p. All right, there we go. And in fact, there are functions for in this discrete RV library for computing variance and standard deviation. They're going to be V and SD respectively, and you can see this function computing the variance and standard deviation. Remember that this is not the same as we were talking about before. So we get to compute those things, and we get pretty much what we had. So, all right, proposition 10. The variance of ax plus b is equal to a squared times the variance of x. And the standard deviation of ax plus b is a times the standard deviation of x, or the absolute value of a times the standard deviation of x. Actually, this would probably be better to write in terms of that SD notation, to say that SD of ax plus b is equal to the absolute value of a times the standard deviation of x. So let's see this. Let's go ahead and prove this. So the variance of ax plus b. So the variance of ax plus b is the expected value of ax plus b minus, we should have the expected value of ax plus b here. Here's the thing though. The b's are going to cancel because expectations are linear. And the a's that a can be factored out in front of that expectation. So that means that a is going to be a common factor, and therefore the a can be factored out completely if we just square it. So we get to say that this is the expected value of a squared, and then we have on the inside x minus the expected value of x, which is equal to a squared expected value of x minus mu squared. Just remember that mu is the expected value of x, and that's the variance. So this is equal to a squared times the variance of x. All right, what do we then say for the standard deviation? We say that the standard deviation of ax plus b is the square root, is equal to the square root of the variance of ax plus b, which is equal to, after you do that algebra, the absolute value of a times the standard deviation of x. Because you're just going to take the square root of what I've highlighted in blue. Just take the square root of that, and you're good. All right, so there's that formula. One final note. There is nothing that says that expectations need to be finite or even exist. There are random variables out there that do not have finite finite expectations, and they may not even have like an infinite expectation. They might not have an expectation at all. Like, there's just no way to define it. Like, I guess technically an infinite expectation is considered undefined, but it's like you can't. But there's a sense in which it is defined. Like, infinite just means arbitrarily large. But even then, you might not be able to say that it's even infinite. It's just, it could be anything. There are random variables out there that don't have expectations. So let's actually see an example of this. This one's a fun one. This is what's known as the St. Petersburg game. Consider a game where a fair coin is flipped until it lands heads up. A player would earn $1 if the game ends with 1 flip, $2 if it ends with 2 flips, $4 if it ends with 3 flips, $8 if it ends with 4 flips, and so on. So basically your winnings are doubling every time this game goes on. The fair price of a game corresponds with the game's expected payout. What then is the fair price to play this game? And before I continue on, I would like for you to think about how much you think this game is worth and how much you would be willing to pay for it. How much would you be willing to pay to play this gambling game? What do you think is the fair price? You might be surprised. So let's calculate it. We're going to say that n is following a geometric distribution with parameter 1/2, because that's how you should. We're flipping a coin until we get heads. And this geometric random variable, it's a fair coin, is what will model such an experiment. So then, what would be our winnings? It would be 2 to the power n minus 1. Because if you get one flip, that would be, you should get $1. So n minus 1, so that'll be 1 minus 1, so 2 to the power 0, which is 1. If it took 2 flips, that's 2 minus 1 in the power, so that'll be 2 minus 1. So the power will be 1, so we get 2 to the 1, which is equal to 2. And if we had 3 flips, that's going to be 2 squared, so we'll get 4. So this is in fact corresponding to what we think it should. All right, then, what we were computing is the expected value of 2 to the power n minus 1. Which we can make our lives a little bit easier by saying that this is 1/2 times the expected value of 2 to the power n. And we know how to compute the expected value of 2 to the power n. So we'll say this is 1/2, and we have the sum from n equals 1 to infinity, 2 to the power n, and then we write down the probability mass function for the geometric random variable, which is 2 to the power negative n. Or which is the same as, that's the same thing as 1/2 to the power n. So n minus n, that's going to be 1. So this is 1/2 times the sum from n equals 1 to infinity, 1, which is equal to infinity. This game has infinite value. You should pay $1 to play this game. You should pay $10 to play this game. You should pay $100 to play this game. You should go to the bank and take out a loan for $1 billion and play this game. Because this game has infinite expected value, any finite price is a bargain. And yet, no one in their right mind would ever do that. No one thinks that this game is really worth anything. People think this is a terrible game. And why that is somewhat remarkable. It gets to the point that once you've earned $1 million, another $1 million doesn't seem that great. I mean, it's pretty good to go from $1 million to $2 million. That's nice. Same thing with $1 trillion and $2 trillion. Like, you're gaining $1 trillion when you go from $1 trillion to $2 trillion, but it doesn't really feel like it. Like, you already got everything you want at $1 trillion. The other $1 trillion is just gravy. So basically the point is, with this game, the way to rationalize the paradox of this game, the fact that its expected value is infinite, but no one wants to pay that, is that people are not actually thinking about the winnings in terms of literal money. They're thinking about it in terms of the utility they get from that money. And people know that the next $1 trillion is not as good as the first $1 trillion. So in that case, this game actually doesn't look very good once you actually account for decreasing utility from your winnings. That's how you resolve the paradox. You resolve it with economics. That's it for this video. We have been talking about general ideas in random variable theory. Let's call it random variable theory. That seems like a good word. Probability mass functions, cumulative distribution functions, all that stuff. These are general things that all discrete random variables have and expectations, excluding the cases where they don't exist. They're generally around 2. So now we're going to start looking at specific examples of common families of random variables that probabilists care about. The first one being the binomial probability distribution. A lot of the ideas also that we talked about here actually transfer over to the continuous case. When we're talking about continuous random variables, they have analogs that are pretty similar. What you do is you replace probability mass functions with probability density functions, and you replace sums with integrals. So that's how you go from the discrete to the continuous case. But everything else applies. Everything else is the same. Variances, expectations, CDFs, probability mass functions become probability density functions, which are pretty similar. So these are all basic ideas that you're going to see over and over again when talking about probability. And from this point on, for the remainder of this chapter, we're going to be looking at specific examples. Because the advantage of talking about a family of distributions is once you have a family of distributions, you get to talk about it once, and then you get to generalize to lots of different cases. And it's like the expected value. If you're able to recognize a random variable as being a particular case of a binomial, then there's an expected value formula available to you. And you don't need to compute it by hand. You shouldn't compute it by hand because it's going to be a pain. You can just use that formula, and it's really easy. Same thing with a lot of these other random variables. Hypergeometric negative binomial. They would be a pain for you to do over and over again, but because we've identified a family of random variables with common characteristics, someone computed a formula, and now you get to use that formula. And that's really nice. That's really nice. Okay, so I'll just leave it at that. We will end the study of this section, and I will see you later. I will see you when we start talking about binomial random variables.
For our next section, we are now discussing the binomial probability distribution. So a binomial experiment is an experiment that satisfies the following requirements. The experiment consists of n Bernoulli trials that end in either success, which we will denote S, or failure, with which we will denote F. The trials are independent, and for each trial, the probability of S is 1 minus the probability of failure, which is some number p between 0 and 1. In the case of p being 0 or 1, this random variable is degenerate. Or the resulting random variable, I guess I haven't mentioned a random variable yet, but that random variable would be degenerate because you'd either always get success or always get failure. So we don't consider that situation. So we can think of the outcome of an experience as a sequence of S and F, such as SS, FSF, which in that case, the duration of the experiment would be n equals 5. So the binomial random variable is the associated random variable with binomial experiments, and what a binomial random variable does is it will count the number of successes in the experiment. So x of omega is equal to the number of s in omega. We should probably not be why did I write that as a set? That doesn't make any sense. It's not a set, right? It's just a number. We will then say that x follows a binomial distribution with parameters n and p. So for example, given that sequence of s's and f's that we saw before, the binomial random variable would evaluate to 3. So we denote the probability mass function of x with lowercase b, although that's more notation for this class. I don't really see notations that we use in this class elsewhere because people know what they're talking about when you're reading papers and stuff. So they don't bother to come up with some special notation for it. Anyway, here we have the probability mass function for binomial random variables. This is 0 for x that's not an integer from 0 to n. And for x between 0 and n, it can in fact be computed that the probability mass function for a binomial random variable with parameters n and p is equal to n choose x, p to the power x, times 1 minus p to the power n minus x. So here's some further explanation of this formula. In this situation, there are x successes out of n trials. Okay? The probability of each of those successes is p. They are independent trials, so you multiply p x times. And you would multiply 1 minus p n minus x times. This is accounting for the probability of each of those failures that occurred.
And here's the thing. That will get you the probability of, let's say, the sequence SSFSF. That would get you the probability of getting that particular sequence. But the thing is, there's a number of sequences where you could have 3 successes and 2 failures. For example, we could have SSSFF, or the other way around, like FF, SSS, and so on. So we need to pick the positions in which successes occur and failures occur. Or we'll just simply pick the position of successes. And if we pick the position of successes, we then know where all the failures occurred in the sample, or in this string. So we end up with n choose x, meaning out of n positions, choose the x positions where successes occur. The CDF of this random variable x is given next. The probability, no, I don't want black, blue. The probability that x is less than or equal to little x is equal to the CDF of the binomial random variable, which is equal to the sum from I equals 0, because you could potentially have 0 successes in your sample. So from I equals 0 to x rounded down, the probability mass function at I NP, which is equal to the sum from I equals 0 to x rounded down, n choose I, p to the power I, 1 minus p to the power n minus I. And it looks like all I did was write down sum over the probability mass function, and that is what I'm writing down. I didn't simplify this any further. There's not really a whole lot more that you can say with this formula. Like, there's no fun little algebraic simplifications that you get. All you're just going to say is sum up over the probability mass function. And for that reason, you're, with the exception of cases like some strange n or p, historically in this class, I would have students use the tables that were provided in the back of the textbook to work with the probability mass function. Or no, not the probability mass function, the cumulative distribution function. Now, seeing as I am teaching this class online at the moment, I don't necessarily see why I should, like, I'm telling my students that they can use R for pretty much anything, even on quizzes and even on tests. So for that reason, I'm just not going to bother with working with the textbook and using the tables in the back of the book in these videos. Instead, I'm just going to use R to get the CDF for binomial random variables. Although there may be some situations where, like, we might have the input x, we might replace the input x with, say, 1. Okay, if it's 1, you don't necessarily have to use R. Maybe I'll tell you not to look up the number and not to use R and ask you to compute the CDF, just because there's only 2 things you're going to end up having to compute. Only 2 things are going to get plugged in. So, but that's kind of what we're working with right now. I might recycle these videos in the future, and if I do, be aware. All right, so one thing that's nice in these upcoming sections is I'm not going to go through the trouble of computing expected values using that summation formula, using like x times p of x, a sum over all x where p of x is not 0. I'm not going to bother with that anymore. I'm just going to tell you what the expected value for this random variable is. It's np. No, it's just np. It's np. I was jumping ahead of my head to the variance. The variance of this random variable x is equal to n times p times 1 minus p, and the standard deviation of x is just the square root of the variance. I'm going to draw your attention to something. One way you can view binomial random variables is as the sum of Bernoulli random variables. In fact, you could probably play around... Oops, I didn't want to erase. Have a look at this probability mass function formula and show, for me, that if you choose an n equal to 1, the resulting probability mass function is the probability mass function of the Bernoulli random variable. That is, in fact, the case. So that's something to look into. But okay, I'm saying that binomial random variables are the sum of n Bernoulli random variables, the expected value of n independent Bernoulli random variables. That's critical. If that's the case, remember that the expected value of a Bernoulli random variable was p, and the expected value of a binomial random variable is n times p. So you're saying, in a sense, that we add up p n times to get the expected value? Intriguing. And actually, remember that the variance of a Bernoulli random variable was p times 1 minus p. Well, now we're adding up n of those, and we get np 1 minus p for the variance? Intriguing. So, that is something to notice. And also these expected value, well, I don't know necessarily about the variance being something very easily interpreted, but the expected value certainly is. It's saying that if there's a probability of a success happening, let's say that the probability of success is 0.1, and you do this experiment 10 times, then you expect to see one success in your sample. Or if you do this experiment 100 times, you expect to see 10 successes in your sample. So it's actually a rather easily interpreted quantity, this n times p quantity. Okay, and I mention here that select values of b, x, and p are given in table 8.1 of the textbook, but in this video, I'm just going to use R. Okay, moving on. You flip a fair coin 10 times. All right, so we should start filling out with numbers. You flip a fair coin 10 times, there's going to be a binomial random variable showing up. So fair coin suggests that the p parameter of this binomial random variable is going to be 1/2. Presumably what we're doing is counting the number of heads. And if we're counting the number of heads, then the resulting random variable is binomial, and the n parameter of that binomial random variable will be 10. All right, what is the probability you see exactly 4 heads? Do so without using a table. The probability that this random variable x, which is following a binomial distribution with parameters n is 10 and p is 1/2. So the probability that x is equal to 4 is going to be 10 choose 4, 1/2 to the power 4, and 1/2 to the power 10 minus 4. Okay, you're probably noticing, well, okay, we got 1/2 to the power 4, 1/2 to the power 10 minus 4, so that's the same as 10 choose 4, 1/2 to the power 10. And that's just basically because 1/2 is equal to 1 minus 1/2. So maybe I should write 1 minus 1/2 to be a little bit more clear. Like that's the reason why. But if you had instead of 1/2, we said the probability of getting heads is 0.1, then this would be then thinking about the probability mass function this way would have been more correct. Or would have been correct. It's not more correct because the other one is incorrect. All right. So, actually, we're going to compute this thing by hand. So we're going to say that 10 choose 4 is 10 factorial divided by 4 factorial times 6 factorial. And we have 1 over 2 to the power 10. That's 1/2 raised to the power 10, which is equal to 10 factorial divided by 4 factorial times 6 factorial. We've got 10 times 9 times 8 times 7 over 4 times 3 times 2 times 1. And then this is all multiplied by 1/2 to the power 10. And the 4 and the 2 will cancel out with the 8, and the 3 will cancel out with the 9, leaving us with 3. So that gets us 210 over 1024. That's the 10th power of 2. Which is equal to, since there is a 2 in common, 105 over 512, which is approximately equal to 0.2. Okay, so that's the answer to that one. If x follows a binomial distribution with parameters 10 and 0.5, compute the probability that 4 is less than x, which is less than or equal to 6. So we've actually got a couple ways we could do this. Let's do this without the table. The probability that 4 is less than x, which is less than or equal to 6, is equal to the probability mass function at 5, because you don't include 4, plus the probability mass function at 6. Which is equal to, it's going to be 10 choose 5, and we know we're just going to end up with 1/2 to the power 10 in the end. But in general, if our parameter were not 1/2, we should probably reason this way. So you got 10 choose 5 plus 10 choose 6. I guess we switched to green. 1/2 to the power 10. And that means what we need to compute now is 10 choose 5 and 10 choose 6. We already know that 1/2 to the power of the 10 is 1 over 1024. So 10 choose 5, that's going to be 10 times 9 times 8 times 7 times 6 divided by 5 times 4 times 3 times 2 times 1. And 10 choose 6 is equal to 210. And that's because 10 choose 6 is equal to 10 choose 4. I'm going to leave it up to you to figure that out. I believe that was a problem in the exercise set. But yeah, that's a thing. So now what we need to figure out is 10 choose 5. So we've got the 5 and the 2 canceling out with the 10, the 3 canceling out with the 9, reducing it to 3, and the 4 canceling out with the 8, reducing it to 2. So we've got in the numerator 3 times 2 times 7 times 6, and 3 times 2 times 7 times 6 is 252, I believe. Yeah, so it's going to be, yeah, that's 252. So this quantity evaluates to 252. So we will get, for our probability, 252 plus 210, which is going to be 462 divided by 1024, which that's around 0.5 after you do some rounding. We could also do some reducing of that fraction too. Now that said, there was an alternative way we could have computed this quantity, which was to say that this is equal to the CDF at 6 minus the CDF at 4. And then what's left to do is get the CDF at 6 and 4. All right. Well, let's get that. I'm going to have to boot up an R session. All right. So we've got P binom. That's the function that is responsible for working with binomial random variables. And we're going to give P binom, what are we going to give it? Right. So we're going to give it 6. Our other parameters are size, that's 10. And prob is equal to 0.5 minus P binom, which is going at 4, size equals 10, prob equals 0.5. Yeah, about 0.45, which rounds to about 0.5. Which, for what it's worth, I said it was approximately 0.5 when we were doing stuff by hand, and that was because we were rounding. I knew I was rounding when I was saying that's about 0.5. So, well, let's go ahead and write down that more exact answer. Say that this is approximately 0.45. Okay. Next example. Compute the probability that 2 is less than or equal to x, which is less than or equal to 4. We could do this by summing up over the probability mass function, but now I really don't want to do that. I've got better ways to spend my time. So I'm going to instead say that this is equal to the CDF at 4 minus the CDF at 2 minus 1. Remember, we have to do the 2 minus 1 because we need to include the 2 in our region. And the only way to do that is if we do 2 minus 1. Okay, and the other parameters are 10 and 1/2. And, you guys know what 2 minus 1 is. This is equal to 1, which is going to be, well, let's compute this. So P binom at 1 minus P binom, or other way around, actually. So we got 4. All right, so 0.366. So approximately equal to 0.366. What is the probability that you see more than 7 heads? Strictly more. So this is the probability that x is greater than 7. That is, well, the converse event, or the complementary event to x being greater than 7 is x is less than or equal to 7. So this is going to be 1 minus the probability that x is less than or equal to 7. Since, remember, the probability of a complement is 1 minus the probability of A, the complement of the set x is greater than 7 is x is less than or equal to 7. So then we get that formula. So this is going to be, this is equal to 1 minus the CDF at 7 with parameters 10 and 1/2. And now we need to compute that, and we're going to turn to R for that. So this is 1 minus the CDF at 7, size equals 10, prob equals 0.5. So the probability is about 0.05. Let's say 0.055. So this is approximately equal to
0.055. Now, I should probably mention something else about how the software is working. We could have done instead p binom 7 size equals 10 prob equals 0.5, and there's an additional parameter that all of these p functions have, which is lower.tail. Lower.tail, let's set that equal to false. That got us the same thing. So basically these p binom functions, by default, they're giving you the CDF, but they can also give you 1 minus the CDF if you set lower tail equals false. If you were to ask the developers for these functions, they would say that rather than doing 1 minus the CDF or 1 minus p binom or whatever, you should use the lower tail equals false parameter. The reason being that you're going to get less numerical error if you're using the lower tail equals false parameter. Because numerical error is very much a thing. Like, we care, whenever we're using software to compute numbers, we care about numerical error. And it turns out that setting lower tail equals false, that results in less numerical error. I don't really know why. I'm guessing it's because they can do some more optimizations or some other fancy numerical tricks. Thing is, as an instructor, I like to make sure that people are thinking, like, this expression or this relationship, like, I really want students to understand that. And it's very easy to just lose that under the easiness of this function and this notation. So I don't know how frequently I'm going to do that. And also for whatever it's worth, sometimes when I'm writing my own functions for probability, I don't always include that parameter myself, just because I don't have it. I don't really know what the developers are doing to make sure that lower tail equals false gets you more accurate answers. So also, by the way, if you're watching this in the future, hello future person, if you're watching this in the future and you're using a table because I told you to, you're using a table for these calculations, you don't have access to the probability that x is greater than 7. You only have access to the probability that x is less than or equal to 7. So being aware of how this stuff is working, or at least being aware of this relationship that I've underlined in blue, still matters a great deal. All right. So continuing on, compute the expected value of x, the variance of x, and the standard deviation of x. All right. So the expected value of x, let's see. All right. The expected value of x is n times p, which is 10 times 1/2, which is equal to 5. All right, simple enough. The variance of x is n times p times 1 minus p, which is 5 times 1/2, which is 5/2, or 2.5. The standard deviation of x is going to be the square root of 5/2. And I don't know what that is off the top of my head. So we can just leave it like that. That's fine. All right. R functions that are doing this stuff. Well, I think we just did it. So some of this is completely redundant. Here I actually created a random variable using discrete RV, which presumably is loaded up. So I create a random variable x to represent the x that we were talking about before, and compute its expected value, variance, and standard deviation. These are basically the same as what I had before. I also plotted its probability mass function. This is what its probability mass function looks like. Okay, next example. A manufacturer of widgets sends batches of widgets in giant bins. Your company will accept a shipment of widgets if no more than 7% of widgets are defective. The The procedure for deciding whether a shipment is defective is to choose 4 widgets from the batch at random without replacement. If more than one widget is defective, the batch is rejected. What's the probability of rejecting the batch if 7% of widgets are defective? Model the process using a binomial random variable. So we're going to assume that there are, in fact, 7% of widgets. And actually, the argument being used in this problem is kind of suggesting the possibility. Well, actually, the procedure being described in this problem is basically a hypothesis test. And we're going to talk more about hypothesis testing later in a later chapter. But basically what you do when you're working on the mathematics of a hypothesis test for computing p-values and all that stuff, you assume that the null hypothesis is true. So the null hypothesis is that 7% of the widgets are defective. So in this case, we assume that 7% of widgets are defective, in which case the distribution of the random variable x is going to be, well, let's see, how many widgets did they pull out? 4. So n is equal to 4, and p is equal to 0.07. Okay. So, also there's another wrinkle here. The bin of widgets has a finite number of bins. Not finite number of bins. Has a finite number of widgets. But this binomial random variable is not supposed to work in that situation. See, if there's a finite number of successes in this possible in this finite population, then an implication of that is that you don't have independent successes and failures. Because if you pull a success out of the population, you cannot pull that success again. And presumably in this example, when you're checking the widgets, you pull out a widget, you check it, but you don't put it back in the bin for you to draw again. No one ever does that. So actually, we don't have independent Bernoulli trials. So we don't have a sum of independent Bernoullis. We don't have independent trials, which means that technically this random variable should not be a binomial random variable. Actually, the random variable that is more accurate for this context is what's known as a hypergeometric random variable, which we'll talk about in a later section. Thing though is, if the population is large enough relative to how many successes there are in the sample, like if there's 1 million widgets and 7% of those widgets are defective, then that means that about 70,000 defective widgets exist in the sample, or in the population. My apologies. In which case, the numbers are so large that basically you can treat this as a binomial experiment anyway, because the difference between the binomial random variable and this more accurate random variable, the hypergeometric random variable, those differences are negligible. So you get to cheat. You get to use the simpler binomial random variable as opposed to the more complicated hypergeometric. Okay. So let's carry on then. They want to know what is the probability of rejecting the batch if 7% are defective, if more than one widget is defective. Okay, with this problem, we actually need to translate out, because this is a word problem. And by the way, in stats classes, I absolutely love to ask word problems. So many word problems. Because statistics is so applied that it just feels inappropriate to not be asking word problems. It's such an applied subject that you have to be asking them. Okay, so what corresponds to rejecting the batch? You reject the batch if there's more than one defective widget in your sample. So more than one, that means greater than one. And our random variable for tracking the number of defective widgets that we found is x. And I guess
All right, a student might find it, wait a minute. You're calling a defective widget a success? Yes, it's mostly for the language. All right, so this is the probability we want to compute. We want to compute the probability that x is greater than 1, which is equal to 1 minus the probability that x is less than or equal to 1. And at this point, you could say, all right, let's go to R and compute this. And I'm going to say, no, we're not going to do that. We're going to instead compute this thing by hand and say that this is going to be the PMF at 0 for parameters 4 and 0.07 plus the probability mass function at 1. Oh, I'm sorry. I need to say that this is equal to 1 minus parentheses, all that stuff. Okay. All right. There we go. That's correct. And now we need to compute each of those probability mass functions. Okay, so the probability mass function at 0 is going to be, we've got 4 choose 0, and 4 choose 0 is 1. There's only one way to choose none of the 4 things in your little group, and that's to choose all the other ones. There's only one way to do it. So 4 choose 0 is 1. Next up, we've got what have we got? So 0.07 to the 0th power and 0.93 to the 4th power. B1 for 0.07 is equal to 4 choose 1, which hopefully you know is 4. You can at least reason about it. It's like, okay, how many ways are there to pick one thing out of 4? We'll pick one of those 4 things. All right, there we go. So there we go. So then we got 0.07 to the 1st power, 0.93 to the 3rd power. And after this, you go to a calculator to compute those numbers. I think I actually computed them rather accurately in my notes. So let's see. What did I have? Okay, so what I'm seeing here is that this is equal to so the top one is equal to 0.748052. That is an exact number. I got a little carried away with the accuracy. And the second one is 0.22522. And that means that we're going to have that this quantity here, that ultimately is what we're trying to compute, is equal to 1 minus 0.748052 plus 0.22522, which is equal to 1 minus 0.973272. 3272, which is equal to 0.026728. All right. Next up. Oh, yeah, there it is. Excuse me. My apologies, I had to sneeze. Okay. Next example. This one's fun. I claim that I can make 80% of my free throw shots when playing basketball. You plan to test me by having me shoot 20 baskets. If I make fewer baskets than a specified amount, you will call me a liar. The threshold amount of baskets is chosen so that the probability I make less than this amount, given that I am, in fact, an 80% free throw shooter, does not exceed 5%. What is the threshold amount? All right. Additionally, compute the mean and standard deviation of the number of shots I would make if my claim is true. Okay. Let's do this. Let's do the second part first because that's easier. The first part is going to require a conversation. So the expected value, we'll say, S is following a binomial distribution with parameters. I'm going to shoot 20 baskets. Yeah, so N is 20 and P is 0.8. Because, all right, this is again a hypothesis testing type problem, in which case you're assuming that I am in fact an 80% free throw shooter. So the expected value of not X, because I decided not to do X, of S is going to be 0.8 times 20, which is equal to 16. So you expect me to make 16% of my baskets. Did I ask for standard deviation? Yes, I did. So the variance of this random variable is going to be 20 times 0.8 times 0.2, which is equal to 3.2. And the standard deviation of S is equal to the square root of 3.2. Which I don't know off the top of my head, and I'm just not gonna bother. Okay. Alright, so that was the easy part. Now for the hard part. I have asked that you pick a threshold amount of baskets so that the probability I make less than this amount, given that I am in fact an 80% free throw shooter, does not exceed 5%. Alright, so we will call this threshold amount, we will give it a name. The threshold amount, we will call this quantity K. Alright? I'm asking you to find a K such that the probability that S is, let's see, so if I make fewer baskets, so S is less than K, this number needs to be at most 5%. So this needs to be at least 0.05. Well, at most 0.05. Actually, there's going to be a number of possible Ks such that it's less than 0.05, but we're going to say that this is the largest possible K, such that this probability is less than or equal to 0.05. K is a constant here. We just don't know what it is. S is a random variable. Let's go ahead and play around with this expression some more before continuing on. This is saying that the probability that S is less than or equal to K minus 1 less than or equal to K minus 1, that's going to be less than or equal to 0.05. All right, so by doing that, I have the CDF on the left-hand side of the inequality and 0.05 on the right-hand side. So what we need to do now is basically a reverse lookup. We're looking up a number such that the CDF is less than or equal to 0.05. The largest number possible such that the CDF is less than or equal to 0.05. This is similar to the notion of quantile, because so you have a probability that a random variable is less than or equal to, let's say, 10%. Then the 10th quantile is that number. So this is actually related to the notion of quantiles. The unfortunate thing, though, is that what we're talking about are discrete random variables, which adds this complication in that it's possible that the CDF, in fact, not just possible, it's quite likely that the CDF never actually equals 0.05. If it were, in fact, equal for the CDF to equal 0.05, then we would say, all right, pick a K minus 1 such that the CDF is equal to 0.05. The only thing, though, is that's not actually likely to be the case. It's likely that the CDF never actually reaches 0.05. In fact, let's now go to R. So let's look at, so we got the CDF. The CDF is, so possible values for this random variable are from 0 to 20. So we're going to ask for the CDF's values for all numbers between 0 and 20. Size is equal to 20. Prob is equal to 0.8. Oh, it's not very helpful. All right, I think that if we were looking at the textbook, we would be rounding to 3 decimal places. So digits equals 3. All right, we're going to do this just because, like, what we have up here is scientific notation, which may be more accurate, but also it's hard to read. So we're going to round to 3 decimal places and work with this. So this is the CDF. And what we're looking for is, we would go, let's actually give this vector a name. So we'll call it CDF. And we'll say names CDF will be 0 to 20. So now let's print out CDF. Okay. All right. So. What we're looking for in this is a quantity where the CDF notice that the CDF is increasing as we increase the input to the CDF, right? Our CDF is increasing, and we want to find the largest number that we can put into the CDF such that it doesn't exceed 0.05, and that number is 12. Because at 12, the CDF is going to be 0.032, and at 13, the CDF is going to be 0.087. So it crosses that threshold at 12, suggesting that k minus 1 equals 12. And then we add 1 to both sides to suggest that k is equal to 13. That is, if I make less than 13 baskets, you're going to call me a liar. What is 13 divided by 20? That is 0.6. So that's 0.65. So if I make 65% or less than, if I make less than 65% of my baskets, you're going to call me a liar. The principle being, the logic being that is such a rare amount. It's so unlikely for you to score less than 65% of your baskets if you were, in fact, an 80% free throw shooter, that we're actually going to say it's more likely that you're lying than you're actually telling the truth. Or at least it seems unreasonable to continue to believe that you are still telling the truth. So so that's how you would use, like, the CDF. If you were using the textbook, you would use the CDF this way. You would scan the CDF. For some reason, my mouse stopped working. I don't know why. This is a super cheap computer. You would scan the CDF until eventually you crossed over that 0.05 threshold, and then take whatever number got the CDF to just below that threshold. So if I had switched this to say, all right, it needs to be less than or equal to 0.10, then we would go to 13. We haven't crossed 0.10 yet. We would go to 14, but then we would cross. So we would say, all right, the threshold amount is 13. Let's say that I said instead 0.01. Actually, 11 is probably not what you would choose because you know that we're rounding here. So you would go with 10. So, because you know that actually, well, I don't know. What was 11? So if we look back at the original vector, that's a bit more accurate. That doesn't have any rounding. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Next one. Oh, actually, it's rounding up, so you could choose 11. Yeah, 11 would be fine. So, yeah, it doesn't always round down. So that's what you would do. You would just kind of reverse look from the CDF, especially if you're using the book. Or you could use QBinom. We'll put in 0.05. Size equals 20.
prob equals 0.8. You could have used, okay, what exactly is QBinom doing? It might be doing something else. It might be saying, okay, you exceed it, because... So we actually might need to do QBinom minus 1. Let's look at the documentation for QBinom. Oh. I think you just... Yeah, you would just have to recognize... Alright, so... it's going to give you some details somewhere... Okay, so it says right here, the quantile is defined as the smallest value x such that f of x is greater than or equal to p, which is actually different from how I just defined it. So R's definition of what a quantile is for discrete random variables is different than what I just said. So being aware of that, you would actually have to take whatever QBinom gave you and then do minus 1 to get the right answer. Okay? But, alright. Or, I mean, I don't know. Like, there's so many different ways to possibly think about it and say, okay, the QBinom that R actually has is effectively giving you this quantity right away, so you don't have to work with the CDF. That's another way you could possibly think about it. All right, so by the way, what we're basically saying is that if you ended up shooting a number of baskets such that you ended up in 11, 12, such that you ended up in this region, it's so unlikely if you were in fact an 80% free throw shooter to end up in this region, I'm justified in saying you're a liar. How unlikely is it? Well, it's actually 3.2%. It's so unlikely that we would just call you a liar, because if you were in fact a free throw shooter, you should probably be ending up in the other region. An 80% free throw shooter, my apologies. I'm always confusing my words. Okay, so that's it for the binomial random variable. And in the next section, we will be talking about the hypergeometric and negative binomial distributions. All right, so I will see you there. We are now on to the last section of this chapter, discussing the Poisson process and the Poisson probability distribution. So, X is said to follow a Poisson distribution with parameter mu, or if the probability mass function of X is given by P of X parameterized by mu, this is equal to e to the power negative mu, mu to the power x over x factorial for x being a member of the set 0, 1, 2, and so on. So in other words, if x is a whole number, then this is the probability mass function, otherwise it's 0. So the first question you may ask, is this a valid PMF? The answer is yes. And why is that? Well, let's sum the probability mass function from x equals 0 to infinity. We got P of X parameterized by mu. This is equal to the sum from X equals 0 to infinity, E negative mu, mu to the X over X factorial. The e to the negative mu part, that is effectively a constant, so that can be pulled out. So we could say that this is e to the negative mu, and then we have the sum from x equals 0 to infinity, mu to the x over x factorial. And that part, which I have highlighted in red, that is e to the power mu. Why? Calculus 2. This is the, if I remember right, the Taylor expansion of the function e to the power x. So this is coming from calculus 2. But yeah, that evaluates to e to the mu. Hence, we get e negative mu, e to the power mu, and that equals 1. And furthermore, this probability mass function is positive everywhere.
So we get this is a valid PMF. So, Poisson random variables. If x is following a Poisson distribution with parameter mu, then the expected value of x is equal to mu, and also the variance of x is equal to mu. So, that means that we are parameterizing Poisson random variables by their mean. So in your book, if you're using the Devore book, table 8.2 contains the CDF of select Poisson random variables, or select Poisson distributions. In R, the functions that are responsible for handling Poisson random variables, are dpois, ppois, qpois, and rpois, handling probability mass function, CDF, quantiles, and random variates. So in other words, creating random instances of Poisson random variables. And they will be parameterized by their mean. So the Poisson distribution describes random variables that follow the Poisson process. So here is the intuition of Poisson random variables. They are tracking how many times how often a quote-unquote rare event occurs within a finite span of time. So, which isn't at all clear from looking at this probability mass function that would be, in fact, be the interpretation. This is more of a limiting result. This footnote that I have right here actually gives a little bit more justification as to why this is the case. But you can think of it as, all right, we have some rare event. I have a favorite example that was used by my 3070 instructor. Maybe I'll just pull up his webpage for you. He's got some interesting stuff on his webpage that even now I kind of look back to it and I think about it and I kind of want to update it. I think it could be updated, but there's some interesting stuff there, genuinely. So math.utah.edu/Treberg. His name was Andres Treberg's professor at the U. Not actually a probability professor. That's not his area of expertise, although he's taught Math 70 a few times and Math 3070, sorry, and Math 3080 a few times. And like he's interested in statistics, but he is a what is that area of study of his? I think it's like analytic geometry. I think that's what he studies. So I wonder what happens if I just go straight here. We could probably find from here his 3070 page. Yes, I think this is it. Math 3070 fall 2013. Math 3070 fall 2012 was that was the class that I took. This was my webpage. This is where I went to find his stuff. So, yeah, I took Math 3070 in this class, I think. I'm pretty sure that's true. All right. If I scroll down, the supplementary materials. Oh, yeah, so here's a Simple R, by John Verzani. This is the lab textbook for the R lab. And several example problems. He's got this one. Let's find it. Let's see. Prussian? No. Poise. Let's see. Is this it? I think this is it. Are there horse kicks? are people getting kicked by horses? That's what I want to know. I think this is it. I don't think so. I don't think this is the horse kick example, but the horse kick example is fun.
let's see. Oh, why won't it close that webpage? If we try horse, come on. Aha! There it is. There it is. The horse kick example. Yeah, I love this one. Yeah, so have a look at this. But basically, it turned out that in the Prussian army, you can model the number of people who died from horse kicks with Poisson random variables. That Poisson random variables actually do a good job of modeling stuff like that. But I also had, as potential examples, I'm not entirely sure how accurate this is, but you could maybe think of the number of calls that a call center is getting in a day, or the number of points that's scored by a team in a game, as Poisson random variables. So, and also as being a Poisson process. A Poisson process is a bit more general than that. So a Poisson process is a stochastic process. Stochastic processes are not the subject of this class beyond this little description. I think another thing that could be considered a Poisson process, or that could be modeled by a Poisson random variable, is, let's say you have some radioactive matter, and the number of is it atoms? I'm not sure. I'm not very good at physics, but some particles are leaving the radioactive mass, and the amount of particles that are leaving the mass over some period of time can be understood as a Poisson random variable and also as a Poisson process. So I have this R code that's meant to simulate a Poisson process, and with a Poisson process, the time at which a particle, or the time at which the process jumps is random. So there are going to be random times at which the process increases its value by 1. So it will jump. So you'll wait for a period of time, and then suddenly the process will jump, and basically something has left. And then you'll wait a little longer, and something else has happened. Maybe you could imagine this as being points in a game, maybe a basketball game. Although you could probably see why it's a little bit inaccurate to view points in a basketball game as a Poisson process, because there's no way that you could. Well, I guess this is possible if maybe you said both teams. If you're counting like total points scored by either team, I don't know. It seems unreasonable though. But basically at random times, this process is going to jump by 1, and the value of the process is going to increase. And basically, at any fixed time, the value of the process at a fixed time, so you fix it at 2 or something, and the value of the process at that time can be modeled by a Poisson random variable. So, yeah, that's hopefully that gives you some idea of what they're describing. How often some event occurs over a fixed period of time, which in principle that event could be unbounded. There's an infinite number of it could happen. Like, there's no upper bound on how many times this event could happen. It can happen an infinite number of times. There's, well, okay, maybe not literally infinite, but any large number of times. It's highly unlikely that it will be very large, but there is no upper bound, right? So you're not going to restrict it. Like, the number of points that you could score in a basketball game, like, there's no limit on that. No one will just end the game. Well, I don't know, maybe, but that seems rather academic. But yeah, so this is going to be a random variable that is defined. Hello, everyone. We are now on the next chapter on continuous random variables and probability distributions. Continuous probability models are another major class of probability models. In the previous chapter, we saw models for discrete random variables. With discrete random variables, there was either a finite number of possible numbers this random variable could take, or it was countably infinite. For example, the whole numbers were possible. In this situation, Not only are the number of possibilities infinite, they are uncountably infinite. So these probability models allow for any real number within some range. It could be within a range a to b, or a to infinity, or 0 to infinity, or negative infinity to infinity. So any real number, any of those could be possibly taken by the random variable. So as a consequence of this, we're going to change some of the notions that we had with discrete random variables, but not by much. For example, the probability mass function is going to be replaced with the probability density function, which is what we're going to be talking about right now. And the CDF is still defined the same way, but it's going to be computed a little bit differently. Instead of it being involving a sum, it's going to involve an integral, and expectations are also going to involve integrals. Basically, whenever you would add numbers with discrete random variables, you integrate with continuous random variables. So this is where your calculus knowledge is going to be tested. One nice thing, though, about continuous random variables, though, is that when you're working with continuous random variables, the probability that that random variable is equal to any particular number is always 0, which is the reason why we have to have integration and density functions. So the probability that x is less than x is the probability that x is less than or equal to x. And admittedly, it is a little strange that the probability that this random variable is equal to a particular number is 0. It's somewhat strange because when you go to your random number generator and ask this thing to produce a number, it gives you a number. But the probability that you got that number was 0. So events that are happening with probability 0 are happening all the time whenever you're working with continuous random variables. But the way Feroz Rasullaga, one of my probability instructors, researcher at the University of Utah, very good mathematician, one way he put it was at some level that someone's going to win the lottery. You just know it's not going to be you. So you get the probability that you win the lottery is 0. And the probability that anyone wins the lottery is not 0. That's the way he put it. So let's move on to discussing probability density functions. So these are the analog to the probability mass function for discrete random variables. The PDF is a non-negative function, which I'm calling f of x, such that for any two numbers a and b, with a less than or equal to b, the probability that a is less than or equal to x, which is our random variable, which is less than or equal to b, is equal to the integral from a to b f of x dx. Naturally, in order for f to be a valid PDF, we must also have that the integral from the integral from negative infinity to infinity of f of x dx. Well, that's the probability that this random variable is between negative infinity and infinity. And that's basically asking for what is the probability that this random variable is any real number. We're basically asking what is the probability that x is a real number. So naturally, this must equal 1 because we know that x will be a real number, and it will be finite. So this is another relation we have to have. Now, regarding this, f itself might not be continuous everywhere. And it's also possible that actually integrating from negative infinity to infinity is a bit much, because actually this random variable is only positive on some interval of finite length, and everywhere else it's 0. So you're integrating for the most part 0. And in fact, we'll see one example of this. we are now discussing the ever famous, maybe too famous, sometimes infamous, not infamous, that's not a word, sometimes infamous normal distribution. We say that a random variable x follows the normal distribution, sometimes denoted like so. X follows a distribution n, mu, sigma. So we say x follows a normal distribution with mean, mu, and standard deviation sigma if it has the PDF v of x parameterized by mu and sigma is equal to, all right, we should probably zoom in for this. It's a little complicated. We have 1 over the square root of 2 pi sigma squared. This fraction multiplying with e to the power negative x minus mu squared divided by, all in the power, 2 sigma squared. It's worth mentioning that often the normal distribution is parameterized not by its standard deviation, but rather by its variance. And you can kind of see why. When I've written this formula down, yeah, it's possible to take this sigma squared and pull it out in front of the square root. But we can put it inside the square root, and then you have, and then everything, you've got sigma squares everywhere, so you could just specify sigma squared directly. And also it feels to statisticians to be, and probabilists, my apologies, to be more appropriate to parameterize by the variance rather than the standard deviation, since it's often easier to work with the variance directly rather than the standard deviation. And in addition to this, you could say that parameterizing with the variance generalizes better when you start talking about multivariate versions of the normal distribution. But this is fine for now. Like, admittedly, at an introductory stats level, it feels somewhat like, since the standard deviation is the more natural measure of spread and the variance a little bit more alien, you could argue that to these students it seems somewhat better to use the standard deviation rather than the variance, but it's fine. So this is the curve. Here is a sketch of the density curve for the normal distribution. We have, so here's kind of what it looks like. We would have, basically, here is the mean. Here is the mean plus 1 standard deviation. And here's the mean minus 1 standard deviation. Okay, so we would have basically a curve that goes up there. Within 1 standard deviation is an inflection point. So it will go from convex to concave at the inflection point. And then it's going to be a symmetric curve and then go from concave back to convex. All right. And this is a simple sketch of what it may look like. Its peak occurs around the mean. And we have our inflection points being within 1 standard deviation of the mean. Okay? So this is whenever you hear the words the bell curve, they are probably referring to the normal distribution. Be aware that the normal distribution is not the only bell-shaped curve that is used in probability and statistics. There are other bell-shaped curves. For instance, there's the t-distribution, there's the Cauchy distribution. I think I encountered a distribution recently that is meant to model it's not really a probability distribution though, but it's kind of like one. When someone gets the coronavirus, or no, not coronavirus, when someone gets a virus
during a pandemic type situation, there's a curve for that looks like the normal but isn't the normal. I can't remember what it is though. It's like the logistic curve. I don't know. But yeah, this is usually when people are talking about the bell curve, all in caps, like capitalized and all that. They're talking about the normal distribution. Here is an R plot of the density function of a standard normal curve. And it's got that bell shape. So, the expected value of a random variable x following this distribution, the variance and the standard deviation will be given next. These should not be shocking at all. The expected value of x is equal to mu. The variance of x is equal to sigma squared, and the standard deviation of x is equal to sigma. So normal random variables are specified by their mean and their variance. Okay. You set the mean and the variance directly with normal random variables. Okay. One property of the normal distribution is the 68, 95, 99.7 rule, which I'm going to sketch out for you. This is basically a rule of thumb for how much of the distribution is within, let's say, within one standard deviation of the mean. So we got mu plus sigma, mu minus sigma, within two standard deviations of the mean. So mu plus 2 sigma, mu minus 2 sigma, and within three standard deviations of the mean. So mu plus 3 sigma and mu minus 3 sigma. Okay. So the peak of the curve happens at mu. And let's see, just kind of getting a sketch. So the inflection points are going to happen within one standard deviation. All right, so we could sketch out the curve to look something like this. Okay, so what this rule says is, let's start out within one standard deviation. The area underneath the curve within one standard deviation is going to be 0.68. So within one standard deviation. So mu plus or minus sigma. All right. Let's go to within two standard deviations. Okay. So within two standard deviations, so the area underneath the curve within two standard deviations. So the area underneath the curve within two standard deviations is going to be 0.95. So this will be mu plus or minus 2 sigma. And then if we go to three standard deviations, so let's have this going. No, let's have this going up and down. Horizontally is rough to draw. Okay. On the other hand, that's kind of a conflicting picture, but you get the idea. Within three standard deviations, the area underneath the curve within three standard deviations is going to be 0.997. So this will be mu plus or minus 3 sigma. Okay. The unfortunate thing about that is I just drew over the text, but I can still read. So let Z follow a normal distribution with mean 0 and standard deviation 1 We then say that the random variable z follows the standard normal distribution. And this distribution is useful since we can relate an arbitrary normal random variable to the standard normal distribution and vice versa. And we can do so like so. As a reminder, z is following a standard normal. Mu is an arbitrary normal random variable. No, not mu. Sorry. Mu is not a random variable. So x is an arbitrary normal random variable, so any mean and sigma. In this case, what you get is that if you take a normal random variable, subtract out its mean, and then divide by its standard deviation, the distribution of the resulting variable will be equal to the distribution of the random variable z. That is, it's following a standard normal distribution, which should make sense. What this operation does is shift the mean to 0. And then what you do is you scale by sigma. Or let's say scale by 1 over sigma. So you both take your curve along the number line. Oops, I didn't want to erase stuff. All right. So what you're doing is you're taking your standard normal curve, which is located at mu. You are shifting it to the left by mu. And then you are compressing the curve. So let's draw like a new curve that's let's draw a new curve that's centered at 0. And then you compress your curve. So it has a standard deviation of 1. All right, that's what that operation is doing. And similarly, we could say that if we take our standard normal random variable z, scale it by sigma, and then add mu, the resulting random variable will be equal in distribution to the random variable x, which is following a normal distribution with mean mu and standard deviation sigma. Right? What this is doing, it's basically doing the opposite. We are scaling by sigma. And then we are shifting the mean to mu. So to sketch out what this is doing, we start out with our standard normal random variable, which is centered at 0. We then take that random variable, shift its mean by mu. So we end up with something over here. And then we scale out its standard deviation. So we get a curve with possibly a different standard deviation. It doesn't have to get bigger. It could get smaller too, but you get the idea of scaling. Okay. So let capital phi of little z be the probability that a standard normal random variable is less than or equal to z. This is the CDF of the standard normal distribution. Then if x is the probability of an arbitrary normal distribution, or of an arbitrary normally distributed random variable, we have we have the following relationship between f and phi. F of x is equal to phi of x minus mu over sigma, where phi is the CDF of a standard normal distribution, which means since we can relate any normal distribution's CDF to the CDF of the standard normal random variable, this means that we only need to worry about tabulating values for phi of z, for the standard normal distribution. in order to work with any normal distribution, which is what's done in Table 8.3 of Devore's book. And often, many of these statistics and probability books will have tables of the CDF of the standard normal random variable. And I even remember buying a study card for Math 3070 for my stats class, and that table came with that card came with a very small table for working with the CDF of a standard normal random variable. And the reason why they're doing that is because you can get all of the information you need for any normal random variable from that table, which is very nice because you can have any real number mean and any positive real number standard deviation and have an infinite number of normal random variables. But you only need to print one table, because once you have the table for the standard normal, then everything works out great. And additionally, let's consider for a second the PDF of a standard of a normal random variable. Let's consider actually first the PDF of a standard normal phi, which we will call just phi of x. That's going to be 1 over the square root of 2 pi. Actually, let's call this phi of z. It's going to be 1 over the square root of 2 pi e negative z squared over 2. And this is kind of a mess, so let's clean that up. Okay. You know by now that CDFs are computed via integration, because all probabilities are computed via integration when you're working with normal random variables. What then is the antiderivative of this? The answer is basically what you see. The thing is, there is no closed form or elementary solution for the antiderivative of a normal random variable. It doesn't exist. It simply doesn't exist. And I think, in fact, it's provable that you can't come up with an antiderivative for a normal random variable, for a normal random variable's PDF, in any elementary form. So at the end of the day, you're just kind of left with saying, all right, this is ranging from negative infinity to I don't know, x, negative infinity to x. You're just left with saying that this is equal to phi of x. Like that, you're kind of left with this unsatisfying answer where you just say, all right, phi is this integral. And yet, at the same time, this is not a problem. In fact, nobody really cares. Nobody really needs to have an antiderivative for what I've written down in black. Nobody really needs it, because we have numerical routines that can compute these integrals. Mathematically, we can still work with it. There's nothing that says that we can't work with this. We have the fundamental theorem of calculus that tells us how to take derivatives of this thing. So we can take derivatives, we can still study its properties, we can study how quickly it grows and decays and stuff like that. There's really no reason we need a simpler expression for the antiderivative of a normal random variable. So we just say this is true by definition and go about our business. Because whenever we need to actually compute what the CDF is, we have techniques for doing it. We can use all of these numerical routines, maybe some Monte Carlo simulations, something like that. There's all sorts of things that we can do to compute the CDF, and you only need to do it once for the standard normal curve. In fact, I think R actually internally, when working with the CDF of of normal random variables is it's working with an internal table that computes probabilities. So, admittedly, I'm teaching this right now in an online format in a context where students are not going to ever enter a testing center. So they don't need to use the table. And if I were teaching this in a regular semester, I would teach students to use the table. And it just feels like right now that's silly because they have access to R and they're not going to want to use the table. And I've never really had a problem with teaching the table from a pedagogical perspective because I feel like using the table was good practice for working with basic properties of the normal distribution. And now I don't really see a reason to use it. I mean, there is still that pedagogical reason, but it's just completely swamped by the convenience of having R around. So we're going to lose that. And I'm actually rather sad that this time I'm not really going to use the table, that I'm just going to compute probabilities using R. But hopefully you can still get the message and understand some of the properties that would be learned by working with the table, such as the symmetry of the normal distribution or working with 1 minus and stuff like that. Okay, if I ever teach this class again in person, maybe I would, and if I were to use these lecture videos again, maybe I would create a separate video for working with the table, but I don't think I will do that now. All right. So, anyway, let's compute the following. We're now working with a standard normal random variable. So remember that this is a random variable with a mean. Ugh, I can do better than that. Hold on. Okay, so this is a random variable. Good grief. Good grief. Come on, just... Some people just don't want to press the undo button. Good grief. This screen. How I hate it. Okay. Okay. So remember that we are working with a standard normal distribution. So it's a distribution, standard at 0, standard deviation 1. I'll just tell you that standard deviation is 1. I want to compute the probability that z is less than or equal to 0. So this is what the normal distribution looks like. This is the area that I want to compute. What is that area? Well, we know the area under the entire curve is 1 because it's a PDF. And we know that we're shading the area to the left of 0, and the 0 is the point of symmetry. So that means half the area. So if you were to fold the curve over on itself around 0, it would have equal area to the left and to the right of 0, which means that this must be half of the area underneath the curve. So that means that this is going to be equal to 0.5 because 0 is the median of a standard normal distribution. All right. Next, what is the probability that z is less than or equal to 1.23? Okay, so what we're computing here is a standard normal curve. Here's 1.23. We are computing the area underneath the curve and to the left of 1.23. Okay, and at this point, I'm going to ask R what that area is. So, okay, so I want P norm. By default, P norm is working with a standard normal curve. So we've got P norm of 1.23. So that's going to be 0.8906, or we'll say 0.8907. So this will be this is equal to 0.8907. Okay. Let's see, next up. Oh, look at that, some R code. And it's basically confirming what we got via R. So, not shocking. All right, next up. The probability that the standard normal variable is between negative 1.97 and 2.1. So this will be, we've got the standard normal curve. Okay, here's 0. Here's 2.1. Here's negative 1.97. And we want the area in this region, the area in between 2.1 and negative 1.97. So how are we going to do that? Well, one thing we could do is say, remembering that we are working with a CDF, that this is going to be the area underneath the curve to the left of 2.1 minus the area underneath the curve to the right of negative 1.97. So you just subtract out the area from the left of negative 1.97 from the area that's to the left of 2.1. You can think of that as you have a piece of construction paper, and this piece of construction paper is the normal curve, including the region underneath the normal curve. That's a really long piece of construction paper, since the normal curve extends from negative infinity to infinity. Right? I never put any sort of bounds on this curve. So I hope you notice that this is a random variable that can take any number, any real number between negative infinity and infinity. So we, but we imagine that we have this. Maybe we clipped it off after a certain point, and which is fine, because after a while the normal curve becomes minuscule, so minuscule. Because it approaches 0 very, very quickly. One way to interpret the 38, 68, 95, 99.7 rule is saying that almost all of the curve is within 3 standard deviations, and there's almost nothing outside of it. So, and that goes even more so for 4 standard deviations, 5 standard deviations, and so on. There's almost nothing there. Anyway, we imagine that we have this piece of construction paper, and we clip off the area at 2.1 and have the area underneath the curve and to the left of 2.1, and then we clip off the area underneath the curve to the left of negative 1.97, and what we end up with is the area that we want. So what we could end up doing is we start out by measuring the area underneath the curve, the area of our construction paper when we did our first clip, when we clipped at 2.1. And we measure that area, and then we clip again at negative 1.97 and measure the area of the part that we clipped off, and then subtract that from our earlier calculation to get the area that's remaining for our construction paper. So this will be phi. Remember that capital Phi is the CDF of a standard normal random variable. So phi at 2.1 minus phi at negative 1.97. Okay, and then we need to compute this. So p norm 2.1 minus p norm negative 1.97. And this is what we get. So we get 0.9577. So we get, so we get that this is equal to 0.9577. Okay. Next example, the probability that z is greater than or equal to 1.8. So this is the area underneath the normal curve that's to the right of 1.8. Okay. And we say that this is going to be, well, we could say that this is the area underneath the entire curve. So here I've shaded the whole thing minus the area underneath the curve to the left of 1.8. Going back to our construction paper analogy, you have this piece of construction paper that's the area underneath the entire curve, and you clip off the part at 1.8, and you're left with the part from negative infinity up to 1.8. So you lost the other part, and you want to figure out the area of the other part. Well, you knew the entire area was 1, so you measure the area of the part the part to the left of 1.8, and subtract that from 1 to get the area that's underneath the curve and to the right of 1.8. So this would be 1 minus the CDF of the standard normal at 1.8. And we can go to R and compute this. So 1 minus P norm at 1.8. And this is going to be 0.0359. So this is 0.0359. Okay, excellent. The probability that it's greater than 5.2. So this is going to be approximately 0. But I'll go ahead and compute this in R and say 1 minus P norm. What was the number we were plugging in? 5.2? Okay, 5.2. All right, very, very, very small number. Not quite numerically 0 because we can go to 16 decimal places, but very, very close. Very small number. And actually, if you were using the table, and if you look at most tables don't go beyond 4 standard deviations. They might even go beyond 3 or 3.5. But you'll almost never see a table go beyond 4 standard deviations. And here we're asking for the area underneath the curve to the left of 5 standard deviations. So if we were actually using the table, which is the context in which these notes were written, we would say, what I would basically tell students is say, this is approximately 0. So don't even bother to look at the table. Just say, this is approximately 0. Okay. Here's some R code that's doing all of these calculations. We also could have done some of that 1 minus stuff using the lower tail parameter. Let's see, is that different from what we had? No, it's not different. So that looks to be about the same. All right, next example. So IQ scores are said to be normally distributed with mean 100 and standard deviation 15. Let Q be a randomly selected individual's IQ score. Compute the probability that Q is between 85 and 115. So, in this case, here's another thing. There's a lot of reasons why I really liked working with the table, and one of the things that was great about working with the table was that it forced you to translate from a normal distribution to a standard normal distribution, or any normal distribution to standard normal. And thus, I felt like it would force students to learn the relationship between any normal random variable and a standard normal random variable. So what we could say here is that this is going to be the probability that 85 minus so Q is going to be, according to this problem, a normal random variable with mean 100 and standard deviation 15. So this will be 85 minus 100 over 15. That's less than or equal to Q minus 100 over 15, which is less than or equal to 115 minus 100 over 15. And this part right here is equal in distribution to a standard normal random variable z. So we could say that this is equal to, after you compute that lower and upper bound, you'll find that this is the probability that -1 is less than or equal to z, which is less than or equal to 1, which is going to be about 0.68 because of the 68, 95, 99.7 rule. So you really wouldn't even have to go the... okay, so 0.68 is very much an approximation. It's not exactly true. But it's kind of close. I think it's true if you round to 2 decimal places. So, well, I'm actually not really sure. But yeah, you do have this. And this is basically forcing us to convert to the standard normal case. The unfortunate thing, though, is that now I could just do this. You could do p norm 115 mean equals 100, and the other parameter is SD is equal to 15 minus p norm 85 mean equals 100, SD equals 15. And we get 0.6826 or 27. If we wanted to, we could instead have written p norm 1 minus p norm -1. And they get the same number using basically that alternate form. Because you might not be converting to a standard normal random variable, but R, I'm pretty sure is. So, all right, there's computing that. So the sad thing is that you can just do that, and now I can't force you to use a table and convert convert to a standard normal random variable. That's unfortunate. Okay, so the probability that Q is greater than 90. You know what? I can't force you to do it, but I can still do it because I still have a point to make, right? So this is going to equal the probability that Q minus 100 over 15 is greater than 90 minus 100 over 15, which is equal to 1 minus the CDF of a standard normal random variable at a 90 minus 100 over 15. This part becomes 10 over 15, or negative 10 over 15, which is negative 2/3. So I would say this is going to be phi at... I'll even round it. I'll even convert it to a decimal number. So negative 0.67, which is approximate, but this is supposed to be negative 2/3. And then I go to R and compute this and say this is 1 minus p norm negative 2/3, which is 0.7475. So this is approximately equal to 0.7475. All right. Next up, the International Society for Philosophical Inquiry requires potential members to have an IQ of at least 135 in order to join the society. This is one of those so-called genius societies. Based on this, what proportion of the population is eligible for membership? So this is the probability that an individual's IQ is at least 135, which is equal to the probability that Q minus 100 over 15 is greater than or equal to 135. Hold on. Let's move this. So this is equal to probability that Q minus 100 over 15 is greater than or equal to 135 minus 100 over 15, which is equal to the probability that this is going to be 1 minus the CDF of a normal random variable, or 1 minus phi so 135 minus 100 over 15 is 35 over 15, which is 7/3, which is about 2.33. Okay, so about 2.33. So 1 minus p norm 2.33. Actually, we'll just do 7 divided by 3. So 0.0098. So this is approximately 0.0098. Okay. And here is some R code where I'm actually calling these mean functions SD function, so mean SD parameters, also using lower tail, rather than doing 1 minus the CDF, and so on. All right, so that was all trying to compute probabilities, but sometimes we want to compute quantiles. So we've got the notation Z alpha, which means that the CDF of at Z alpha is equal to 1 minus alpha. We can relate this back to general percentiles defined for arbitrary normally distributed random variables, because these are the percentiles of standard normal random variables. Okay? So this is going to, so we have in general eta p is going to be sigma z 1 minus p plus mu. That's our percentile formula. And z1 minus alpha can be found using table 8.3 using a reverse lookup, but since you now have R, there's really no point about discussing reverse lookups like this. Okay. I mean, I felt like they were good practice, but we're now not going to be doing that anymore. All right, so what is Z 0.5? That's the median of a standard normal. Z 0.5 is the area where the curve is split in two equal parts, and that's going to be 0. What is Z 0.05? Well, what we could do is say, all right, let's go to P norm. No. We're not using P norm anymore. We're using Q norm. So Q norm 0.05. So you could put in 0.99. Put in 0.95 instead. That would get us the same thing. This is going to be 1 minus. So this is 1 minus 0.05. Or alternatively, we could do Q norm 0.05 lower dot tail equals false. And that also works. Those all get us the same number. So, in the end though, this is about 1.64. So this is, Z 0.05 is about 1.64. Okay, what are the first and third quartiles of the standard normal distribution? So what we're looking for is Z. So the first quartile will be Z 0.75, because remember we're doing up. So the so here the subscript of the Z is the upper tail area. So this is the first quartile. And the third quartile is Z 0.25. This is Q3. All right, so what are those going to be? Well, we go to R and say Q norm 0.75 lower dot tail equals false. So we get negative 0.67. So negative 0.67. And this one, well, actually, I'm not even going to bother compute it because I know what it is. It's 0.67. Because we're working with a symmetric curve. Since we're working with a symmetric curve, if we know one of those things, then we know the other one. Because if the area underneath the curve to the left of z 7.75 is 0.25, the area underneath the curve to the right of z 0.25 is also 0.25. So all we ever did was just flip over the y-axis where x is equal to 0. Oh, no, let's not put a y there. That's just confusing. But my stupid undo button isn't working. Ugh. Gosh. Why does stuff have to be so moody? Anyway. Well, since we're working with a symmetric distribution, we actually have a property that I think gets written down later. Where did I write it down? Was I supposed to write it down up here? Where did I write it? I know I wrote it down. I know that I plan on talking about it at some point in these lecture notes. Oh, I wrote about it on page 21, but basically I'll just cut to the chase and write it right now. So z alpha is equal to negative z 1 minus alpha. So basically, you can just flip over the y-axis. So change the sign and work with 1 minus that area, and you can get the same quantiles. So, but if it makes you feel better, I'll go ahead and compute it. And this is 0.25. Yeah. So what I did basically was exploit the symmetry of the standard normal distribution. It's symmetry around 0. All right. Description of the random variable q from example 11. So using that, answer the following questions. Mensa International requires individuals have an IQ score that would place them in the top 2% of the population. What is the minimum IQ score needed to be a member of Mensa? Well, that would be... so the standard deviation is 15. We've got z, so top 2%, so that's going to be 0.02. The upper tail area is 0.02 plus 100. And this is going to be, let's see... We've got 15 times Q norm, 0.02, lower dot tail equals false, plus 100. 130, or I guess he'd round it to 131. So we'll say 131 after rounding. So 131. You need to have an IQ of 131 in order to be a member of Mensa. There's an alternative way to do that, though. We could have instead done Q norm 0.02, mean equals 100, SD equals 15, lower dot tail equals false. That would have also worked. Okay. The part of the population with the lowest 5% of IQ scores is considered to be intellectually disabled. What is the highest IQ score needed to be in this group? Okay, so that means that we are looking at z 0.95, or actually we're asking for eta of 0.05. Up here in this problem, we were looking for eta of 0.98. Okay, so this is going to be 15z 0.95 plus 100, and then we go and compute that. So in this case, we got 0.95 now. This is going to be 75.32, so we'll say about, after rounding, 75. So if you have an IQ score of 75 or lower, you're considered intellectually disabled. Okay. So, right, there's some R code that's doing the same thing. So due to the symmetry of the normal distribution, we have the following useful identities for phi.
1 second.
Okay, we have that the CDF at z is equal to 1 minus the CDF at negative z, which what this is saying is if you were looking at, so this is a standard normal distribution. If you were looking at the area underneath the curve and to the left of z, another way you could compute that quantity is look at the area underneath the curve and to the right of negative z, which is what you get when you flip over the y-axis, and then subtract that from 1 to get the red area underneath the curve. So the area above negative z is going to be equal to the area below z, or the area to the right of negative z is equal to the area to the left of z, because of the symmetry of the curve. And equivalently, well, as a consequence of this, we have z alpha is equal to negative z 1 minus alpha. That's our immediate consequence. All right, so as mentioned before, phi can be used to approximate the CDF of other random variables. So it turns out that the normal distribution can be used to approximate the CDF of other random variables, or approximate other random variables, basically. Which, of course, mattered more historically when we didn't have... when we had to basically physically print out tables for random variables. But you still want to be able to get probabilities for binomials with large parameters, large n, or Poisson random variables with large mu. But in this situation, like in the world in which we currently live, that's less of an issue because software doesn't ask you how big n is; it just works. So, all right. So, well, I guess it does literally ask you, but it's not like you put in the wrong number and it will just not work. Unless, of course, you put in something that's really big to the point that software can't handle it, but that's highly unlikely. Anyway, still, the fact that certain random variables can be approximated by normal random variables is not only important, it's getting to fundamental theorems of statistics and probability that will be discussed in Chapter 5. So, let's say, for example, let's work with a binomial random variable when n, the sample size is large. The CDF of a binomial random variable at x with parameters n and p, and here we're assuming that n is somewhat large. You should probably say, well, okay, so a rule of thumb is that n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. That's one rule of thumb that they're using. We could probably say that if your p is between 0.1 and 0.9, then a sample size of 40 is probably fine. So this is going to be approximately equal to the CDF of a standard normal random variable evaluated at x minus the mean of the random variable, which is np, because that's the mean of a binomial, divided by the standard deviation of a binomial, which is n times p times 1 minus p. And then, in addition to this, we do plus 0.5. The plus 0.5 is what's known as a continuity correction. It accounts for the fact that we are using a continuous random variable to approximate a discrete random variable. If you didn't do this, then you often end up with some numerical inaccuracy with the approximation. The approximation is still at some level true, but it's just off, and you get better approximate computations for, say, the CDF when you include this continuity correction. I think the justification for why you add plus 0.5 is you could imagine that you have this probability mass histogram and your the PDF or CDF of the normal curve would be going through it basically at the left endpoints. So you'd have something that's looking like this. And if you shift everything over to the right, yeah, I think it's to the right when you do plus. No, it's to the left. But when you shift the curve, oops, the undo button is not working. When you shift the curve over a little bit, you get like a better pass through these histograms. So it's like recentering so that it's centered evenly on the probability histogram, or this probability mass function understood as a histogram. Anyway, let's do an example. A manufacturer will reject a batch of widgets if in a sample of 100 randomly selected widgets of the batch, 15 or more are defective. If 12% of the widgets in the batch are defective, what is the probability of rejecting the batch? So the random variable in question is, we'll call it S. And it's following a binomial distribution. The parameter N is 100. And the parameter P for the probability of getting a defective widget is 0.12. Okay? So the approximating normal random variable follows a normal distribution with what is going to be the mean? Well, it's going to be the sample size times P. So that's 12. And then we've got standard deviation, which is going to be square root of 100 times 0.12 times 0.88. Okay, so the standard deviation is about 3.25. So 3.25. This is the distribution of the approximating normal random variable. So S's distribution is approximate. So S is approximately equal in distribution to X. So then when we want, reject the batch. When is the batch rejected? The batch is rejected when 15 or more widgets are defective. So we're looking at the probability that S is greater than or equal to 15. And this is going to be 1 minus the CDF of this random variable at, at 14. And it's got parameters 100 and 0.2 and 0.12. Okay, and this is, according to our normal approximation, approximately equal to 1 minus phi. And we've got 14 minus 12 divided by 3.25. And then we add in the continuity correction, 0.5. And what is this going to be equal to? Well, we've got 1 minus p norm. So we've got, 14 minus 12 plus 0.5 divided by 3.25. So 0.2209. And just for reference, we could have alternatively computed P binom, and we would have used 14, size equals 100, prob equals 0.12, and we would have said lower.tail equals false. Yeah, so that's pretty close to what we got using the normal approximation. Okay.
All right, so scrolling down. Oh, did I? Oh, something's different. On the other hand, is the R code wrong? Okay, it looks like I might have made a mistake here. So the probability that s is greater than or equal to 15 is the probability that is 1 minus the probability that s is less than or is strictly less than 15, which is 1 minus the probability that s is less than or equal to 14. So I think that my R code in this, yeah, I think that I did not put in, yeah, or, curious. I don't know. I'm thinking actually that this might be wrong. On a second look. Okay. But you get the point at the very least. And by the way, I would suggest using the normal approximation at the very last step. So right when you're about to compute something that you don't know how to compute. So like for example, I guess I should probably write down what steps I've kind of been omitting. I can say this is the probability that s is, no, this is 1 minus the probability that s is less than 15, which is 1 minus the probability that s is less than or equal to 14. So here I basically was still treating s as if it were a discrete random variable. You should still do that. You should, like, if I was treating this as a continuous random variable, I would not be caring so much about whether I was working with less than or equal to. But you should still treat your random variable that you're approximating with a normal random variable as if it's discrete up until the final point when you need to compute something like the CDF. Okay? So that's what I recommend. All right. The approximation works for Poisson random variables as well. When this lambda parameter is large, or I don't know why I wrote lambda here. I think that might be because the book's using lambda. I'm not really sure why. Because of what I remember is that in chapter 3, I was using mu to write down Poisson random variables. Okay, but whatever. So in this case, the approximating distribution for a Poisson random variable, let's suppose that x follows a Poisson distribution with mean parameter mu. Then we could approximate it with y, which is following a normal distribution with mean mu and standard deviation square root of mu, because the standard deviation of a Poisson random variable is the square root of mu. Okay, so suppose that x follows a Poisson distribution with parameter 100. Let's estimate the probability that x is less than or equal to 110. So the probability that x is less than or equal to 110 is approximately equal to phi at 110 minus 100 plus 0.05, that's the continuity correction, divided by the square root of 100, which is 10. So this is going to be the CDF at 10.5 divided by 10, which is 10.5 minus 10. Divided by 10. Oh yeah, that's 1.05. So that's going to be 0.8531. Okay. Let's compare that to what we would have had
if we use the Poisson distribution directly. So 110 and lambda is equal to 100. Oh, very close. Very, very close. So a good approximation. All right. Okay, that concludes this section. This is a very important section. Very, very important, because the normal distribution is a distribution that is appearing all over the place. So, and not just in this chapter, but in later chapters too. Chapter 5, Chapter 7, Chapter 8, you're going to be using the normal distribution all the time. It's going to be assumed that random variables are normally distributed. So you need to get comfortable with this distribution. All right, so work on problems for this. Make sure you understand it. If you don't understand it, fix that. And yeah, it's your responsibility to fix it. Part of the way you fix it is by asking me what you don't understand. Right, so part of how you fix not understanding something is getting help when you need it. All right, from whoever could possibly help you. But you need to fix what you don't understand. Please, please learn the normal distribution inside and out, and you will be rewarded for it. All right, so that's it for this section, and I will see you in the next section when we talk about exponential random variables, which we've already talked about quite a bit, and also the gamma distribution, which is an interesting distribution and often shows up in applications and also in a more theoretical setting. Okay, all right, so see you then.